Imagine a single thread capable of holding the weight of a skyscraper, strong enough to ride out a storm over the ocean or to lift a drilling rig from the depths of the sea. How is this living armor born from a cold piece of steel in a world where weakness is not an option? Why does the fate of a billion-pound project hang on a microscopic flaw in a single wire? We will journey from the searing heat of the furnace and giant carousel machines to the most brutal tests of strength and endurance, where the line is drawn between what will hold and what will break. Watch to the end and you'll uncover a secret that will make you look at a simple steel cable in an entirely new light. You'll find them at work in maritime cranes, hoisting modules onto oil platforms, deep in mine shafts, erecting wind turbines in the middle of the ocean, and in the construction of monumental bridges and skyscrapers. The material used to create these immense ropes is a high-alloy carbon steel, but not just any steel. This is a grade perfected with alloys. Chromium, nickel, and sometimes molybdenum are added to the mix, each with a specific purpose. Chromium enhances corrosion resistance, while nickel adds strength and ductility. These elements transform the metal into a form of engineered armor. And to prepare this steel for weaving, it must first be drawn into wire. The initial stage is rolling. Steel billets are passed through rollers, progressively reducing their diameter. Next comes thermal quenching. The wire is heated to extreme temperatures and then rapidly cooled to create a precise molecular structure, making the steel both hard and resilient. The third step is coating. This is chosen based on the final application: a zinc coating, galvanizing, for protection against rust, or a polymer sheath for operating in aggressive environments like saltwater. But even after all this, it is not yet a finished wire. Now comes computerized calibration. Each wire is inspected by high-precision machines, measuring not only its diameter down to the micron, but also checking for microbends, tension, and symmetry. A deviation of 1/100th of a millimeter could be critical, because thousands of these wires will soon act as one. A single weak segment creates a potential point of failure. Once every wire has been treated, tested, and calibrated, one of the most spectacular stages begins: the stranding of the rope. And this isn't simply twisting wires together. It is a mathematically precise system of tension, angle, and the interplay of hundreds of individual elements. At the heart of every rope is a core, which can be steel or a synthetic fiber. It is around this core that strands of steel wire are laid in spirals. Each strand can contain dozens, even hundreds of wires, all woven in a strict, predetermined pattern. The goal is to distribute the load perfectly evenly along the entire length. Every rope has its own configuration: the angle of the lay, the number of strands. For flexibility, more thinner wires are used. For rigidity, fewer but thicker ones. The process takes place on giant stranding machines that operate like carousels. They rotate slowly, methodically, drawing individual wires from dozens of bobbins. A single machine can construct a rope over 100 meters long. As it's woven, every single wire is held at a precise tension, managed in real time by an automated system. If just one wire is twisted or over-tightened, the rope could lose its integrity. The entire operation is continuously monitored. Sensors detect the slightest vibration, and the machine will halt automatically if a fault is found. Human oversight here is minimal. Interestingly, some ropes have a composite structure, an outer layer with polymer insulation or fire-resistant coating housing internal metallic strands with different properties. When the stranding is complete, the rope is still not ready. It now faces one of its most critical trials: testing and certification. This is where it must prove it can handle the forces it was designed for. The first test is for breaking strength. The rope is secured between two colossal hydraulic grips, which then begin to pull with incredible force. We are talking about hundreds of tons of load, gradually increasing. The aim is to find the ultimate tensile strength. Ideally, the rope must withstand 3 to 5 times the load it will carry in the real world. But surviving maximum force isn't enough. It also undergoes a fatigue test, where the rope is repeatedly tensioned and relaxed, simulating thousands of real-world operational cycles. Separate tests are conducted for torsion, where the rope is twisted to assess its rotational stability. This is vital for applications where the load vector is constantly changing. Another critical phase is the environmental trials. The rope is submerged in salt water, frozen to minus 40 degrees Celsius or heated to over 100 degrees. Some are tested for resistance to UV radiation, chemicals, or even fire, because the conditions on a North Sea oil rig or in a mine shaft are nothing short of extreme. Only after passing this battery of tests can a rope receive certification from international bodies like Lloyd's Register or DNV. Every rope is given an individual serial number linked to its testing protocols. In some cases, its pedigree is even recorded, showing which steel mill produced the metal for every single wire. Once it has passed every trial, the rope is wound onto enormous reels, 20, 50, or even 100 meters long, and transported on special platforms. A single reel can weigh several tons. On site, the rope is installed with millimeter precision, and only after a final inspection does it begin its work in a world where there is no margin for error.
Every year, enough glass fiber rebar is produced worldwide to challenge the dominance of steel itself. This isn't science fiction, it's modern manufacturing. The world spends billions fighting rust, repairing bridges and car parks destroyed by corrosion. But there is a solution. A composite material that is twice as strong as steel, 4 times lighter, and simply does not know the meaning of the word rust. The market for this material is growing at 12% a year, and today you will see how hundreds of bobbins and a barrel of resin give birth to the building material of the future.
It all begins at one end of a vast workshop, in front of a structure that looks like a giant library for thread. It's called a creel. On a wall several meters high, hundreds, sometimes thousands of huge bobbins are mounted in neat rows. Wound onto each one is a fine glass thread, or roving. This isn't the glass from your windows. It's a special glass fiber produced by melting glass and drawing it through microscopic holes. The result is a thread thinner than a human hair, but with incredible tensile strength. This will be the skeleton. From each of these hundreds of bobbins, a single separate thread is drawn, and they all converge into one thick, fluffy bundle.
This river of glass fiber now begins its journey. It passes through a system of guides and tensioners. Each of the thousands of threads must be held at exactly the same tension. If one thread sags while another is too tight, the load in the final product will be distributed unevenly, compromising its strength. The dry glass bundle is then slowly submerged in a bath filled with a thick, sticky, honey-like liquid. This is the polymer resin, the flesh that will be built upon the glass skeleton. It's a complex chemical cocktail. The base is typically a polyester, vinyl ester, or epoxy resin. To this, a hardener is added, a catalyst that will trigger a chemical reaction, turning the liquid into a solid plastic.
Various additives can also be mixed in. Pigments for color, UV inhibitors to protect the rebar from sunlight, and fire retardants. The purpose of this bath is to impregnate every single tiny fiber. The bundle must be completely saturated in the resin, leaving no dry spots. Now heavy and soaked in sticky resin, the bundle emerges from the bath and heads towards the point of its creation, the forming die. This is the heart of the entire process. Imagine a thick steel plate with the perfectly round, polished hole, its diameter precisely matching that of the future rebar. The die is heated to a specific temperature.
As the wet bundle is pulled into this hole, several things happen at once. First, the die acts like a press, squeezing out all excess resin. Second, it compacts all the glass fibers tightly together, forming a perfectly round rod. Third, the heat from the die initiates the first stage of the curing reaction. Emerging from the die, we can already see the familiar shape of a rebar, but it is still soft and vulnerable. So how does it get its famous ribbed surface? Immediately after the die, while the rod is still hot and pliable, a special glass fiber strand is wound around it. A thin resin-soaked thread is wrapped in a spiral around the surface of the rod, creating the textured pattern. The formed and wrapped rod now enters the longest part of the machine, the curing tunnel, or polymerization oven. This is a long chamber which can stretch for dozens of meters, where a high temperature, typically around 200 degrees Celsius, is maintained. Here, the final transformation occurs. This isn't just drying. Under the heat, the resin molecules begin to rapidly link together, forming a strong, rigid, three-dimensional grid. The liquid, sticky syrup turns into an exceptionally strong and hard composite material, permanently bonding millions of glass fibers into a single, monolithic rod. As the rebar moves slowly through this hot tunnel, it acquires its final, rock-hard strength.
But what is pulling it through this long journey? At the end of the line sits a special pulling device. It typically consists of two caterpillar track mechanisms like those on a tank, positioned one above the other. They gently but very firmly grip the finished solid rebar and pull it towards them at a constant, precisely controlled speed. It is this machine that provides the force to draw the glass fibers through the resin bath, the forming die, and the oven. The speed of this movement is one of the most critical parameters controlling the quality of the final product. And so, from the other end of this long production line, an endless, perfectly straight, hard and hot GFRP rod emerges.
The final act is cutting. An automatic saw is mounted across the line. It synchronizes with the speed of the moving rebar, and at the right moment, it makes a quick forward dash, and with a sharp whiz, it cuts a standard length, for example 6 or 12 meters, from the continuous rod. It then returns to its starting position. The finished, still warm rebars roll onto a cooling table, after which they are collected into bundles, tied, and sent to the warehouse. And so, before our very eyes, thousands of fragile glass threads and a barrel of sticky liquid have journeyed through baths, presses, and ovens to become the lightweight yet incredibly strong building material of the future.
The market for glass fiber rebar isn't yet a giant like the steel market, but it is the boldest newcomer, rapidly gaining traction. The global market for this material is already valued in the hundreds of millions of dollars, with staggering forecasts. It's expected to grow by 10 to 12% annually. Now for the key features that are making the steel industry nervous. The first and most obvious is weight. GFRP rebar is roughly 4 times lighter than steel of the same diameter. Imagine a lorry. It can deliver 4 times more GFRP rebar in a single trip than it could steel.
On the construction site, 2 workers can easily carry entire coils of GFRP rods, whereas moving steel requires a crane. This represents a colossal saving in logistics and labor. Second is strength. And here, GFRP steps into the ring and knocks steel out in the first round. Its tensile strength is approximately twice that of standard steel rebar. This means that for some structures, a smaller diameter rebar can be used, saving even more on weight and volume.
But the ultimate advantage, the true superpower of GFRP, is its war on rust. The main enemy of any reinforced concrete structure, from bridges to car parks, is not the load, it's rust. Water and salts penetrate through microcracks in the concrete, reach the steel rebar, and it begins to corrode. Rust expands in volume and literally bursts the concrete from within. And GFRP? It simply laughs in the face of rust. It is chemically inert. It is completely indifferent to water, salt, acids, and alkalis. This means the lifespan of the structure increases dramatically. A concrete structure reinforced with steel is designed for about 50 years. A structure with GFRP rebar can easily be designed for a lifespan of over 100 years. Every year, people around the world devour over 50 billion pieces of fried chicken, millions of burgers, and 1 billion pizzas. But hardly anyone stops to think about what's behind those perfectly golden crusts and aromas we've come to take for granted. What if I told you that inside these flavor factories, technologies operate with more precision than surgical instruments, and recipes are guarded more closely than military secrets? In this video, you'll see how the food the entire planet loves is made, from KFC's secret blend of 11 herbs and spices to Domino's billion pizza assembly line. Stick around until the end, and you'll learn things they've never revealed, even in their advertising.
Do you love KFC fried chicken as much as I do? Its story doesn't start in a fryer, but on massive American farms where chickens are raised under the strictest safety standards. After arriving at the plant, each bird flows through a cascade of automated systems. Artificial intelligence, like a vigilant guardian, analyzes images from high-resolution cameras, filtering out any defects. This isn't just a conveyor belt. This is a river of raw material flowing through an incredibly complex control system. Only the best specimens, passing this digital selection, move to the next stage. This is the first level of guarantee that every single piece will be perfect.
What follows is a processing stage that resembles a high-tech ballet. The carcasses are plunged into water at a precisely calibrated temperature of 140 degrees Fahrenheit to soften the feathers. Then, automated machines equipped with thousands of rubber fingers spinning at tremendous speed strip away the plumage in seconds. These units can process up to 10,000 carcasses per hour. After that, laser-guided robotic cutters divide the carcasses into 9 standard parts with surgical precision, no more, no less. Every single piece gets weighed, scanned, and assigned its own digital footprint in the production management system.
But here's where things get really interesting. The chicken gets marinated in a special brine that makes the meat incredibly juicy. And then comes the sacred ritual, the breading. That legendary secret blend of 11 herbs and spices, a recipe Colonel Sanders developed way back in 1940, remains one of the most closely guarded trade secrets in the world. Word is, the original recipe sits in a vault at KFC headquarters. The blend ships to factories in 2 separate bags, and they only mix the contents right before breading. The breaded chicken gets fried in special pressure fryers at 375 degrees. It's that pressure that locks in the juiciness inside while creating that iconic crispy coating outside.
If beef's more your style, welcome to the world of the Big Mac. McDonald's uses only 100% beef from verified suppliers. After rigorous inspection, the meat's ground and formed into patties weighing exactly 1.6 ounces. This precision isn't a quirk, it's what guarantees each patty cooks perfectly. To preserve freshness without preservatives, the patties undergo flash freezing at 0 degrees Fahrenheit. This allows ice crystals to form instantly without damaging the meat structure. Big Mac buns are baked on automated lines, where the dough is mixed, shaped, and topped with exactly the amount of sesame seeds the standard requires.
Vegetables, crispy iceberg lettuce, onions, pickles, go through multiple rounds of washing and slicing. But the real secret of the Big Mac? That's the sauce. Its exact recipe is another mystery, guarded like classified intel. In restaurants, frozen patties get seared on a double-sided grill at 425 degrees for just 42 seconds. That's the perfect window. Golden crust on the outside, juicy meat inside. Then the crew, like soldiers on an assembly line, stacks the burger in strict order in mere seconds. That's why this icon of an era has stayed exactly the same for over 50 years. Did you know the Domino's pizza story started with a $500 debt? In 1962, 2 brothers bought a small pizzeria in the American town of Ypsilanti. Their main promise, which became the driving force of the entire industry, pizza delivery in 30 minutes. This rule sparked a revolution. Today, everything starts with the dough. At giant facilities, flour, water, yeast, and oil get mixed in industrial mixers. The dough rises in chambers with controlled humidity and temperature. Then it's divided into portions, shaped into round bases using presses, and flash frozen. That's what makes it possible to deliver identical dough to thousands of pizzerias around the world.
Tomato sauce is made from specially grown tomato varieties that get processed into puree within hours of harvest. Mozzarella is shredded on industrial graters, and pepperoni is sliced with laser precision. Sauce gets spread on the base, cheese is sprinkled on top, and exactly the number of pepperoni slices required by the standard gets laid out. Then the pizza heads into a conveyor oven at around 500 degrees Fahrenheit. Domino's Pizza is the world's largest pizza chain, cranking out roughly 1 billion pizzas every year. Their newest automated dough production center in Indiana can produce enough raw dough for tens of thousands of pizzas daily.
But how does all this food, produced in giant factories, make it to our table while staying fresh and flavorful? Behind it lies an invisible yet incredibly complex system, cold chain logistics. It's the actual nervous system of the global fast food empire. Frozen patties for the Big Mac and chicken for KFC travel in special refrigerated trucks where the temperature is maintained at -4 degrees Fahrenheit, accurate to within a degree. Sensors transmit temperature data to a central server in real time. Any deviation, the system sounds the alarm. Buns, vegetables, and sauces are transported in separate compartments at their own optimal temperatures. It's a whole science ensuring products don't thaw and refreeze, which destroys their texture and flavor.
Why does a Big Mac in Tokyo taste exactly like one in New York? The secret lies in sensory analysis science and obsessive consistency. Every major company has what are called sensory panels, teams of specially trained tasters with superhuman taste and smell. Their job? Sample products and compare them against the gold standard, a reference sample stored in the lab. They evaluate dozens of parameters: the saltiness of the sauce, the crunch of the lettuce, the softness of the bun, the aroma of the patty. Any deviation from the standard, even the slightest, and the entire batch can be rejected. It's a genuine flavor DNA code that companies replicate and reproduce worldwide. So no matter where you are, you always get that same familiar taste from childhood.
So what's the main secret promised at the start? It's not 11 herbs and spices, and it's not some sauce recipe. The real secret these giants are hiding is creating consistency. It's psychology. The secret is they're not just selling food, they're selling comfort. In a world full of uncertainty, you always know exactly what your Big Mac or chicken wing will taste like. This isn't just lunch, it's an anchor of stability, a flavor that hasn't changed in years and decades. They took the most complex processes, from animal genetics to global logistics to flavor chemistry, and packaged them in a simple cardboard box. And they made us believe it's simple, fast, and always tastes the same. And that's their real genius.
Every year, over 100,000 kilometers of new railway tracks are laid worldwide, enough to circle the Earth several times. But few people stop to think about how a perfectly straight strip of steel, capable of withstanding the weight of multi-ton trains and speeds of over 300 kilometers per hour, is born from a piece of scrap metal. Inside furnaces, the temperature reaches 1,500 degrees Celsius. Molten metal flows like solar lava, and precision is measured down to tenths of a millimeter. And most importantly, there is a secret here that is rarely shown publicly. If you watch until the end, you'll learn this secret that allows rails to last for decades without a single joint.
First, a steel mixture needs to be made. Scrap metal, iron ore, coke, and limestone, the raw materials that will become the future rail, are fed into the furnace. The temperature in a blast furnace reaches over 2,732 degrees Fahrenheit. Under this infernal heat, the metal becomes liquid, acquiring the color of the red-hot sun. Workers carefully monitor the composition. Even an extra 0.1% of carbon can make the rail brittle or too soft. After melting, the molten steel is poured into molds, metal ingot molds that form rectangular blocks called ingots or slabs. They don't yet look like a rail, they are just bars several meters long, over 30 centimeters wide. After pouring, each such blank is cooled, but not completely. It is kept warm to reduce the load during rolling. This stage is the foundation of everything. If the steel is of poor quality, even perfect rolling won't save the situation. So control here is almost a ritual. Chemists check the composition, metallurgists control the temperature, and automatic sensors record the uniformity of cooling. And only when everything matches down to the last parameter is the blank sent further, into the fiery furnace of the rolling mill. In the rolling mill, massive bars, up to 20 meters long, are heated in furnaces to a temperature of over 1,200 degrees Celsius. The metal becomes plastic, like dough, but retains its density and strength. The hot blank is immediately fed into reversing rolling stands. These are huge machines with heavy rollers. It passes through them several times, first to reduce the thickness, then to give it the correct shape.
Each pass involves compressing and stretching the metal, which gradually transforms from a simple bar into a future rail with a complex cross-sectional profile, with a head, a web, and a foot. To achieve precise geometry, finish calibration rolling is used. This is like the final polishing of the shape. The tolerances at this stage do not exceed 0.3 of a millimeter. Immediately after rolling, the rails, still hot, undergo a cooling process. They are evenly blown with air or left to cool in an open area. It is important that the cooling is symmetrical, otherwise the metal may warp. To ensure a smooth, impact-free ride at high speed, individual rails are welded into long sections, up to 400 meters without a single joint. The main method is thermite welding.
In a special mold between two rails, a gap of a few millimeters is left. A molten steel mixture formed as a result of the reaction of powdered aluminum with iron oxide. The temperature reaches as high as 2,500 degrees Celsius is poured there. This melt penetrates both parts of the rail and envelops the joint zone. When it solidifies, a monolithic joint is formed, stronger than the rail itself. After this, the excess metal is cut off, and the weld site is ground to a perfectly level surface without any protrusions. Every joint is inspected with ultrasound or eddy currents so that no hidden microcracks remain. Such long rails are easier to transport than it seems. They are wound onto special drums or transported on platforms with swivel nodes.
And at the construction site, the sections are joined again, this time by welding or using special bolt joints. The result is a rail string that stretches for kilometers without a single click. The same silent glide that we are used to taking for granted on high-speed trains. But first, after rolling and welding, the rails are still alive. Stresses remain inside the metal, and the grain structure needs stabilization. This is where heat treatment comes into play, which gives the rail strength, wear resistance, and durability. And it looks almost like a metallurgical spa session. The rail is rapidly heated to high temperatures, about 1,832 degrees Fahrenheit. This is done in furnaces up to tens of meters long, where the temperature is controlled with degree precision. At this point, the crystal lattice of the steel transitions to a new state, austenitic. But the main part begins after.
The rail is instantly cooled. Jets of water under high pressure are directed along the head and web, the very part on which the wheel rolls. The temperature drops in a flash, and a martensitic structure forms in the metal, an extremely hard, wear-resistant phase. But to avoid brittleness, the rail is slowly heated and cooled again, This balances the structure, relieves excess internal stresses, and ensures that the rail will withstand both frost and heat, and thousands of trains a day. As a result, the metal holds its shape and withstands a pressure of tens of tons per square inch without deforming. Before the rail hits the road, it goes through a whole series of rigorous tests, as if it wants to join the army of high-speed transport. In special laboratories, it is tested for strength, hardness, geometry, and internal defect.
First, ultrasonic inspection. High-frequency waves are sent into the rail. If there is a micro crack or a void somewhere inside, the signal is reflected and reveals the problem. Then, hardness measurement along the entire length to ensure that the heat treatment was uniform. In parallel, the straightness and profile are checked. Laser sensors scan every inch, detecting even minor curvatures that could cause vibration or wear. And finally, a bending and impact test. A fragment of the rail is loaded with a pressure tens of times greater than the weight of a train to make sure it will withstand any challenges on the route. When the rail has successfully passed all the tests, it's time for the most responsible journey, to the installation site. But how do you transport giant metal strips over 90 meters long? Ordinary trucks can't handle it. Here, special railway platforms with curved supports are used, which reduce stress and prevent the rail from sagging or vibrating during movement. Sometimes rails are transported already welded into even longer sections of 400 to 600 meters. Before installation, the rails are heated or cooled depending on the ambient temperature. This is necessary to compensate for the thermal expansion and contraction of the metal. Otherwise, in the heat, it will buckle, and in the cold, gaps will form. In practice, each rail is laid taking into account these physical changes. Usually, this is a point of no thermal stress.
There's something almost poetic about watching a massive steel plate, thick as your fist, transform into a perfect cylinder. What we're seeing here is one of Central Europe's finest engineering firms working with a steel plate 4 3/4 inches thick, nearly 10 feet wide, destined to become a cylinder with a 55-inch diameter. For those of us who remember when heavy industry was the backbone of manufacturing, this is the kind of craftsmanship that built the world we know. The star of this operation? The plate rolling machine. And let me tell you, this Italian marvel is about as perfect as metalworking equipment gets. The company's been perfecting this craft since 1946, right after World War II, when Europe needed reliable machinery to shape the infrastructure of the modern age. The machine operates on a 3-roller pyramid principle, which has been the gold standard for rolling heavy plates since the Industrial Revolution, though the precision we're seeing here would have blown the minds of craftsmen from that era. Here's how this beautiful process unfolds. A steel plate, which has been preheated to reduce brittleness, gets positioned between 3 massive cylindrical rollers arranged in a triangular configuration. The 2 bottom rollers are the driving force, rotating in synchronized harmony to pull the plate through, while the top roller, which can be hydraulically adjusted to within fractions of a millimeter, applies downward pressure, creating the curvature. Think of it like rolling out dough, except this dough weighs several tons and could support a building. The operator, working from a computerized control panel, inputs the desired diameter and thickness parameters. The machine's sophisticated sensors continuously monitor the bend radius, making real-time adjustments through hundreds of hydraulic cylinders. Remarkably, despite working with such massive forces, the machine achieves tolerances that would make a Swiss watchmaker proud. The plate makes multiple passes through the rollers, bending a little more each time, gradually approaching that perfect cylindrical form. This incremental approach prevents stress fractures and ensures uniform curvature along the entire length. As the plate begins its transformation, you can actually see physics at work. The outer surface of the bend stretches while the inner surface compresses, and the metal flows like frozen honey, maintaining its structural integrity while taking on this new shape. Now, let's step into the world of heavy forging, where tradition stretches back to the blacksmiths of ancient Rome. Except now we're working with hammers that make Thor's hammer look like a toy. What's especially mesmerizing is the combination of raw power and surgical precision. We're watching parts being forged that can weigh up to 250 tons. The process begins long before the hammer ever strikes. Steel ingots, fresh from the mill, are slowly heated in gas furnaces to temperatures around 2,200 degrees Fahrenheit. This isn't a rushed process. Depending on size, heating can take anywhere from 8 to 24 hours. Once the steel reaches that perfect forging temperature, glowing that unmistakable orange-yellow color that means it's ready to flow, the real dance begins. Massive manipulators, essentially industrial robotic arms that can rotate and position these multi-ton pieces with remarkable delicacy, move the workpiece under the forging press. Both hydraulic presses and mechanical hammers are used, depending on what the job demands. A hydraulic press applies slow, steady pressure, ideal for ensuring the force penetrates deep into the heart of the piece, eliminating any internal voids or inconsistencies. The mechanical hammer, on the other hand, delivers rapid blows that shape the surface and create specific forms. The forge master, a craftsman whose skills require decades to develop, orchestrates this symphony of heat and pressure. Between each strike or pressing, the piece rotates, gets repositioned, and sometimes reheated. This is called open die forging, because unlike closed die forging, where metal is compressed into a specific shape, here the masters are literally sculpting the metal through repeated strikes and pressure applications, gradually drawing it into the desired form. Each strike refines the grain structure, making the steel stronger and more reliable than anything achievable through casting or machining alone. Now let's move on to modern precision forging, which has adapted traditional forging techniques to produce complex automotive and industrial components at volumes that would have been unthinkable in the old days of small batch artisan forging. The process starts with steel bars, often supplied in coils, which are cut to precise lengths and then fed into induction heating systems. Induction heating is one of those technologies that seems almost magical when you first encounter it. No flame, no combustion, but within seconds a steel billet placed inside an induction coil glows cherry red, then orange, then that brilliant yellow-white that tells you it's ready for forging. The secret lies in electromagnetic induction, discovered by Michael Faraday way back in 1831, but only practically applied to industrial heating in the early 20th century. Alternating current flowing through the coil creates a rapidly changing magnetic field, which induces electrical currents in the steel itself, and these currents generate heat through resistance. After heating to the optimal forging temperature, typically between 2,000 and 2,300 degrees Fahrenheit, depending on the steel grade, the billet moves to the forging press. Sophisticated closed die forging is used, where the hot steel is placed between two die halves that contain the negative impression of the desired part. When these dies come together with thousands of tons of force, the steel has nowhere to go but to fill every contour of that cavity. What's remarkable is the speed and precision of modern forging presses. We're talking about machines that can complete a forging cycle in just a few seconds, yet achieve dimensional tolerances that would have required extensive machining in the past. There's something deeply satisfying about watching skilled craftsmen build storage tanks. The process begins with selecting and cutting steel plates. Modern fabrication shops use CNC cutting tables, plasma or laser, that can slice through thick steel plate with remarkable precision, following computerized patterns that ensure minimal waste. But before any cutting happens, there's meticulous layout work, figuring out how to arrange different components to get the most from each plate. It's a puzzle that combines geometry, efficiency, and materials science. After cutting, the components move to rolling and forming operations. Tank shells typically need to be cylindrical, which means flat plates must be rolled into curves using 3-roll bending machines like the ones we saw earlier. The edges of these rolled sections are then prepped for welding, usually with beveled cuts that let the weld penetrate completely through the material's thickness. The welding process, that's where the craftsmanship really shines. Tank fabrication typically uses submerged arc welding for the main seams, a process where the arc works under a blanket of granular flux, protecting the weld from atmospheric contamination while allowing deep penetration and high deposition rates. End caps, whether they're flat, dished, or hemispherical, get fitted and welded on, and then comes the real test, hydrostatic testing. The completed tank gets filled with water and pressurized above its operating pressure to verify integrity. Any leaks or weaknesses show up here, not during service, which could be catastrophic. Let's wrap up with the 3-roll plate bending operation, because there's something fundamentally impressive about watching these machines transform flat steel into curves with such apparent ease. The 3-roll bending machine is one of those elegant engineering solutions that's remained fundamentally unchanged for over a century because, simply put, it works beautifully. The machine consists of 3 essential rollers arranged in a pyramidal or triangular configuration. The 2 bottom rollers are drive rollers that grip and feed the plate through the machine, while the top roller, which can be adjusted up or down hydraulically, provides the bending force. The beauty of this setup is in its simplicity and efficiency. By varying the top roller pressure and making multiple passes, you can achieve a wide range of diameters and even create nearly perfect circles. The process itself is mesmerizing to watch. The plate enters between the rollers, and as they rotate, you can literally see the flat material take on curvature. For thicker plates or tighter radii, multiple passes are necessary, with each pass increasing the curvature incrementally. Modern machines can handle impressive specs, plates several inches thick and many feet wide, bending them into cylinders or cones with remarkable precision. The rollers themselves are precision-ground, hardened steel, designed to maintain their shape under enormous loads. This technology represents a perfect marriage of time-tested mechanical principles with modern control systems, creating tools that are simultaneously powerful and precise, capable of forming the steel that builds our world. Imagine if construction could be not just strong, but ultra-lightweight, durable, and environmentally friendly all at once. That's exactly the revolution fiberglass rebar brought to the table. A modern material that's gradually replacing classic steel rebar in countries around the world. China produces it especially aggressively, a giant controlling a massive share of the global market. But what is this secret material that's changing the game? Fiberglass rebar is 4 to 5 times lighter than steel, never rusts, withstands harsh environments, and lasts over 50 years. China produces more than 500 million pounds of this stuff annually and controls 60% of global exports. But why are Western countries afraid of this dependency? What role does fiberglass rebar play in Beijing's geopolitical strategy? And how do they make this material that starts as molten glass at 2,700 degrees? Stick around till the end. You'll learn about projects where this material has already changed the future of construction. Fiberglass rebar. These are reinforcing rods made from a composite material based on fiberglass, impregnated with specialized resins. Unlike traditional steel rebar, it's 4 to 5 times lighter, doesn't rust, resists corrosion, and withstands harsh conditions, like acid rain, salt spray, and high humidity. To put it in perspective, standard steel rebar weighs nearly half a kilogram per meter of length, while fiberglass rebar weighs around 120 grams for the same size. This means it's easier to work with, requires lower transportation and installation costs, and as a result, construction becomes faster and cheaper. China holds the leading role in global fiberglass rebar production. Factories located primarily in the eastern and central regions of the country are equipped with modern pultrusion, molding, and fiberglass polymerization lines. Chinese manufacturers produce over 500 million pounds of these materials every year, with exports making up about 60% of total global volume. China's huge advantage isn't just scale, it's price. Thanks to low-cost electricity and resources, Chinese products often undercut competitors from the US and Europe. But this triggers intense geopolitical debates. Zoom out, and fiberglass rebar has become a real hot card in global trade. Western countries increasingly face a dilemma: support domestic production with significantly higher costs but less export influence from China, or actively import cheap Chinese rebar, becoming dependent on Chinese materials. Here's the secret angle. China uses fiberglass rebar not only in its own massive infrastructure projects. Through strategic investments in Asia, Africa, and Latin America, Beijing is aggressively pushing this material via its global construction corporations operating under the Belt and Road Initiative. This allows China to not only expand its presence in the global construction market, but also strengthen economic influence in these regions through control over building resources. The trend toward fiberglass rebar isn't just about cost savings or new materials, it's about ecology and safety. Fiberglass rebar is rapidly gaining popularity in the US, where more and more bridges, roads, and homes are being built using lightweight composites. Unlike metal, this material doesn't corrode, making infrastructure more reliable and longer lasting. According to reports from the American Association of Construction Materials, average construction costs using fiberglass rebar drop by 20%, while structural lifespan doubles. For young engineers, architects, and entrepreneurs, this means more opportunities for innovation, less environmental impact, and industry growth. Picture this: you're building a bridge or a high-rise. Instead of heavy steel rebar, you're using thin fiberglass rods. They can be longer, lighter, and easier to install. Plus, you don't have to worry about them rusting years later and causing the concrete to deteriorate. China's already deploying its fiberglass rebar on massive construction projects. In major districts of Beijing, Shanghai, and Guangzhou, new highways and bridge spans are going up with these materials. Around the world, Chinese companies are supplying this rebar to projects in the US, Europe, and the Middle East, strengthening their technological and economic footprint. It all starts with glass, the raw material for making glass fibers. Glass is produced from a mixture of sand, limestone, and soda. These ingredients head into massive industrial furnaces, cranking up the heat to 2,700 degrees Fahrenheit. Here, the mixture melts down into liquid glass. Then, molten glass flows through specialized openings, spinnerets, forming thousands of thin filaments. These fibers get cooled and gathered into bundles. This creates primary fiberglass, thin, flexible, and incredibly strong strands. To give the fibers their necessary properties, they're treated with a special chemical solution, an organic binder, or silane. This coating ensures a rock-solid bond between the fiberglass and the polymer matrix that comes next. The treated filaments get collected into bundles that can contain thousands of individual fibers. These fibers are oriented parallel to each other for maximum strength. Next comes the main event, forming the composite matrix. The raw material? Polymer resins, typically epoxy, polyester, or vinyl ester. They deliver high-strength performance and provide resistance to moisture and chemical exposure. Bundles of fiberglass are dipped or soaked in a polymer resin solution. The fibers get evenly coated with polymer, and excess resin is removed to prevent clumps and irregularities. The prepared wet bundles feed into a specialized forming line, an extruder. Here, the molten composite is pushed through forming dies, shaping it into rods or bars of the required diameter. Then comes a critical step, pulling and polymerization. The finished reinforcing rods immediately move to cooling and hardening in special thermal chambers. Here, the polymer matrix solidifies, firmly binding the fibers into a unified structure. Dimensional and shape control is crucial, so production lines are equipped with automatic calibration systems to ensure the specified diameter and round shape of the rebar. Standard diameter for fiberglass rebar ranges from 1/4 inch to about 1.5 inches, depending on the application. To ensure better adhesion to concrete, the rebar isn't left completely smooth. During manufacturing, it passes through forming rollers that create ribs, notches, or texture on the surface. This makes fiberglass rebar more effective for reinforcing concrete structures. It grips firmly in the concrete mass and won't slip under load. At the end of the production line, workers or automated systems cut the reinforcing bars to standard lengths, typically 20 feet or 40 feet. The bars are bundled into packages that are easy to transport and store. Each batch goes through testing for strength, flexibility, and corrosion resistance. Manufacturers often guarantee the rebar will last over 50 years, several times longer than traditional steel reinforcement. Fiberglass rebar is gaining more and more importance in modern construction thanks to its lightweight, strength, and corrosion resistance. You're about to see some of the most interesting projects actively using this innovative material. Delhi Metro, Phase 4 in India. A massive metro project where this rebar is being used extensively to reinforce tunnels and structures. This helps extend the lifespan of the infrastructure and reduce the weight of construction materials. Jizan Flood Mitigation Channel in Saudi Arabia, the world's largest project using fiberglass rebar, designed to reinforce long channels for flood control. We're talking 240 tons of fiberglass rebar that need to provide high resistance to aggressive environments. Muskrat Falls Hydroelectric Project in Canada. Rebar manufacturers are supplying material for reinforcement that guarantees the hydroelectric plant's long service life, especially under conditions of water contact and high humidity. The Sunshine Skyway Rest Area Seawall in Florida, USA. A marine structure where fiberglass rebar is the ideal material due to its corrosion resistance in saltwater. Here it reduces the need for repairs and extends the service life of the walls. The Alligator River Bridge in North Carolina, USA. A bridge reinforced with composite rebar to increase durability and minimize the weight of metal structures. Toronto's TTC North Subway Extension Tunnels in Canada, a project where fiberglass rebar helps increase structural flexibility and reduce damage risks during seismic events. And just like that, traveling from molten glass at 2,700 degrees through the formation of ultrafine fibers, polymer resin impregnation, and ribbed surface creation, a material is born that serves for over 50 years without a single trace of corrosion. This is a story about how humanity learned to create rebar lighter than air and stronger than steel, a material that's changing the geopolitics of construction and making bridges eternal.
Every year, millions of components, tons of alloys, and hours of high-precision calculations come together in one deadly symphony. This missile isn't simply metal. It's a moving brain, an engine, and coded death that flies over 1,000 miles whilst hiding from radars. How is a secret capable of changing the course of battle born from hundreds of metal sections? Stay until the end. I'll reveal one production secret that few people know. Want to know what's hidden inside? Imagine lasers, press forming, robots welding components in clean rooms with tolerances of 1/100th of a millimeter. All of this for a single flight. Designing the Tomahawk missile is a symphony of formulae and calculations. Engineers don't simply draw a body. They solve equations that must allow it to cut through air with centimeter precision. Every surface and curve is calculated in computer-aided design systems and undergoes aerodynamic modeling. The goal is to create a body that will fly over 1,000 miles, remaining almost invisible and stable at an altitude of 100 feet or 160 feet above ground. In digital simulations, they test wind force, resistance at speeds of 550 miles per hour, and the effects of rain. One mistake, and instead of a precise strike, the missile will hit a barn on the outskirts. Body components, electronics, payload, all of this fits into nearly 20 feet of length and 20 inches in diameter. It's genuine artistry, packaging death with such elegance. Only after dozens of virtual tests does the missile move to the production phase. After the calculation stage, drawings are transferred to the real world, to factories with high-precision equipment. Here, not a single crack nor an extra micron can be permitted. The missile body, over 18 feet long, is assembled from sections manufactured from high-quality aluminum alloys, sometimes with titanium added. This is an aerodynamically refined cylinder that must withstand overloads, vibration, and temperature fluctuations. Blanks are cut with laser or water jet installations with tolerances up to 1/100th of a millimeter. Then press forming. Large hydraulic machines bend metal like fabric. Welding is conducted in an inert atmosphere, often by robotic arms, to avoid even the smallest oxygen inclusions. Technologists check welds hourly with ultrasound and apply special anti-corrosion coatings. Even the inscription Tomahawk isn't applied as decoration, but as a marker of version and the missile's history. For the cruise missile, a compact Williams F-107 turbofan engine is used, similar to a small aircraft engine but adapted for high maneuverability. Turbine blades are manufactured from nickel alloys in a form resembling sculpture more than a technical component. They're cast using precision casting methods, then polished to mirror finish to give air minimal resistance. The compressor and combustion chamber are a complex mosaic of dozens of elements. Each component is checked for seal integrity because any micro leak and the missile simply won't launch. The nozzle is manufactured from heat-resistant alloy capable of withstanding flame temperature without deformation. Engine assembly occurs in clean zones similar to laboratories. Workers in sterile suits, stable temperature and humidity. After assembly, each engine undergoes individual ignition testing in a test chamber. The engine simulates genuine flight, but not in the sky, on a concrete table with sensors. Tests last for hours. They check stability of revolutions, temperature, fuel consumption, and even noise, because volume could betray the missile's position. And only when the engine has sung its song is it integrated into the Tomahawk's body, as though breathing life into it. When the body is ready and the engine installed, the missile still isn't ready to fly. It knows nothing yet. It must be taught. Inside is a genuine brain, a node of microprocessors, sensors, antenna, and memory blocks. But the moment it receives its first power signal, a machine consciousness awakens within it. Its navigation is an entire ensemble of systems. Inertial sensors maintain course even if the signal disappears. GPS correction helps prevent deviation from the route. But most important is its ability to see. Special cameras analyze terrain, comparing every hill or bridge with the map stored in memory. If there's forest beneath it when there should be field, it knows something's wrong. It makes decisions. The control system works like nervous tissue, flexible and infallible. Small stabilizers and control surfaces respond to every tilt and altitude change. And finally, the most important thing, that which transforms the missile from an engineering creation into a weapon, its warhead. It looks simple, a cylinder hidden in the body. But inside is explosive capable of penetrating concrete and destroying equipment. It's manufactured separately under conditions of absolute sterility. Not a single spark. This is work where mistakes aren't corrected, they're not permitted. Before final assembly, each component undergoes inspection. X-ray, vibration tests, electronic diagnostics, and then assembly. Quietly, step by step, as though someone's assembling not a weapon but an antique clock that must strike just once. And when everything's connected, the missile silently settles into its container. It doesn't glow, doesn't flash, it simply waits. Its flight lies ahead, but it's already ready.
Every second, a new Michelin tire is produced somewhere in the world. But did you know that a single tire contains over 200 different ingredients? That each tire undergoes testing equivalent to 600 million miles of driving per year? That's 40,000 trips around the planet. Picture this. Hidden inside every tire are 1,400 steel cords, each capable of holding 33 pounds. That means just 8 cords in your 4 tires could support 31,700 pounds, the weight of 10 cars. And then there's the secret C3M technology that Michelin hides even from factory visitors. How does liquid rubber at 230 degrees Fahrenheit transform into a tire that can withstand 390 degrees during vulcanization? What chemical miracles happen when sulfur mixes with rubber? And why does a 10 to 15-minute mistake in vulcanization turn months of work into scrap? Stick around till the end. You'll discover how they create tires that millions trust with their lives. It all starts with research. Michelin engineers study how people drive, what roads they take, what conditions they put their tires through. This isn't just rubber on wheels. It's a highly complex engineered product, packed with as much technology as a modern smartphone. Over 130 years ago, brothers André and Edouard Michelin founded the company in the French city of Clermont-Ferrand. And today, the company's headquarters is still right there. Michelin now runs factories all over the world, from the US to China, from Europe to Brazil. But the manufacturing process is identical everywhere. A tire made in America is identical in quality to one made in China or France. This is achieved through the strictest standardization of every single process. Each plant is a specialist. For instance, the plant in Valladolid, Spain has been making tires for agricultural equipment, combines and tractors since 1973. And the plant in Lasarte in northern Spain specializes in premium motorcycle tires. This isn't random. Each factory has honed its craft for decades. But the most fascinating part begins at the materials development stage. A single tire contains over 200 ingredients. This isn't just rubber, it's a carefully engineered blend of natural rubber, synthetic rubber, carbon black, silica, metal and textile cords, dozens of chemical agents. Every ingredient plays its role. Natural rubber forms the tread base. It's extracted from the sap of the hevea tree, the rubber tree. This white latex is collected from plantations in Southeast Asia, Africa, and Latin America. Synthetic rubber is produced chemically from petroleum products. It's essential for achieving specific characteristics, like resistance to high temperatures or low rolling resistance. Michelin is actively researching the possibility of producing synthetic rubber from more sustainable sources, moving away from petroleum. Carbon black and silica are reinforcing agents. They make the tire tough and wear resistant. Silica is especially important. It reduces rolling resistance, which means better fuel economy and lower carbon dioxide emissions. Metal and textile cords are the tire's skeleton. They give it shape and rigidity. Get this, a single standard tire has around 1,400 textile cords, each one capable of handling 33 pounds of load. And the steel cords in the tire beads? Even stronger. Each one can take nearly 4,000 pounds. 8 of those cords across your 4 tires create a strength reserve of over 31,000 pounds. That's more than the weight of 10 cars. Chemical agents give unique properties. Low rolling resistance, ultra-high grip on wet roads, resistance to wear. Every rubber compound recipe is the result of years of research. The percentage of each ingredient varies depending on the tire type. Now comes the really interesting part, mixing the components. This happens in massive mixers under strictly controlled temperatures. First, they mix the rubber with carbon black, silica, oils, and other ingredients, but without sulfur and vulcanization accelerators. This is critical. Temperatures at this stage can reach 300 degrees Fahrenheit, and if you add sulfur now, the mixture starts to vulcanize prematurely. That's called scorch. So sulfur and accelerators only get added at the final mixing stage at around 230 degrees. The mixture looks like thick black goo. This is your future rubber. After mixing, it's rolled into sheets or formed into strips of specific thickness. These semi-finished materials head to the next stage, assembly. Meanwhile, they prepare steel cords for the belt and bead of the tire. Steel wire gets pulled through special dies, coated with a thin layer of latex for better adhesion to the rubber and woven into strong cables. Textile cords are made from polyester, nylon, or aramid fibers, the same stuff used in bulletproof vests. These cords get coated with rubber too. Now the assembly of the green tire begins. That's what they call the unvulcanized blank. This is an incredibly complex process where each layer is placed with micron-level precision. First, they wrap an inner sealing layer around the drum. This is synthetic rubber, the modern equivalent of an inner tube. This layer makes the tire airtight. On top of that, they lay down the carcass layer, thin textile cords embedded in rubber. This layer determines the tire's strength. Then they form the tire beads, the spots where the rubber grips the metal wheel rim. Steel rings made from thick wire get embedded here. All the engine's power and braking force transfers through the bead from the rim to the contact patch on the road. Next layer, the belt. This is several layers of steel cord laid at an angle. The belt reinforces the tire, prevents it from bulging at high speeds, and protects against punctures. And finally, the tread. This is a rubber strip with the future pattern that gets laid on the very top. A protective rubber layer is applied to the tire's sidewalls. At this stage, Michelin uses its secret C3M technology. It's a revolutionary process whose details the company keeps under lock and key. Even those who've toured factories with this technology haven't seen it in action, but we know C3M allows different rubber compounds to be placed with micron-level precision in different tread zones. For example, in Michelin Pilot sport tires, the tread shoulders use a compound with carbon black for maximum grip in corners. The center of the tread, a compound with 100% silica content for wet road traction. And along the sides of the central rib, a softer compound for snow and cold weather performance. All in one tire. Since 1997, Michelin has produced over 15 million tires using C3M technology. Today, more than 20% of the Michelin Pilot lineup is made with this method. When the green tire is assembled, it looks like a smooth rubber blank with no tread pattern. And now comes the most critical moment, vulcanization. This is the process that transforms soft rubber into a strong, elastic material. Charles Goodyear discovered it in 1839 by accident, dropping a mixture of rubber and sulfur onto a hot skillet. To his surprise, the rubber didn't melt, but hardened, becoming strong and elastic. Today, vulcanization is a precise science. The green tire is placed in a massive press mold, and a rubber capsule, a bladder, is inserted inside. The mold closes and the magic begins. Superheated steam under pressure is fed into the capsule, or nitrogen is used. The temperature climbs to 290 to 320 degrees Fahrenheit, sometimes up to 400 degrees. Pressure reaches 3 to 450 pounds per square inch. The capsule inflates from within, pressing the tire against the mold walls. The mold is also heated from the outside with steam. And in these conditions, high heat, high pressure, a chemical miracle happens. Sulfur starts creating cross-links between the long rubber molecules. Linear molecules transform into a three-dimensional network. The rubber becomes hard, strong, elastic, resistant to heat and cold. At the same time, the tread pattern and sidewall lettering get stamped onto the tire's surface. This process takes 10 to 15 minutes for a passenger tire, up to 20 or 30 minutes for a truck tire. Timing is critical. Undercure it and the tire will be soft and wear out fast. Overcure it and the rubber becomes stiff and brittle. Temperature is critical too. The entire process is computer controlled down to the degree. Modern systems even measure each green tire's temperature before curing with infrared sensors and adjust the time based on starting temperature. After curing, the mold opens, steam releases from the bladder, and out comes a finished tire. Hot with that distinctive rubber smell with crisp tread pattern. But that's not the end. Every tire goes through brutal quality control. First up, visual inspection, any surface defects, bumps, or bubbles. Straight to the reject pile. Next, size and shape verification using laser scanners that measure hundreds of points across the surface. Balance testing follows. An imbalance of more than a few grams is unacceptable. X-ray inspection comes next. They peer into the internal structure, hunting for core defects, voids, or foreign objects. And the big one, road testing. Michelin runs over 600 million miles of tests every year. That's equivalent to 25,000 trips around the Earth. Tires get hammered on wet and dry pavement, on snow and ice, in scorching heat and freezing cold, at high speeds and under extreme conditions. And so, after traveling from a rubber tree in the jungle through the blending of 200 ingredients, Through the precision assembly of 1,400 cords through the hell of vulcanization at 400 degrees Fahrenheit, and through 600 million miles of testing, a Michelin tire is born. The only point of contact your car has with the road, the thing your life depends on.
Every year, humanity forges colossal anchor chains capable of withstanding a force of over 1,500 tons, enough to hold back an entire freight train loaded with coal. A single link can weigh more than 500 kilograms and be as thick as a tree trunk. But how is such immense strength born from a simple bar of red-hot steel? What brutal trials must every meter of this steel serpent endure before it is trusted to the depths of the ocean? Stay with us until the end to witness a process of fire, sparks, and true engineering alchemy. It all begins not in the forge, but at a steel mill, where a special alloyed steel is created from ore and scrap. This is no ordinary metal. To produce chains that can handle loads of thousands of tons, you need the highest grade of steel, one capable of resisting not only tension, but also the embrittlement that comes from the extreme cold of Arctic waters. After smelting and chemical analysis, the steel is cast into massive cylindrical billets. These billets, while still hot, are passed through rolling mills that, with incredible force, squeeze and stretch the metal, forming it into long, round steel bars with a diameter that can exceed 200 millimeters. The production hall is a kingdom of fire and metal. The air here is thick with the hum of machinery and the sharp, distinct smell of incandescent steel. It is here that the magic happens, transforming a straight bar into a curved, closed loop. First, the steel bar enters the infernal mouth of an induction furnace. In a matter of minutes, a powerful electromagnetic field heats it to 1,200 degrees Celsius, making the metal plastic and malleable. The glowing bar is then immediately fed to a bending press. Hydraulic arms effortlessly bend it into its characteristic U-shape. Now comes the critical moment. While still hot, the U-shaped piece is threaded through the last, already completed link of the growing chain. This is how the links are interconnected. The two ends of the U-shaped piece are then brought together and clamped tightly in the giant copper jaws of a welding machine. The process of flash butt welding begins. An enormous electrical current is passed through the joint. The metal at the point of contact instantly melts, accompanied by a blinding flash and a fountain of sparks. At that exact moment, a hydraulic press with hundreds of tons of force squeezes the molten pans together, fusing them at a molecular level into a single seamless piece. The excess metal, known as flash, is immediately sheared off by special cutters. While the link is still hot from welding, a special stud is fitted into its center. This crosspiece not only gives the link additional rigidity, but, most importantly, prevents it from deforming and tangling during use. After the stud is set, the entire chain, or a section of it, undergoes heat treatment. It is reheated to a precise temperature and then rapidly cooled or quenched in a huge pool of water. This process makes the steel extremely hard, but also brittle. To remove this brittleness, the chain is heated again to a lower temperature and left to cool slowly in the air. This final step is called tempering. Not a single meter of a giant chain leaves the factory without undergoing a series of the most stringent tests. This is the guarantee that it will not fail at a critical moment. First, the entire chain is subjected to a proof load test. It is secured in a special testing machine, a colossal hydraulic bench dozens of meters long. The machine begins to stretch the chain with a force significantly greater than its nominal working load. Inspectors meticulously examine every link for any sign of deformation. But the most dramatic trial is the break test. A test sample of several links is cut from the finished batch. It is placed in the same machine and pulled until it shatters. The deafening crack of rupturing metal is not a sign of failure, but the ultimate confirmation of the entire batch's quality. After the mechanical tests, every single link is inspected with ultrasound to detect any hidden internal flaws. Only after successfully passing all these stages does the chain receive its quality certification. Loaded for transport, it looks like a sleeping steel leviathan ready to begin its silent service in the depths of the ocean. For the highest grade chains, this proof load can exceed 1,000 tons. This means the chain is stretched with a force equivalent to the weight of 3 Boeing 747s. The minimum braking load for such products often exceeds 1,500 tons. Behind every giant link is a world of impressive numbers. A single link of a top-grade anchor chain can be forged from a steel bar over 200 millimeters in diameter. The weight of such a link easily exceeds 500 kilograms, more than a grand piano. However, chains are not measured by the link, but in sections. A standard marine section, or shot, is 27.5 meters long. The complete anchor chain for a supertanker can consist of 12 to 15 of these shots, reaching a total length of over 400 meters. Its total weight can easily exceed 250 tons, comparable to the weight of 2 adult blue whales.
Deep beneath the ground in Ohio sits a machine that holds up America's skies. The Mesta 50 press, a 36,000-ton monster that plunges 10 stories underground. It squeezes metal with 50,000 tons of force. That's the weight of 10 Eiffel Towers at once. Without this machine, the United States would have no F-35 fighter jet, no Boeing 787, and when a crack appeared on the press in 2009, the entire American aviation industry held its breath. Today we'll see how white-hot titanium transforms into fighter jet wings under the blow of a steel fist from the Cold War era, and why this machine, and no other, remains irreplaceable to American defense. If you stood outside the Alcoa plant in Cleveland, Ohio, you wouldn't see anything special. Just an ordinary industrial building, gray brick walls, pipes, trucks. But head underground and you enter a world where real power is born. The Mesta 50 doesn't sit on the ground, it's embedded into it. 100 feet down, 10 stories of concrete and steel. Why so deep? Because when 50,000 tons of force slams into metal, the earth shakes for half a mile in every direction. Without this colossal foundation, the press would punch through the ground like a knife through butter. This machine was built in 1955 at the height of the Cold War, and it's still running, almost 70 years. In that time, generations of aircraft have come and gone, materials have evolved, control systems have advanced, but the press remains, because nobody has built anything more powerful. If you're into stories like this about machines that change the world, subscribe to the channel right now and hit the bell so you don't miss the next one. America and the Soviet Union weren't just racing in space, they were racing for the sky. Whoever builds the best aircraft dominates the air.
and the best aircraft need parts that can't be made with conventional methods. Picture a turbine blade from an F-35 fighter jet engine. This component is only about a foot long, but it spins at 10,000 revolutions per minute at temperatures exceeding 2,500 degrees Fahrenheit. No welded seam could handle that. It would fail in seconds. The blade has to be solid, forged from a single piece of titanium or nickel superalloy. That's exactly what the 50,000-ton press is for. It doesn't cut or weld, it crushes. Takes a red-hot chunk of titanium and transforms it into the precise shape of a wing or blade in a single strike. Press forging doesn't just shape metal, it changes the metal's very structure. The crystalline grain of titanium gets refined and aligned along the part's contours, making it several times stronger than if you cast or machined the same part from stock. The process starts with prep. A titanium ingot heats up in a specialized furnace to 1760 degrees Fahrenheit. At that temperature, titanium becomes soft as clay, but keeps its incredible strength. The metal glows bright red, almost white. You can't look at it without special glasses. When the temperature hits the sweet spot, a robotic arm pulls out the glowing ingot and moves it to the press in seconds. Time is everything. If the titanium cools even 90 degrees, it becomes too hard and the press can't deform it. The operator literally has no room for delay. Every move from furnace to press is drilled to perfection. Decades of practice, hundreds of thousands of parts. They lay the ingot into the lower die, a massive steel form that mirrors the shape of the finished part. The dies themselves are made from special tool steel and cost hundreds of thousands of euros each. From above, the upper die drops, 330,000 pounds. And then the strike hits. 50,000 tons of force slams down onto white-hot titanium. To put that in perspective, imagine stacking 150 passenger jets on your desk, all at once. Hydraulic cylinders 8 feet in diameter generate pressure of 50,000 psi. That's 3,500 times atmospheric pressure. Under this monstrous force, titanium behaves strangely. It doesn't break. It doesn't crack. It flows. Metal atoms shift, sliding past one another, filling every microscopic corner of the die. In 3 seconds, a shapeless ingot transforms into a perfect replica of a wing spar or turbine blade. The entire factory shudders from the impact. Workers feel the vibration hundreds of feet away, like a minor earthquake. Operators at the press wear specialized ear protection. The sound of the strike reaches 130 decibels, louder than a jet taking off. The strike itself lasts no more than 3 seconds. But in those 3 seconds, something happens that would take hours of conventional machining, and the result is stronger. But the most amazing thing? The precision. Despite the savage force, the press controls the shape to within half a millimeter. Laser sensors track every movement of the die. Hydraulics adjust pressure thousands of times per second. If something goes wrong, a part worth 300,000 euros turns into scrap metal. Mesta 50 produces parts for all major American aircraft: F-35 and F-22 fighters, Boeing 787, Apache helicopter engines. They all carry parts born under the blow of this press. Every month, more than 2,000 tons of titanium and nickel superalloys pass through it. The plant employs hundreds of specialists, metallurgists, press operators, quality control engineers. Each finished part undergoes rigorous inspection: ultrasonic scanning, X-ray, geometry measurement, accurate to hundredths of a millimeter. Documentation for each part is stored for decades. If a plane crashes, investigators can reconstruct the entire manufacturing history of every component. Only after passing all inspections does a part receive clearance for installation on an aircraft. And then disaster struck. In 2009, during a routine press operation, engineers heard an unusual sound: metal cracking. The press was immediately shut down. Inspection revealed something terrifying. A crack nearly 4 feet long had appeared in the main support beam. For the U.S. aviation industry, this was a real shock. Mesta 50, the only press of this power in the country, without it, F-35 production stopped. Boeing couldn't manufacture parts for the Dreamliner, military contracts were frozen. Every day of downtime cost millions of dollars. The problem was that a 2,000-ton beam can't just be removed and replaced. It's installed in the structure at a depth of 100 feet, surrounded by dozens of other systems. And building a new press of equal power, that's years of work and billions of dollars. The country had neither. Engineers would have to repair it right there on site, 100 feet down, in cramped conditions with no way to extract the structure. A desperate repair effort began. A specialized team of welders worked around the clock for 4 months. They used cutting-edge technology, electroslag welding in an inert atmosphere. The crack was welded layer by layer, each about 1/8 of an inch thick. After each layer, the metal underwent heat treatment to relieve internal stresses. In total, 760 weld layers were laid down. Meanwhile, a backup beam was being fabricated, just in case the repair failed. It was made at another facility and delivered using America's largest crane, capable of lifting 4,000 tons. In December 2009, Site 50 was operational again. 200 engineers watched the first strike after repair. Everyone held their breath. The press struck. The facility shuddered. The titanium deformed precisely to the die shape, and the crack didn't reappear. 4 months of work, 760 weld layers, thousands of hours of heat treatment. It all held. The American sky was saved. Today, the 50 is still running. It's almost 70 years old now, an incredible age for industrial equipment. Modern presses are more efficient and automated, but none reach this kind of force. 50,000 tons remains an unbeaten record for the entire country. The 50 is more than just a machine. It's a symbol of industrial might and engineering determination. Every plane you see in the sky, every military fighter, every wide-body airliner, its structure contains parts born right here, beneath the Ohio ground, under the strike of this steel fist. Over the decades, an entire ecosystem has formed around the press. Thousands of engineers, metallurgists, operators who pass down from generation to generation the knowledge of how to work with this monster. It's proof that sometimes the best solutions aren't the newest ones, but those proven by decades of reliable work under incredible pressure. Literally.
Every year, the world produces over 1,200,000,000 wool products. Sweaters, scarves, coats, all made from a material that's remained essential in the textile industry for thousands of years. But what makes ordinary sheep's wool so special? Behind every warm sweater lies a process where nature meets cutting-edge technology. From shearing sheep to finished fabric, wool undergoes an incredible transformation. How does a clump of dirty fleece become an $80 billion a year industry? Stick around to the end, and you'll discover how an industry turns nature's gift into the foundation of global fashion. The wool industry is a massive machine that processes over 4 billion pounds of wool every year. That's nearly 2 million tons.
3 countries control more than 60% of global production: Australia, China, and New Zealand. Australian farms specialize in fine, high-quality merino wool, which commands the highest prices. China, meanwhile, is the biggest processor and consumer. Thousands of textile factories there transform raw fiber into finished products. The economic value of the entire wool industry tops $80 billion annually, including exports of raw fiber and finished goods. But wool's biggest advantage? It's a completely renewable natural material. Sheep grow new fleece every year, making this one of the most eco-friendly industries in the fashion world. The journey of wool begins on the endless pastures of New Zealand and Australia, where farmers manage their flocks by the strictest standards. Each farm carefully selects sheep breeds based on production goals. Merinos produce ultra-fine fiber for premium clothing, while Romney or Corriedale breeds generate longer, stronger fibers for industrial use. Every sheep gets a personal tag, recording age, health, and wool quality. Flocks graze on rotational plots, preventing soil depletion and preserving the land's fertility. Their diet is supplemented with hay, grain, and minerals to grow dense, uniform, and lustrous wool. Pens stay dry and well ventilated to prevent parasites and skin diseases. Each season, farmers vaccinate, deworm, and inspect every animal because a sheep's health directly determines fiber quality. Before breeding season, sheep undergo a process known as flushing. Their diet gets enriched with special supplements for several weeks to boost fertility and produce stronger lambs with finer fleece. During lambing, mothers are closely monitored so newborns get milk right away. A few weeks later, the young ones are tagged, weighed, and moved to lush pastures for weaning. When the warm months arrive, flocks are washed, treated for ticks, and left to air dry naturally before shearing. Each sheep is handled gently to avoid stress and yield a single clean fleece without tears. After shearing, they're inspected again. Minor cuts are treated and they're given time to rest before heading back to the fields. Every stage, from nutrition to shearing, follows strict animal welfare standards because only healthy sheep can produce the clean, durable wool of highest value. After months of care, when the sheep's fleece has fully grown back and the weather starts warming up, shearing season arrives. The timing's perfect. Sheep stay comfortable after losing their warm coat, and they've got plenty of time to grow a new one before winter hits. Before the process begins, the flock's kept in clean, dry pens and given lighter feed portions to keep the animals calm. Shearers are highly skilled professionals trained to work safely with each animal. They use precision electric clippers with fine blades, moving in a specific sequence, starting with the belly and legs, then working their way to the sides, shoulders, and back. The goal? Remove the entire fleece in one smooth, continuous motion without damaging the fibers. An experienced shearer can process 200 to 250 sheep in a single day, spending just 1 to 2 minutes on each animal. Short, dirty wool from the belly and legs gets separated for lower quality products, while the long, fine white fleece from the back and sides is reserved for premium fabric production. After shearing, sheep are checked for cuts or scrapes, treated with antiseptic, and sent to rest in wind-protected pens. Each large fleece, the result of an entire year of care and growth, now becomes the very first raw material in wool's industrial journey. From the shearing sheds, fresh fleeces head straight to the sorting zone, where human expertise remains irreplaceable, even amid modern automation. Each fleece gets laid out on wide tables and examined for color, fiber length, and fineness. Any sections tangled with grass, dirt, or too short for spinning get removed. Experienced sorters divide the fleece by zones. Wool from the belly and legs is reserved for industrial use, while the long, clean fibers from the back and sides are set aside for fine fabrics. This meticulous stage not only maximizes the value of each fleece, but also ensures consistency in production batches before the wool is compressed into bales and shipped to the washing plant. Once the sorting process is complete, clean fleeces are collected and moved to the pressing area. Here, powerful hydraulic presses compress each batch into dense rectangular bales, weighing between 300 and 400 pounds, tightly wrapped in burlap or heavy plastic for moisture protection. Each bale is marked with detailed information, including the farm of origin, sheep breed, and wool grade, ensuring full traceability throughout the supply chain. At the raw material processing plant, the wool bales are unpacked and evenly distributed onto conveyor belts for cleaning. The first stage happens inside an opener, a machine equipped with several rows of high-speed rotating metal teeth designed to separate tangled fibers and remove trapped contaminants like dust, grass, and dirt. This loosens the wool and prepares it to better absorb water in the next washing stage. The washing system consists of 6 continuous tanks of hot water, operating at temperatures between 168 and 180 degrees Fahrenheit. The first 3 contain diluted soapy solution to dissolve lanolin, the natural oil secreted by sheep that protects their fleece from moisture. The remaining 3 are filled with clean water for thorough rinsing. Water is filtered and circulated in counterflow through automatic pumps, conserving energy and maintaining consistent quality across all batches. Between each tank, soft press rollers gently squeeze out dirty water without damaging the fibers. Temperature and flow sensors automatically adjust washing parameters to keep the system at optimal safe levels. The extracted lanolin is collected and refined separately for use in cosmetics and pharmaceuticals. Finally, the clean wool enters a rotary drum dryer, where warm air circulates evenly as the drums continuously rotate, allowing heat to penetrate every strand. When the process is complete, the fibers reach a standard moisture level of around 12%, soft, vibrant, and completely free of contaminants, ready for storage and quality control. The dried wool bales are fed into a fiber blending machine. Each batch, varying in color, fineness, or origin, is precisely weighed and blended by rotating rollers with spiral blades that separate fibers clumped together during drying. A spray system maintains air humidity and prevents static, while sensors monitor speed for perfect uniformity. The fibers emerge soft, light, and springy, ready for the next mechanical stage. Entering the structural formation phase, the dried wool is fed into the carding section, where loose fibers are aligned in a single uniform direction. The material passes through a carding machine equipped with multiple metal-toothed rollers rotating at different speeds to create controlled friction and pulling force. Through this continuous motion, tangled fibers separate, straighten, and gradually clean themselves. Throughout the entire process, dust removal systems and electronic sensors eliminate short fibers, fine dust, and contaminants left over from previous cleaning stages. When the material exits the chamber, it emerges as a thin, continuous web of fibers, which automatically coils into soft slivers of consistent thickness and weight. After the carding stage is complete, the long and cleaned wool slivers move to the spinning section, a critical phase that determines the strength and fineness of the material. Here, the fibers enter a multi-roller spinning frame, where each roller spins at slightly different speeds to apply gradual drafting tension.
The front rollers hold the fiber steady, while the back rollers accelerate slightly, drawing the sliver thinner while maintaining its elasticity and internal cohesion. Before the twisting unit, the surface of each strand is coated with an ultra-thin layer of spinning oil, reducing friction and preventing static buildup. As the fibers pass through the central twisting unit, they bind tightly together into a single strand, forming a structure that's both strong and elastic. The degree of twist is controlled by tension sensors, ensuring perfect consistency along the entire length of the yarn. The finished threads are wound onto large spools, then rewound into smaller, standard-size bobbins. Optical scanners inspect every strand in real time, detecting thick spots, weak points, or over-twisted sections. Any defects are automatically cut and joined using thermal welding, creating smooth, seamless connections almost invisible to the naked eye. In the next stage of production, the wool threads, now refined to the perfect balance of fineness and strength, enter the weaving system, where the material transforms from loose threads into a unified textile structure. And just like that, having traveled from vast pastures through washing, carding, spinning, and weaving, ordinary sheep's wool becomes the foundation for warm sweaters, elegant coats, and luxurious blankets that keep millions of people around the world cozy.
You're holding $100 in your hand, a green piece of paper with Franklin's face on it. Light, thin, looks ordinary, but it's not paper, and it's not ordinary. This bill was printed in a building guarded better than the Pentagon. Cameras everywhere, motion sensors, armed security. Getting in there is harder than getting into Fort Knox. The paper for it was made using a secret formula, 75% cotton. 5 people in the world know the formula. Printed 3 times. Each time with different inks. Each time with precision down to a micron. One wrong stroke, and the bill is counterfeit. Checked by machines, every millimeter scanned. Rejects burned immediately. Not even one bad bill gets out. Because if it makes it outside, someone could forge it. This piece of paper is protected better than a vault in a bank. Watch till the end, you'll learn how money is printed. And you'll never look at a dollar as just a simple piece of paper again. Texas, cotton fields stretching to the horizon, heat pushing 100 degrees. White cotton bolls bursting on the bushes. Combines harvesting the crop, but not all cotton makes the cut for money. Only the longest fibers. White, strong, hand-selected, shipped to the factory, Massachusetts, town of Dalton, Crane Currency Facility. They've been making paper for dollars since 1779. Nobody else in the world has the rights. The grounds are guarded around the clock. Airport-level security screening. Cameras in every corner. Cotton gets mixed with linen. Boiled in massive vats. Water added. Creates a white pulp. Rolled into thin sheets. During the rolling, red and blue fibers get woven in. Randomly. Chaotically. Impossible to replicate the pattern. First line of defense. Then a security strip gets embedded. Thin metallic thread. Glows under ultraviolet light. Water pressed out. Dried. Cut into large sheets. Every sheet inspected against the light. Checking for defects. One air bubble. Sheet gets rejected. Finished paper gets packaged. Transported under convoy. Armed guards. Armored truck. Because if someone steals this paper, they can print real money. Washington, D.C. A building with no signs. Gray, nondescript. Inside, they print money. Bureau of Engraving and Printing. Security level like a military base. Metal detectors, retinal scanners, fingerprints. Even employees can't enter without triple verification. Cell phones banned. Cameras banned. Any recording devices confiscated. Inside, printing presses the size of a bus. Each one costs $10 million. Running around the clock. Sound like a jet taking off. Paper loaded in stacks. 32 sheets per stack. Each sheet will print 32 bills. First pass, background printing. Green patterns, fine lines. Hand-drawn by engravers, for months. One mistake, start over. Lines so fine they're invisible to the naked eye. That's the second anti-counterfeiting measure. Special ink. Formula classified. Made at a different facility. Under the same level of control. Sheets pass through the printing cylinder. Come out green. Wet. Dried under infrared lamps. Every sheet inspected. Sensors scan color, density, line alignment. Precision. 1/100th of a millimeter. Thinner than a human hair. Second pass. Intaglio printing. The most important one. Franklin's portrait, the numbers, the text, all of it printed under massive pressure. 3 tons per square centimeter. The ink gets pressed into the paper. Run your finger across it, you feel the texture. That's the main security feature. Impossible to fake. Regular printers can't do this, even professional ones. You need a special machine. There are 10 of them in the world, and they're all here. The printing cylinder is covered in microscopic grooves. The design is laser engraved. Precision, 5 microns. That's 10 times thinner than a human hair. The cylinders get replaced every year. The old ones are destroyed, melted down, turned into scrap metal. So nobody can recover the design. Sheets pass through the machine. Come out with Franklin's portrait. Sharp numbers, raised lettering. Another inspection. Machines scan every detail, compare it to the standard. If even 1 pixel is off, the sheet gets rejected. Rejects are set aside separately. Shredded at the end of the day. Burned. The ash dissolved in acid. Even the ash from dollars can't just be thrown away. Third pass, serial numbers. Every bill gets a unique code, 11 digits and letters. This combination doesn't exist anywhere else in the world. Printed in green ink, right side and left side. The numbers must match perfectly. The machine checks. If left and right don't match, rejected. Right then, they print the Treasury seal, green circle, and the Federal Reserve Bank seal, black. The letter shows which bank issued the bill. All of this happens in 3 seconds. The sheet runs through the machine, comes out with numbers and seals. Final inspection, the toughest one. Machines scan the bills under ultraviolet light, under infrared light, under magnification. They check 15 parameters: color, texture, security strip, watermark, line alignment, ink density, size, centering, numbers. Any deviation, rejected. Rejection rate, 3%. Out of every 1,000 bills, 30 get destroyed. Good sheets go to cutting. The rest, into the shredder. Cuts into individual bills. Precision, 1. Cuts into individual bills. Precision, 1/10 of a millimeter. If even one bill is cut crooked, the entire sheet is scrapped. Bills drop into a tray. A robot picks them up, counts them. 100 bills per stack. Wraps them in paper. 100 stacks per block. $10,000 in a single block. Blocks get wrapped in film, sealed, stamped with the date. Serial number, quantity, loaded into safe containers. Metal ones. Locked with 3 separate locks. 3 different people hold the keys. 1 person can't open it. Containers get loaded into an armored truck. Armed guards. 2 escort vehicles. Driven to the Federal Reserve Bank. There they're unloaded into the vault. Underground. Walls 3 feet thick. Steel-reinforced concrete. The bills sit and wait until some bank requests them. Then they're pulled out, counted, packaged, shipped off. Your local bank orders fresh bills. The request goes to the Federal Reserve. From there, they ship a container, again, under guard. Brink's armored truck, 2 armed guards. GPS tracker, dispatch communication. Any route deviation triggers an alarm. They arrive at the bank, unload into the vault, check the seals. Open the container, count everything, by hand and by machine. The amount must match to the cent. Some bills go into ATMs. An operator loads the cassettes, $4,000 in one cassette, inserts it into the ATM, closes it up, a TM's ready. You walk up, insert your card, enter your PIN, request $100. Inside, rollers activate. Grab one bill, sensors check it. If the bill's wrinkled or torn, the ATM won't dispense it. Takes the next one, feeds it through the slot. You grab it, fold it into your wallet, and walk away. Never thinking about the journey that piece of paper took. From a cotton field in Texas to your wallet. Secret paper, triple printing, 15 inspections, armed guards at every stage. Now you know. This bill isn't just paper. It's the most protected document in the world. It was printed by people who passed security clearances, working on machines worth $10 million, under cameras and sensors. Any mistake, and the bill is destroyed, burned, dissolved in acid, because even a defective bill in the wrong hands is a threat. Someone could study it, understand the technology, try to counterfeit it. That's why the security is so tight. You'll never look at a $100 bill like ordinary paper again, because now you know it has 300 years of technology encrypted in it. Red fibers in the paper are randomly placed. The security strip glows under ultraviolet light. Franklin's portrait is pressed under 3 tons of pressure. Microlines thinner than a hair. Serial numbers unique. This bill is impossible to counterfeit, even if you really try, because it wasn't made to be beautiful. It was made to protect money from counterfeiters, and it works.
Picture this. 8% of all CO2 on the planet comes from one industry, steel. Every single second, the world produces 60 tons of steel, and every ton leaves behind nearly 2 tons of carbon dioxide. But in Sweden, something seemingly impossible happened. They made steel without coal, 0 coal. Instead, hydrogen and electricity. Sounds like science fiction? In 2021, a Volvo truck built from this steel hit the roads, the first vehicle in history made from steel with a 0 carbon footprint. How is humanity walking away from a technology that's 3,000 years old? You'll learn why traditional steelmaking is killing the planet, how hydrogen is replacing coal in blast furnaces, and why this revolution will change everything, from skyscrapers to cars. Watch to the end. The finale will show you that the future of steel isn't black anymore. It's green. The history of steel production began 3,000 years ago when humanity learned to smelt iron. The principle remained unchanged for millennia. Iron ore is heated with coal. Carbon strips oxygen from iron oxide, and you get pure iron. This is called reduction. And the byproduct? Carbon dioxide, which escapes into the atmosphere. For centuries, nobody cared. In the 19th century, blast furnaces appeared, steel giants as tall as a 20-story building. Inside, temperatures hit 3,600 degrees Fahrenheit. Superheated air blasts in from below, while iron ore and coke, specially fired coal, get loaded from above. The ore descends, meets the carbon, and out comes molten pig iron, glowing orange like lava. Pig iron then becomes steel by blowing oxygen through it to remove excess carbon. This technology fueled the Industrial Revolution, built skyscrapers, bridges, ships, automobiles, but it comes with a monstrous cost. Every ton of steel requires about 1,300 pounds of coke. When burned and used to reduce the ore, it produces nearly 4,000 pounds of carbon dioxide for every ton of steel. Global steel production, almost 2 billion tons per year. Do the math. Around 7.5 billion tons of CO2 annually. That's 8% of all global greenhouse gas emissions, more than all aviation worldwide. If the steel industry were a country, it would rank third in emissions after China and the US. And the problem's getting worse. Demand for steel is rising, especially in developing countries. By 2050, emissions from steelmaking could double if nothing changes. Humanity's caught in a trap. Modern civilization is impossible without steel, but steel is killing the climate. Aluminum or plastic can't replace steel in most applications. The properties are just too different. We needed a revolution, and it started in cold Sweden, in the city of Luleå, above the Arctic Circle. In 2016, 3 Swedish companies, SSAB, Vattenfall, and LKAB, announced the launch of the Hybrid project, Hydrogen Breakthrough Iron-Making Technology, a breakthrough technology for producing iron with hydrogen. The idea seemed insane. Replace carbon with hydrogen in the ore reduction process. Instead of the iron plus carbon reaction that produces CO2, use iron plus hydrogen, which gives you H2O, water, just water, no carbon dioxide. But the challenge was titanic. They needed to build a hydrogen production plant using electrolysis, powered by renewable energy. They needed to design direct reduction reactors that use hydrogen to process iron. They needed to prove this iron could be transformed into quality steel and make all of it economically viable. 5 years of work, hundreds of millions of euros in investment. In June 2021, they fired up the world's first hydrogen-based steel plant in Luleå, a pilot facility, but fully operational. The revolution had begun. Now let's break down how this actually works. The process starts with hydrogen production. Typically, hydrogen comes from natural gas, but that creates CO2 emissions. Hybrid uses water electrolysis. They run electric current from wind and hydroelectric plants through water. The water splits into hydrogen and oxygen. Pure green hydrogen, zero emissions. This hydrogen feeds into a shaft furnace, a direct reduction reactor. Iron ore pellets get loaded from the top. These are walnut-sized granules made of iron oxide. Superheated hydrogen enters from below at around 1,500 degrees Fahrenheit. The hydrogen rises up through the pellet bed. A chemical reaction occurs. Hydrogen strips the oxygen from the iron oxide. What forms is metallic iron and water vapor. Yep, just steam. The pellets sink downward, gradually losing oxygen and transforming into porous iron, called sponge iron or direct reduced iron, DRI. What comes out are gray, porous granules of pure iron. But this isn't steel yet. The sponge iron gets loaded into an electric arc furnace, a massive steel vessel with graphite electrodes as thick as telephone poles. They run monstrous electrical current through these electrodes, tens of thousands of amps. Between the electrodes and the metal, an electric arc forms with temperatures reaching 6,300 degrees Fahrenheit. That's hotter than the surface of the sun. The iron melts in minutes. They add alloying elements, chromium, nickel, molybdenum, to get the exact grade of steel they need. The electricity for the furnace also comes from renewables, hydroelectric plants, and wind turbines. The molten steel glows blindingly white. They pour it into molds, let it cool. What you get are steel ingots or billets, indistinguishable in properties from conventional steel, but their carbon footprint, practically zero. The entire process uses not a single ounce of coal, not a single ounce of coke, not a cubic foot of natural gas, just iron ore, hydrogen, electricity, and water. This is fossil zero metallurgy. In August 2021, a historic event occurred. The company SSAB shipped its first batch of green steel to a customer. The buyer was Volvo. This steel was used to manufacture body parts for trucks. The first vehicles in human history made from carbon-free steel. Volvo ran tests: strength, fatigue resistance, weldability, corrosion resistance, all parameters identical to regular steel, or even better, because the process is more controlled, fewer impurities. In 2022, other companies also received batches of green steel: manufacturers of excavators, construction equipment, household appliances. Mercedes-Benz ordered a batch for use in passenger cars. SSAB announced that by 2026, it will launch the first full-scale hydrogen-based plant. Capacity, 1,300,000 tons of steel per year. By 2035, all SSAB products will be carbon-free. The company promises to cut Sweden's emissions by 7% just by switching to hydrogen. But hybrid isn't the only project out there. Right there in Sweden, they're building the H2 Green Steel plant, 5 million tons per year. Launch is set for 2025. In Germany, ThyssenKrupp is converting its blast furnaces to hydrogen. Austria's voestalpine fired up a pilot hydrogen plant. South Korea's POSCO is pouring billions into the technology. Even China, the world's biggest steel producer, announced it's building hydrogen plants. Governments are backing the tech with subsidies and tax breaks. The European Union rolled out a carbon tax on steel imports. More emissions, higher tariff. That makes green steel competitive. The big problem right now? The cost of green hydrogen. Hydrogen from electrolysis is still pricier than hydrogen from natural gas, but prices are dropping. Over the last 10 years, the cost of electrolysis fell by 2/3. As renewable energy capacity grows, hydrogen will get cheaper still. Another advantage of hydrogen metallurgy: it's way more compact. A traditional steel plant is an absolute monster of a complex. Coking plants, sintering factories, blast furnaces, converters, rolling mills, all of that eats up miles of land. A hydrogen facility is much tighter: an electrolyzer to produce hydrogen, a shaft furnace to reduce the ore, an electric arc furnace for melting. You can build a plant right next to your iron ore source and renewable energy, instead of hauling raw materials halfway across the globe. Swedish projects use ore from local Kiruna deposits, one of the largest in the world, and electricity from hydroelectric plants and wind farms in northern Sweden. Logistics get simpler, costs drop. Steel quality can be higher too. Direct reduction with hydrogen gives you purer iron with less sulfur, phosphorus, and other nasty impurities. That steel's better suited for high-strength applications: aviation, cars, bridges, wind turbines. Ironically, the green technology turns out to be technically superior as well. Sure, there are challenges. Hydrogen metallurgy demands massive amounts of electricity. Producing 1 ton of steel requires about 3.5 megawatt-hours of power. That's a small city's daily energy consumption. That's why projects are being built where cheap renewable energy is abundant. Scandinavia with its hydroelectric plants, Germany and Denmark with wind, Australia with sun. You also need infrastructure for storing and transporting hydrogen. It's an explosive gas. They're building special pipelines, storage tanks, safety systems. But all of this is solvable. The technology exists, the economics are starting to add up, and so is the political will. Analysts predict that by 2030, 10% of the world's steel will be produced with hydrogen. By 2050, a third or even half. That'll cut CO2 emissions by 1 billion tons annually, like removing 200 million cars from the roads. The metallurgy revolution, quiet but powerful.
And just like that, journeying from ancient blast furnaces where iron was smelted with coal 3,000 years ago, through recognizing an environmental catastrophe and searching for solutions, humanity arrived at hydrogen, the most abundant element in the universe. The very same gas that stars are made of now melts steel on Earth. Instead of black smoke from blast furnace stocks, water vapor. Instead of billions of tons of carbon dioxide, water. This is a story about how a technology that seemed unshakable was rewritten in a decade. Every time you see a new skyscraper, bridge, or car 10 years from now, know this: inside, possibly, green steel. Metal produced without harming the climate. The metal of the future, made from ore, water, wind, and sun. Black metallurgy is turning green. And this isn't just a color change, it's a paradigm shift. Humanity has proven you can build civilization without destroying the planet, even in an industry as dirty as steel.
the hydrogen revolution has begun, and it will change everything. The metal hiding in every muffler. Every minute, 130 cars roll off production lines around the world, and each one hides between 2 and 7 grams of palladium, a metal more expensive than gold and platinum, so rare that all the world's reserves could fit in a single room. But without it, every modern city would choke. Palladium scrubs poisonous substances from exhaust gases. 85% of all palladium mined goes into automotive catalysts. Platinum's little brother has become the critically important metal of the 21st century. How do you extract a silvery metal worth $40,000 per kilogram from ore mined a kilometer underground in Siberia? You'll learn why palladium was named after an asteroid, how it transforms poison into harmless gas, and why its reserves could run out in 20 years. Watch until the end. The finale reveals what stands behind the clean air in our cities. This is the story of the metal the future of the automotive industry depends on.
The story of palladium began in 1803 in London. British chemist William Wollaston was studying platinum ore from South America. He dissolved the ore in aqua regia, a mix of hydrochloric and nitric acids, the only solvent capable of dissolving platinum. From the solution, he extracted platinum, but noticed some impurities remained in the solution. Wollaston performed a series of chemical operations and isolated a new metal, silvery white, similar to platinum, but lighter. He named it palladium after the asteroid Pallas discovered a year earlier. Coincidence or not, Pallas in Greek mythology is the goddess of wisdom. Palladium turned out to be an amazing metal. It could absorb hydrogen in volumes 900 times its own. Picture this. A cube of palladium 1 centimeter by 1 centimeter can soak up nearly a liter of hydrogen. The metal swells up like a sponge. But the key property was discovered later, catalytic activity. Palladium speeds up chemical reactions without taking part in them. For a long time, palladium remained a laboratory curiosity. It was used in jewelry. White gold often contains palladium. In dentistry, for dental crowns. In electronics, palladium contacts don't oxidize, but consumption was minimal, just a few tons a year for the entire world. Everything changed in the 1970s, when environmental regulations suddenly got much stricter. Car exhaust contains carbon monoxide, nitrogen oxides, and unburned hydrocarbons, all of them toxins. Cities were choking in smog. A solution was needed, and one was found: the catalytic converter, a device that transforms poisonous gases into harmless ones. Inside a stainless steel casing, a ceramic honeycomb structure coated with an ultra-thin layer of platinum, palladium, and rhodium. Hot exhaust gases pass through the honeycomb. On the surface of the platinum group metals, reactions occur. Carbon monoxide converts to carbon dioxide, nitrogen oxides to harmless nitrogen, hydrocarbons burn off. The converter cuts emissions by 95%. But there's a price. Each converter contains precious metals.
Palladium turned out to be perfect for the job. It's cheaper than platinum, but better at oxidizing hydrocarbons. With environmental regulations rolling out in Europe and the US, demand for palladium exploded. Production jumped from just a few tons a year to 300 tons. The price rocketed from $500 per troy ounce in the 90s to $3,000 in 2020. Palladium became more expensive than gold and platinum. Catalytic converter thefts started spreading. Thieves cut the converter out from under a car in 5 minutes and sell it for $200 to $500. The palladium inside is worth even more. The problem is, palladium is one of the rarest elements out there. In the Earth's crust, it makes up 6 parts per 10 billion. That's 30 times rarer than gold. Worldwide, only about 200 tons of palladium get mined each year. For comparison, 3,000 tons of gold, 20 million tons of copper. Palladium doesn't form its own deposits. It shows up as an impurity in nickel and platinum ores. Main sources, Russia and South Africa. 70% of the world's palladium comes from Russia, mostly from the Norilsk mining complex in Siberia. Norilsk is a city above the Arctic Circle, one of the most northern cities on the planet. Winter temperatures drop to -50. But underground lies a unique deposit of copper-nickel ores containing platinum group metals. The ore is mined in shafts up to nearly a mile deep. They blast the rock, load it onto dump trucks, bring it to the surface. The ore contains about 1% nickel, fractions of a percent copper, and just a few grams per ton of platinum group metals: platinum, palladium, rhodium, iridium. But the volumes are massive. 20 million tons of ore per year. The ore is crushed, ground into fine powder, enriched by flotation. The process is similar to lead ore enrichment. They get a concentrate containing 10 to 15% nickel and copper and elevated levels of precious metals. The concentrate is smelted in massive furnaces. This produces matte, an alloy of nickel, copper, and iron sulfides. All the platinum group metals are concentrated in the matte. Feinstein gets shipped to a metallurgical plant. There, it's converted, blasted with oxygen at temperatures hitting 1200 degrees. Iron and sulfur oxidize and get stripped away. What you're left with is crude nickel-copper alloy containing the platinum group metals. This alloy gets dissolved in sulfuric acid. Nickel and copper go into solution. Precious metals stay behind in the residue, what they call slimes. These slimes contain up to several percent platinum group metals. It's not palladium yet, but it's highly concentrated feedstock. The slimes get dissolved in aqua regia, that same acid mixture Wollaston used. All the platinum group metals go into solution. Now the ultra-precise separation chemistry begins. From the solution, they sequentially precipitate platinum, palladium, rhodium, iridium, ruthenium, osmium. Each metal precipitates at a specific pH with specific reagents. The process takes weeks. The result, precipitates of various palladium salts. These salts get calcined at high temperature. You get sponge palladium, a gray porous powder. It's almost pure metal, but not yet a marketable product. Spongy palladium gets melted down in an induction furnace under argon or vacuum. Palladium can't oxidize. The molten metal pours into ingots. You end up with small bars weighing anywhere from a few ounces to 2 pounds. Silvery white with a slight steel tint. Palladium's softer than platinum, so you can roll it, forge it, draw it into wire. Palladium's melting point, 2,828 degrees Fahrenheit, lower than platinum. Density, about 0.43 pounds per cubic inch, lighter than platinum, but still a seriously heavy metal. Palladium doesn't tarnish in air, doesn't react with most acids, only dissolves in aqua regia and hot concentrated nitric acid. Corrosion resistant. But here's the key property, catalytic activity. Palladium speeds up oxidation and reduction reactions. On its surface, gas molecules get adsorbed, activated, react with each other. That's exactly what makes palladium irreplaceable in automotive catalytic converters. The entire journey from ore to metal takes months and involves dozens of processing steps. How does a palladium car catalytic converter work? The device looks like a metal canister installed in the exhaust system right after the engine. Inside is a ceramic honeycomb structure, like an actual beehive. Thousands of channels in this structure. Total surface area, several square feet. The surface is coated with aluminum oxide, a thin porous layer that multiplies the area hundreds of times over. On top of that layer, palladium, platinum, and rhodium. Total weight between 2 and 7 grams. Palladium and platinum oxidize carbon monoxide and hydrocarbons into carbon dioxide and water. Rhodium reduces nitrogen oxides back to nitrogen. Exhaust gases at temperatures between 750 and 1470 degrees Fahrenheit flow through the honeycomb. Reactions happen on the metal surfaces. What comes out? Almost pure nitrogen, carbon dioxide, and water vapor. Efficiency, up to 98%. Without a catalytic converter, a car dumps dozens of grams of toxins into the atmosphere every mile. With one, fractions of a gram. A modern passenger car contains 3 to 5 grams of palladium, a truck or SUV up to 7 grams. Here's the problem. Palladium reserves are limited and running out. There aren't many accessible deposits left. At current extraction rates, proven reserves will last 20 to 30 years. Prices are climbing. The shortage is getting worse. Automakers are hunting for alternatives to palladium. They're partially switching to platinum. It's also a catalyst, but more expensive and less effective for gasoline engines. For diesels, platinum works better. Recycling palladium from spent catalytic converters is ramping up. Old converters get collected, crushed, and the platinum group metals extracted. Recycling provides up to 30% of palladium supply. It helps, but it doesn't fully solve the problem. Demand keeps growing. Around 90 million cars roll off production lines worldwide every year. Electric vehicles don't use catalytic converters, but their share of the market is still small. Hybrids still need palladium. The palladium market's unstable. Prices swing from $2,000 to $3,000 per troy ounce. Palladium has become a strategic metal. The entire automotive industry and urban air quality depend on it. And just like that, journeying from ore a mile deep beneath the Siberian permafrost, through months of chemical operations and ultra-precise separation, palladium emerges into the world. Platinum's younger brother, now the champion of clean air. A few grams of silvery metal hidden inside every muffler, saving millions of lives annually. The rarest of elements, 30 times scarcer on Earth than gold, has become critically vital to modern civilization. It's the paradox of technological progress. The more we care about ecology, the more we depend on rare metals. Every time you start your car, remember, beneath the chassis works a palladium catalyst, transforming poisons into harmless gases. A metal worth $40,000 per kilogram makes city air breathable. From the asteroid palace to automotive catalysts, 220 years of history for a metal that found its calling in the fight for ecology. But reserves are dwindling, prices are climbing, and palladium's future looks uncertain. Perhaps in 20 years, humanity will discover a replacement, or learn to recycle more efficiently, or switch to electric vehicles. But for now, palladium remains the thin silvery thread connecting 1 billion automobiles to clean air, the metal without which megacities would suffocate, the hidden hero of the environmental revolution, tucked away in every muffler.
Hey folks, on this channel, we go where cameras usually aren't allowed. If you dig these behind-the-scenes deep dives, hit subscribe and smash that bell so you don't miss new episodes. Today, I'm showing you how they make those manhole covers we walk over every day without even thinking about it. Turns out, it's way more interesting than you'd expect. I'm standing in the middle of a foundry floor, and it's about 110 degrees Fahrenheit in here. Sweat's pouring down like crazy, my glasses are fogged up, and the air's thick with the smell of molten metal and coal. Black coke dust crunches under my feet, and in the distance, a furnace pulses with a crimson glow. Come with me. I'll show you everything from the first ladle of molten metal to the finished cover. I'm met by the foundry master, a man in his 60s, with hands scarred by thousands of sparks. He's worked here for 38 years and says he's seen manhole covers cast for every major city. His creations lie everywhere beneath our feet. It all starts with scrap metal, massive piles of old cast iron, engine fragments, pipes, radiators, even old manhole covers that have served their time. Cast iron can be remelted an infinite number of times without losing its properties. It's one of the few things humanity gets right. Metal recycling here is 100%. The scrap is sorted by composition, weighed, and crane-loaded into a cupola furnace, a massive furnace about 30 feet tall, resembling a medieval tower. Inside, layers of coke and cast iron scrap alternate. The coke burns at around 2,700 degrees Fahrenheit, and at that temperature, the cast iron melts, transforming into a glowing orange liquid that flows to the bottom of the furnace. I stepped closer, as close as safety regulations would allow, and felt the skin on my face instantly tighten from the heat. At 15 feet, The temperature is so intense you want to back away. But the workers stand right by the furnace in special reflective suits, looking like astronauts. When the iron's melted, they release it into a ladle, a massive metal scoop that holds about 2,000 pounds. The ladle hangs from a crane and glides smoothly over rows of sand molds laid out across the factory floor. Each mold is the negative of a future manhole cover, an imprint of every detail, every letter, every ridge. The molds are made from special sand mixed with clay and water. A master craftsman showed me how it works. They take a wooden or metal model of the cover, press it into the sand, then carefully lift it out. What's left is a perfect impression. Every line, every curve, copied with accuracy down to a few thousandths of an inch. They place the second half of the mold on top, and you've got a cavity ready for the metal. A single model can produce thousands of impressions before it needs replacing. The coolest part? The text on the manhole covers. Each one shows the name of the city or water department. The letters are made separately. Small wooden or plastic type pieces get pressed into the sand in just the right spots. When the iron hardens, the text pops out. That's why all the words on manhole covers are mirror images of what was in the mold. Now comes the most spectacular part, the pour. Two workers in silver suits tilt the ladle, and out flows a stream of molten iron. It glows so bright you can't look at it without protective glasses. Your eyes start watering after a couple seconds. The metal hits 2,600 degrees Fahrenheit. The iron fills the mold in 5 seconds flat. But you've got to pour carefully. Too fast and the metal traps air, creating pockets inside the manhole. That cover will be weak and could crack under the weight of a truck. Too slow and the metal starts hardening on the way down, filling the mold unevenly. An experienced foundry worker feels the right speed instinctively. It's a skill that takes years to develop. The sand mold starts smoking after the pour, moisture from the sand and clay evaporating. The smoke is thick, gray, smells like scorched earth. Ventilation runs full blast, but visibility in the shop still drops to about 50 feet. Then comes the waiting. The iron needs to cool, but not too fast. Slow cooling is what gives the metal its proper structure and strength. Open the mold too early, and the manhole cover warps from the sudden temperature shift. Scrap. The sweet spot is 18 hours. During that time, temperature gradually drops from about 2,550 degrees Fahrenheit down to around 210. The molds sit in rows on the shop floor, radiating steady, dry heat, like a radiator. Next day, workers smash the sand molds with hammers, and out come the manholes, still hot, dark gray, coated in sand residue. They look rough, messy, nothing like those smooth covers lying in the streets. Each manhole cover weighs between 66 and 132 pounds, depending on the size. A standard cover for city sewers runs about 24 inches in diameter and weighs roughly 95 pounds. I tried lifting one, barely got it off the ground. The foreman laughed. He's been lifting 10 of these a day for nearly 40 years. Next, the covers go to processing. A special machine with rotating steel cable brushes cleans off any remaining sand. Sparks fly in every direction. The metal gradually takes on a clean gray color. Pneumatic hammers knock off the flash, leftover metal that solidified in the wrong places. The most critical step is machining the seating surface. The cover's edge has to fit the frame perfectly or it'll rattle under traffic. Tolerance, about 1/10 of an inch. A lathe turns the edge to perfect roundness, and every cover has small holes, 2 or 4. They're for the special hook utility workers use to pull covers out. Without them, lifting a 95-pound cast iron lid off a flat surface is basically impossible. The quality control here is amazing. An inspector just taps each manhole cover with a small hammer and listens to the sound. If the sound is clean and ringing, the cover's good. If it's dull or has an off tone, there's a crack or void inside somewhere, and that cover gets scrapped. He checks 200 covers a day and says he's never wrong. I ask why manhole covers are round. Seems like square ones would be simpler to make. The foreman explained something brilliantly simple. A round cover can never fall through its own hole. A square one can be turned diagonally and drop right down. A circle is always bigger than its opening, no matter how you turn it. That's why manhole covers are round all over the world. It's not tradition, it's math. Another detail, the pattern on the surface. Those grooved lines, stars, or grid patterns aren't there for looks. It's an anti-slip coating. Smooth cast iron in the rain is slippery as ice. With the ridges, traction is way better. I stood on one cover right there in the shop, held firm even in work boots with smooth soles. Finished manhole covers get stacked 10 to a pile and shipped out to cities. Each stack weighs around 900 to 1,100 pounds, so they only load them with a crane. One factory produces 50,000 covers a year. Sounds like a lot, but a major city alone might have over 300,000 manholes. That means every few years, every single cover needs replacing. Why so often? The covers break down. Sand and salt in winter, vibrations from trucks, temperature swings from -22 to 130 Fahrenheit on the asphalt in summer. Cast iron is tough, but it's not forever. Average lifespan is 30 years, and in high traffic areas, just 5. There are covers for steam tunnels, telephone, electrical, water mains. Each type differs slightly in size and thickness. The thickest ones are for highways, where they get run over by trucks weighing 36 tons. There, the wall thickness hits 2 inches. The factory museum holds old manhole covers, the oldest one from 1892. Over 130 years old, and it's still intact. The cast iron's dark, smooth from time, but not a single crack. There are covers from different countries: France, Japan, England. The Japanese ones are the most beautiful, engraved with cherry blossoms or mountains. Over there, manhole covers are art. When I left the factory, there was an ordinary manhole cover lying in the street. I stopped, crouched down, ran my hand across its surface. Now, I see it differently. This isn't just a lid. This is 2,700 degrees of heat, 18 hours of waiting, precision down to 1/10 of an inch, workers' hands in silver suits, and the ring of an inspector's hammer. Every manhole cover beneath our feet has been through this journey and will last another 30 years, bearing thousands of tons, millions of footsteps, rain, snow, and heat.
Every year, over 1,000 giant ships are sent for scrapping, each weighing up to 50,000 tons, nearly the length of 3 football fields. It's like dismantling an entire floating city with hundreds of miles of cables, tons of toxic substances, and metal worth millions of dollars. One mistake, and an environmental disaster becomes inevitable. But here's the thing, that's not even the most surprising part. Inside each of these massive vessels lies something that turns scrapping into a genuine treasure hunt. Workers risk their lives amid plasma cutters and toxic fumes to extract these valuables. What exactly are they after? And why have some countries turned ship graveyards into a multi-billion-dollar business whose dark side everyone stays silent about? Stick around till the end. What you're about to discover will make you look at every ship in port with completely different eyes. This is the story of how steel giants die and new metal is born. Why is ship recycling important? The vessels we typically picture as massive floating megastructures can stretch nearly 1,000 feet long. Their weight sometimes reaches tens of thousands of tons, making them among the largest man-made objects created for ocean travel and cargo transport. But beyond their massive scale, these ships have an incredibly complex internal structure. Hundreds of miles of cables, pipelines, shafts, and various safety and comfort systems, plus countless different components and mechanisms serving different functions. This entire architecture isn't just metal, it's a complex organism that needs to be very carefully and properly dismantled when a ship reaches the end of its service life. It's absolutely critical to properly remove all hazardous substances accumulated during its operation. These can include bioactive materials, toxic paints, fuel residues, oils, chemicals. If handled improperly, these substances can contaminate the ocean, soil, and air, causing serious environmental problems. Without proper preparation, dismantling such a vessel can turn into a disaster for nature. However, recycling these ocean giants has a very bright positive side. The metal the ship is made from is excellent and valuable raw material that can be recycled and returned to production. This metal is used to build houses, cars, construction structures, and even create new ships. This reduces the need for smelting new steel, saves energy and resources, and also cuts down on waste. Recycling metal from ships becomes a critical link in the closed loop of the modern industrial economy. Disposing of such massive objects also frees up ports where old vessels sit, making room for new, modern ships. The ship is brought to specialized ship graveyards, typically shorelines with shallow water or dedicated slipways. These locations aren't chosen randomly. Shallow shorelines allow easy beaching, where the vessel can be safely moored and dismantling can begin. Often these are small bays or beaches where the massive ship is deliberately run aground so it doesn't obstruct maritime traffic or damage port infrastructure. Slipways, on the other hand, are large platforms or specialized structures where the ship is positioned for land-based dismantling. They're equipped with everything needed for convenient and safe operations: crane equipment, metal cutting tools, waste removal systems. One of the specialists' primary tasks is ensuring environmental safety. After all, during its operational life, the ship accumulated many substances that could harm the environment if handled carelessly. We're not just talking about oil and fuel residue here, toxic paints and chemicals too. That's why the entire scrapping process kicks off with removing all that hazardous stuff. Fuel and oil get drained into special containers and hauled away for processing or disposal, keeping them out of the water and soil. Same goes for electronics and furniture. Anything that could potentially harm the environment gets pulled out first. This stage demands speed and extreme caution, so environmental regulations aren't violated. Once the ship's been cleared of all hazardous and everyday materials, the actual hull dismantling begins. And this is the toughest and most dangerous part. Using specialized plasma cutters and gas torches, massive steel structures get sliced into smaller pieces. It takes both handheld equipment and heavy machinery, cranes, lifts, specialized manipulators. Plasma cutting allows for incredibly precise, fast, and efficient separation of metal that'll later be melted down and recycled. The dismantling process itself happens sequentially, step by step, starting with the most difficult to reach or hazardous zones. Metal sheets, beams, decks, and internal bulkheads are carefully removed to avoid damaging structures that might still be needed for analysis or processing. The challenge is that these massive components are often unevenly positioned and may be under tension, and due to corrosion or hull deformation, sections can unexpectedly shift or collapse at any moment. Worker safety is also critically important. During plasma cutting, hot sparks and toxic fumes are generated, requiring workers to use special protective equipment, respirators, specialized clothing, and constant air quality monitoring. A small mistake or disregard for safety protocols can lead to serious injuries and accidents. That's why every step of the process is governed by strict safety protocols, and the entire facility is covered by fire suppression systems and medical support. Breaking down the hull and main steel structures of the ship is, without a doubt, an incredibly important and complex stage in scrapping a giant vessel. But once that massive chunk of work is done, the job isn't over. Up next, another huge phase that demands just as much attention and a certain level of skill, because it involves dismantling and sorting tons of smaller yet equally valuable and complex materials. One of the most massive and challenging processes is dealing with cables. A ship contains hundreds of miles of cable networks that power and connect all its systems. These are heavy-duty steel cables with plastic insulation, rubber, and maybe even non-ferrous metals mixed in. Cables don't just sit around at the recycling yard. They're carefully extracted, processed, and sorted. Separating the metal core from the insulation materials makes it possible to send pure copper or aluminum for remelting, while the insulation layer goes for processing as raw material for new polymers. Workers have to be really careful not to damage long cable sections, and they've got to follow safety protocols because of residual substances or rust. Another important category of materials is insulation materials that are glued to or fill the ship's walls, technical spaces, and pipelines. Insulation is often made from specialized materials: mineral wool, polyurethane foam, or basalt wool. These substances help control temperature inside systems and ensure safety when working with hot or cold components. After the insulation is extracted, it's sorted and sent to specialized facilities. Working with ventilation systems demands equal care. Ventilation ducts and units, used for air conditioning and circulation throughout different parts of the vessel, get dismantled and cleaned of dust, oil residue, and other substances. The metal components of these systems are typically high-quality material for remelting, while plastic or rubber often becomes raw material for new products. Special attention goes to water supply systems and sanitary installations. A ship carries complex shut-off mechanisms: piping, fittings, faucets, tanks, and other equipment. Pipe sections and equipment get carefully separated, cleaned of sediment, oil, and other contaminants before being sent for remelting or appropriate processing. These materials can contain toxic substances, so their disposal or recycling follows strict protocols. Equally critical is dismantling equipment from the engine room. That's where you'll find engines, generators, pumping systems, turbines, and other complex machinery. Stuff that's usually heavy as hell and packed with metals, including non-ferrous ones. This equipment mostly gets repaired and reused or broken down into parts, some of which are recycled. In certain cases, engines are even sold as used spare parts, dodging the scrap heap entirely. Furniture, appliances, lighting, and other interior items from the ship don't just get tossed either. They're removed and sorted. Wooden, metal, or plastic components go through separate recycling or disposal processes. Sometimes, if furniture's in decent shape, it gets sold for reuse. And just like that, after going from floating city to thousands of tons of sorted raw materials, the giant ship gets a second life in new homes, cars, and even new vessels. This is the story of how the death of a steel giant becomes the beginning of a new life for millions of tons of metal.
Every year, the world mines thousands of tons of metals, but only one is so dangerous it can kill you even as dust, and yet helps us peer 13 billion years into the universe's past. That's beryllium, a metal lighter than aluminum but many times harder than steel, a metal without which the James Webb Space Telescope wouldn't exist. But there's one detail almost nobody talks about. Why does producing it feel like a chemical nightmare? And why does working with it become a deadly gamble? And what exactly are those factories hiding behind thick, protective glass? Subscribe so you don't miss out. You'll learn something that'll forever change how you think about metal. Let's jump straight to the numbers, because they're absolutely mind-blowing. Look at this block of metal. Appears to be just another gray hunk of iron, but try to lift it and you'll nearly clock yourself in the chin from the surprise. Beryllium has a density of just 1.85 grams per cubic centimeter. That's almost 30% less than aluminum, which we've always considered the gold standard for lightness. But here's the kicker. Despite being this lightweight, beryllium is 4 times stiffer than steel. Its elastic modulus hits an incredible 303 gigapascals. What that means is this material puts up insane resistance to any deformation. You could build a structure thin as paper, and it would still hold its shape under colossal stress. On top of that, beryllium has this exceptional ability to maintain its strength at high temperatures, making it absolutely irreplaceable in the aerospace industry. The extraction process, that's a whole chapter in the textbook of industrial survival. The primary source here is a mineral called bertrandite, mined in the deserts of Utah. The ore contains just 0.5% beryllium. To extract this metal, the rock gets crushed and dunked into sulfuric acid, turning everything into a chemical slurry. Then, through a series of complex manipulations with hydroxides and fluorides, they get pure beryllium fluoride. They mix it with magnesium in massive crucibles and heat it up to 2400 degrees Fahrenheit. The magnesium grabs the fluorine, and shiny metallic grains settle to the bottom, so-called pellets, or beryllium pebbles. Each grain is only a few millimeters across, but it's from these tiny pieces that parts for spacecraft and military hardware will eventually be assembled. But this is just the beginning, because working with them directly is impossible. And here's where we get to the most dangerous part of the tour. Beryllium is a genuine toxic bomb. Its dust causes chronic beryllium disease, which basically makes your lungs shut down. All it takes is breathing in a microscopic amount of particles and your immune system starts attacking your own tissues. The disease can show up years after exposure, when you've long forgotten that one day you spent at the facility. So nobody here pours the metal into molds like cast iron. Instead, they use powder metallurgy methods. Metal grains get ground into fine powder in special mills under vacuum. Every single dust particle has to be controlled. Then, they pour this powder into massive steel capsules and subject it to vacuum hot pressing. Imagine hundreds of atmospheres of pressure and temperatures over 1800 degrees Fahrenheit, simultaneously crushing this powder, forcing it to become a solid block. This goes on for hours until the structure becomes perfectly uniform. Why did the telescope engineers choose this hellish material for their mirrors? It's all about the cold of space. James Webb operates at Lagrange Point 2, about 930,000 miles from Earth, where temperatures plunge to minus 370 degrees Fahrenheit. Regular glass deforms unpredictably when it cools this much, expanding in one spot, contracting in another. But beryllium has a unique property. Its thermal expansion coefficient at low temperatures becomes virtually zero. It basically freezes in place. The shape stays constant no matter how brutal the cold gets. This made it possible to build mirrors that remain perfectly smooth even in the savage cold of deep space. Each of the 18 mirror segments measures 4.3 feet across but weighs just 44 pounds. If they were made from glass, each one would tip the scales at over 200 pounds, and the rocket simply couldn't lift off the ground. Each mirror was carved from a single block, removing 90% of the mass from the back to create a lightweight honeycomb structure. This is called lightweighting. The walls there are just a few millimeters thick. After that, polishing begins. It's done using computer systems that remove irregularities measured in nanometers. 1/1000th of a meter. That's the precision we're talking about here. If Webb's mirror were the size of the Atlantic Ocean, the biggest bump on its surface wouldn't be taller than a regular coin. Then the mirrors are taken to a cryogenic chamber, where they're cooled to space temperatures, microscopic warping is measured, and then they're polished again to compensate for those changes. This cycle was repeated dozens of times over several years. Now take a look at this color. We're used to seeing telescope mirrors in gold, but underneath that gold lies pure beryllium. The gold is only applied at the very end through vacuum deposition. The gold layer is just 100 nanometers thick. That's 1,000 times thinner than a human hair. The entire massive mirror, covering about 270 square feet, used only about 1.7 ounces of gold. That's like 3 or 4 wedding rings rolled out across a giant surface. Gold is essential because the telescope searches for infrared radiation from the very first stars that ignited 13.5 billion years ago. Beryllium provides rigidity and stability, while gold delivers perfect reflection in the precise wavelength range needed. At this facility, safety protocols look like paranoia, but it's justified paranoia. See those yellow lines on the floor? You can't cross them without special footwear. The air in the shop completely refreshes every 3 minutes. Beryllium levels in the air must not exceed 0.2 of a microgram per cubic meter. That's so small you couldn't even see it under a microscope. But sensors are everywhere. After every shift, each worker goes through a special shower, and their clothing gets disposed of as hazardous waste. That's the price we pay for the ability to peer into the depths of space. But beryllium isn't just about space. Look at these tiny components for aircraft engines. Because beryllium conducts heat better than most metals, it's perfect for parts that need to cool down fast. Its thermal conductivity is around 210 watts per meter Kelvin. It pulls heat away faster than aluminum and doesn't melt until 1287 degrees. This lets planes fly faster and engines run more efficiently. Here's another wild fact you probably won't hear in chemistry class. Beryllium is almost transparent to X-rays. Take an X-ray through a steel plate, you'll see nothing. But with beryllium, the rays pass through like it's not even there. That's exactly why the windows in every X-ray machine and CT scanner at hospitals are made from beryllium foil. It lets doctors get crystal clear images of your body without losing radiation power at the machine itself. So what does all this cost? If you want to buy a kilogram of pure beryllium, expect to shell out anywhere from $800 to $1,000. But that's just raw material. The cost of a finished part can be 10 times higher or more because of how difficult it is to machine and all the safety precautions required. A single web mirror segment cost millions of dollars when you factor in all the years of testing and polishing. And even with these insane prices, global beryllium production doesn't exceed a few hundred tons per year. That's how rare and difficult it is to work with. Thanks for watching. Hit that like button if you love real science as much as I do. See you at the next classified facility.
Every year, the world produces billions of square feet of veneer, a petal-thin material hiding the strength and beauty of entire forests. Picture this. From a single log, you can get enough surface area to cover a football field. That's exactly why this industry is worth over $40 billion annually. From one perfect American walnut log, about 3 feet in diameter, you get anywhere from 10,000 to 30,000 square feet of unique surface. One log, almost an entire football field of veneer. Using veneer cuts the need to harvest valuable tree species by 98% compared to making furniture from solid wood. Instead of cutting down 20 trees to make 20 tables, you can harvest one perfect tree and leave the other 19 growing in the forest. But what's behind that number? How does an ordinary tree go through spa treatments, fiery tunnels, and encounters with scalpel-sharp blades to become luxury furniture? Watch closely. At the end, you'll discover a secret almost nobody realizes. Picture a lumber mill that specializes in veneer production. Massive logs of premium hardwoods, oak, ash, maple, walnut, cherry, arrive here by truck. But not every tree makes the cut. These have to be perfectly straight, tall trees with large trunk diameters, and most importantly, free of knots, cracks, and other defects for a significant height. Every knot is a scar that ruins the perfect grain pattern. That's why only the finest specimens are chosen for a veneer. When one of these perfect logs arrives at the mill, it doesn't go straight to the blade. First, it gets the industrial spa treatment. The logs are submerged in enormous pools of hot water or placed in special chambers filled with hot steam. This isn't about cleanliness. This process, lasting anywhere from several hours to several days, at temperatures around 212 degrees Fahrenheit, does two crucial things. It softens the wood, making it more pliable and cooperative for cutting, and it transforms its color, making it richer and more uniform. After the hot bath, the bark gets stripped from the log. A special machine peels away the rough outer shell, revealing clean wood underneath. And now comes the most critical moment before the main show, centering. The log gets locked into the machine, and an operator uses lasers to find its perfect axis of rotation. This is absolutely crucial. Giant pencil in a giant sharpener. The log starts spinning around its axis, and the blade cuts into the spinning wood and starts shaving off a continuous wide ribbon of veneer, just 1/50th to 1/8 of an inch thick. It's like unrolling a paper towel roll. An endless, wet, flexible sheet comes out of the machine, which is then cut into pieces of the right size. This method is highly productive, but it creates a characteristic chaotic pattern that isn't always valued in high-end furniture. The second method, used to obtain the most beautiful decorative veneer, is called slicing. This isn't a sharpener anymore. It's the world's biggest cheese slicer. Here, a log, or part of it cut into beams, is firmly secured to a movable platform. Above it, or to the side, sits a massive, sharp blade. The platform with the wood moves back and forth, or up and down, and with each pass, the blade shaves off a single, perfectly flat sheet of veneer. It's a slower, less productive process, but it's what gives you that refined, linear, or figured grain pattern we value so much in expensive furniture.
Depending on exactly how the log was cut before slicing, you can get different types of patterns: radial, tangential, mimicking the look of solid plank.
Freshly cut veneer, no matter the method, is called green. It's soaking wet, flexible like damp paper, and tears easily. It needs to dry. The ribbons or sheets of veneer are carefully fed into a long drying chamber. Think of it as a giant tunnel oven, where the veneer slowly moves along on rollers or a mesh conveyor. Hot air circulates inside, gently and evenly pulling moisture out. The process is tightly controlled. Dry it too fast and the veneer will crack or buckle. Within minutes, that wet, floppy sheet becomes dry, slightly brittle but stable. After drying, the veneer sheets have ragged edges. They're stacked high and sent under a massive guillotine. A sharp blade slams down and in one stroke slices off the rough bits, creating perfectly straight edges. Now the sheets are ready for the most critical stage, where it's not machines doing the work, it's people with trained eyes. This is sorting.
Specialists carefully inspect each sheet, evaluating its color, grain pattern, and any defects, then sort them into bundles by grade. It's meticulous work, because this determines the veneer's price and application. But individual veneer sheets are often too narrow for making something like a tabletop, so they need to be joined into one large panel. This process is called stitching or splicing. Two sheets with perfectly straight edges are fed into a special machine. It presses them tightly together, and a specialized mechanism bonds them. This could be a thin zigzag line of adhesive or a glued paper tape. The result? A large, continuous veneer sheet, ready to be applied to a substrate. Now for some history. Using thin layers of wood goes back thousands of years. Ancient Egyptians used veneer to decorate sarcophagi and furniture 3,000 years ago. But modern industrial veneer production only began in the 19th century with the invention of steam engines and precision machinery.
The first veneer peeling lathes appeared in the mid-19th century and revolutionized the furniture industry. Instead of sawing valuable wood species into thick boards and losing most of the material to sawdust, manufacturers could now obtain ultra-thin sheets, maximizing every inch of the log. The global veneer market is a massive industry, turning over more than $40 billion a year. The largest producers are China, the US, Germany, Italy, and Indonesia. Veneer isn't just for furniture. It's used in making doors, musical instruments, yacht interiors, luxury car interiors, and premium space finishes. But the most important application is plywood. Yes, ordinary plywood as we know it is multiple layers of veneer glued together with perpendicular grain direction. This exact structure gives plywood its strength and resistance to warping. And now the most impressive number behind veneer, its efficiency rating. Take one massive, perfectly straight log of premium American walnut, several yards long and about 3 feet across. If you just sawed it into boards, you could make, say, one big table and a few chairs. Now here's the kicker. If you slice that same log into veneer just 24 thousandths of an inch thick, you can get anywhere from 10,000 to 30,000 square feet of unique surface. To put that in perspective, that's enough to cover almost an entire football field from a single log.
Using veneer cuts the need to harvest precious hardwoods by 98% compared to making solid wood furniture. Meaning instead of cutting down 20 trees to build 20 tables, we can harvest one perfect tree and leave the other 19 growing in the forest. This makes veneer one of the most environmentally responsible ways to use wood. But veneer has another hidden advantage that few people think about. The thing is, the most beautiful, unique wood grain patterns are often found in the most unusual parts of a tree, where the trunk branches out, in burls, in the root section. If you saw a tree like that into boards, these areas often end up as scrap because they're too small or irregularly shaped. But with veneer production, even a small section with a unique pattern can be turned into several square meters of luxurious material. There are entire categories of exclusive veneer made from burls, wood growths with incredibly complex, swirling patterns. One burl the size of a soccer ball can yield enough veneer to finish an entire study, and this veneer can cost thousands of dollars per square meter. There's even a market for archive veneer, material made from trees cut down decades or even centuries ago and stored in warehouses. Some species of wood that are now protected or extinct can only be found in the form of this archive veneer.
Veneer manufacturing technology is constantly evolving. Modern machines are equipped with laser scanning systems that analyze the log structure before cutting and select the optimal angle and method to produce the most beautiful grain pattern. Computer control allows sheets less than half a millimeter thick to be sliced with precision down to hundredths of an inch. New processing methods are being developed that enable veneer to be stained, embossed with textures, and made to imitate rare species. And so, after journeying from a majestic tree in the forest through a hot bath at 200 degrees Fahrenheit, past a knife sharp as a scalpel, and through the fiery tunnel of a dryer, this material emerges, thin as a petal, carrying all the beauty, history, and unique character of the forest, ready to bring a piece of it into our homes. These billions of dollars aren't just money, they're proof that beauty and practicality can walk hand in hand, allowing us to enjoy nature's unique patterns without causing irreparable harm. Every sheet of veneer is a thin slice of a tree's history, one that lived for decades or centuries, and is now ready to serve humanity for centuries more in the form of beautiful furniture.
Picture this, a sheet of aluminum, 4 millimeters thick. You can bend it with your bare hands, scratch it with a key, punch through it with a hammer. Now imagine that exact same material is what makes up the wing you're sitting on at 36,000 feet. That wing's carrying 300 tons at 550 miles per hour, and it doesn't break, doesn't bend, doesn't crack, for decades. How does a 4 millimeter sheet transform into a structure you trust with your life? Today we're going behind the scenes at an aircraft manufacturing plant where they press wings and fuselages for passenger jets. And I'm going to show you every single step of that journey. If you're into deep dives like this, hit subscribe and ring that bell so you don't miss new episodes. It all starts in the raw materials warehouse. And the first thing that hits you is the scale. Aluminum sheets and plates are stacked several meters high, each sheet marked with its alloy designation. Aviation doesn't use regular aluminum. They use 2000 and 7000 series alloys, enhanced with copper, zinc, and magnesium. These additions make the metal several times stronger than pure aluminum, while keeping its light weight. Every batch arrives with a passport, chemical composition, mechanical properties, ultrasonic inspection results. If even one parameter falls outside tolerance, the entire roll goes back to the supplier. There's no such thing as good enough here. The cost of a mistake is measured in human lives. From the warehouse, sheets travel to the cutting shop on special carts with soft padding to prevent surface scratches. Laser and water jet cutters slice blanks from digital templates, each part cut to within tenths of a millimeter. A single wing skin set comprises hundreds of parts in different shapes and thicknesses, and each one has its own unique number in the engineering documentation. Now for the most spectacular part, forming. That flat sheet needs to become a panel with precise curvature, matching the aerodynamic profile of a wing or the roundness of a fuselage. For this, they've got presses that'll take your breath away. The hydraulic stretch press for skin forming. This machine stands as tall as a 3-story building, with force measuring tens of thousands of tons. The aluminum sheet gets clamped along the edges by special grips. A massive steel die, the punch, rises from below with the exact shape of the future panel, and the press slowly, inch by inch, stretches the sheet around this form. The metal stretches, takes on the curvature, and stays that way forever. The sound, a deep, heavy groan of metal that makes the floor vibrate under your feet. The entire pressing cycle takes several minutes, but prepping for one cycle? Hours. Setting up the die, calibrating the force, checking the sheet temperature, because cold aluminum behaves completely differently than warm. For fuselage panels, they use a different method, shot peen forming. It looks almost absurd. They lay a flat sheet on a table and blast it with steel balls about a millimeter in diameter from special nozzles under pressure. The balls hammer the surface at enormous speed, creating thousands of microscopic dents. The top layer of metal stretches while the bottom stays the same, and the sheet starts to curve on its own, like running scissors along a ribbon and watching it curl into a spiral. By controlling the intensity of the bombardment and the impact zone, you can achieve precisely the curvature you need, that signature fuselage roundness. The method seems crude, but the precision is stunning, within tenths of a millimeter on panels several meters long. After forming, each panel gets checked with a laser scanner. The beam sweeps across the entire surface, building a 3-dimensional model of the part that's overlaid on the digital reference. The computer highlights deviation zones, and if even a single point falls outside tolerance, the panel goes to scrap or rework. The formed panels aren't wings or fuselage yet. They're just skin, a thin shell that can't handle anything serious on its own. To make it withstand flight loads, internal structural elements are attached from the inside, stringers and frames. Stringers are long profiles running along the structure. They handle tension and compression. Frames are cross-sectional rings that maintain the shape. Together, they form a skeleton to which the skin gets riveted. And this sandwich of shell and framework can now bear enormous loads. And here begins the most painstaking work, riveting. A single wing on a passenger jet has several 100,000 rivets. Each one is made from a special aviation alloy. Each one goes into a drilled hole with precision down to a few thousandths of an inch. Automated riveting machines place up to several thousand rivets an hour. The robot drills the hole, inserts the rivet, bucks it, and immediately checks the force. But there are places the robot can't reach. That's where people work. A riveter with a pneumatic hammer and bucking bar is one of the most respected workers on the aircraft factory floor. While the skin is being made, they fabricate the spars, the main load-bearing beams of the wing. These are the most heavily stressed parts in the entire aircraft. The whole fuselage hangs from them, along with passengers, fuel, and cargo. A spar for a large airliner is a single piece up to 115 feet long, milled from a solid aluminum plate several inches thick. A 5-axis machine removes up to 90% of the original metal, leaving behind a complex landscape of ribs, webs, and flanges. Milling a single spar takes up to 24 hours of continuous operation. The cutting tool follows its programmed path inch by inch, and you can't stop the process because any pause will leave a mark on the surface. From a plate weighing several tons, you get a part that weighs 10 times less but can carry loads of hundreds of tons. The chips don't go to waste. They're collected, pressed into briquettes, and sent back for remelting. When all the parts are ready, assembly begins. The wing is assembled in a special jig, a massive steel frame as long as the wing itself, holding every component in its exact position. First, they install the spars, then the ribs, transverse frames that define the aerodynamic profile, followed by the stringers, and finally, the skin. Panels are fitted and riveted one after another. At every stage, inspectors check gaps, alignment, and rivet tension. The tolerance for panel fit-up is 0.3 of a millimeter. If the gap is larger, the panel comes off and gets refitted. Assembling one wing takes about 2 weeks. The fuselage is built in sections: nose, center, tail, and each is finished completely on its own. Then they're joined into a single tube. The moment of joining is an incredible sight. 2 enormous cylinders, several meters in diameter, slowly approach each other on rails, slide together with a gap measured in fractions of a millimeter, and lock in place with thousands of bolts and rivets. After assembly comes sealing. Every seam, every rivet hole in the fuselage gets coated with a special sealant that turns flexible and waterproof when it cures. Without it, at 36,000 feet, where pressure is 4 times lower than at sea level, air would leak through microscopic gaps, making it impossible to keep the cabin pressurized. After sealing, they close up the fuselage and pump in pressure, simulating flight conditions. Sensors all over the body track leaks. If air's seeping out somewhere, they hunt it down, find it, fix it. Only after passing that test does the section get cleared. The wing goes through its own trials. They mount it in a test rig and bend it upward with hydraulic cylinders, slowly, carefully, measuring deflection at hundreds of points simultaneously. The wing has to withstand bending several feet upward without breaking. It flexes like a bow, but doesn't snap. During certification tests, they bend the wings until they actually break to know the exact failure limit and confirm it exceeds the design spec with margin to spare. Once the wing and fuselage pass every inspection, they're hauled to final assembly. That massive hangar the size of several football fields, where ceilings soar 10 stories high. Here, wings mate with the fuselage through the central keel beam. Landing gear gets installed, engines hang beneath, cockpit and systems go in. From separate sections, an airplane is born. The entire journey from flat sheet aluminum to finished wing, that's months of work, hundreds of operations, millions of control points. Every rivet recorded in a passport, every seam documented, every panel with its own story, from metal smelting to the machine number that formed it. Next time you sit by the window and look at that wing, remember, this structure started as a flat sheet barely 1/6 of an inch thick, and every fraction of that journey, someone's work, someone's inspection, someone's craft. This ship doesn't go around the ice, it goes straight through it. 10 feet of frozen ocean, and it doesn't care. I'm standing in a shipyard where they're assembling the hull of a nuclear-powered icebreaker, and in front of me is a giant steel skeleton that will soon be working where temperatures drop below -50, and ice pressure can crush any ordinary structure like a tin can. You know, I usually go look at things you can touch without risking your cheek freezing to them. But today, I slightly overestimated my ambitions. And right now, I'm going to show you how a machine is born that makes even the Arctic itself back down. The first thing that hits you at the shipyard isn't the size, though the future vessel stretches over 500 feet long, and individual hull plates run several inches thick. What stuns you is the steel itself. They don't use ordinary rolled stock here. An icebreaker hull demands special steel grades that stay flexible even in brutal cold. Regular steel turns brittle in the freeze. Strike it, and it'll crack like glass. This stuff, though, has to take impacts from ice fields and not fail. The engineers explain it simply. The hull needs to give a little, flex slightly under pressure. Otherwise, the Arctic will just snap it. Massive steel plates arrive at the yard already rough processed from the rolling mill. Each plate weighs dozens of tons, and when the crane lifts one into the air, it looks like a chunk of an apartment building somebody randomly decided to relocate. But the icebreaker's shape doesn't appear all at once. First, these plates pass through giant rollers that slowly, with enormous force, bend them to the required angle, giving the metal that crucial curve without which the hull can't push ice aside. In front of me, steel rollers, each as thick as a decent tree trunk, stacked one above the other. Between them, they slowly feed a flat steel sheet. Heavy, rigid, seemingly completely inflexible at first glance. The operator gives the command, and the mechanism starts moving. The rollers rotate at low speed, but with massive force. The sheet gradually gets pulled inside, and at some point, you can see it start to change shape. First, it's a barely noticeable bend. Then the radius increases, and the metal's no longer flat. It curves smoothly, as if obeying someone's will. The sound here is unique, a muffled pressure, grinding, and a slight crackling, like the metal reluctantly gives in. I'm standing nearby, and I hear how the steel literally groans under the load, a sound like you're pressing on something really stubborn, and it's grudgingly surrendering. They might roll the sheet several times, adjusting the roller positions each time, until they get the exact angle or curvature. And there in front of you is no longer just a piece of steel, but part of a future hull that perfectly matches its contours. By the way, if you're into stories about how seriously complex and powerful machines are built, hit subscribe so you don't miss the next episode. Now, let's keep going. Next comes the assembly of sections, and this looks like a giant construction set, except each block weighs as much as a small locomotive. Individual hull blocks are assembled in the shop. These can be sections 60 or even 100 feet long. Inside each block, there are already bulkheads, cable routes, and even foundations for future decks. In other words, the hull isn't built from scratch in one spot. It's assembled in pieces, like a puzzle, just really heavy and really hot to produce. I walk into the shop and there are finished sections already standing there. These aren't just sheets of metal, they're entire fragments of the future ship. Inside each one, you can see passageways, openings for cables, spots where pipes, wires, and entire life support systems will run later. Then these blocks are transported to the slipway and joined together. The cranes move in. They lift the section into the air slowly, smoothly, no sudden movements, and transport it to the slipway. There, they carefully lower it and fit it against the already installed parts of the hull. At this moment, you literally see separate pieces starting to come together as one. The future icebreaker takes shape right before your eyes. Welding is a whole different story. You can't just run a bead and go grab coffee. Every joint goes through multiple levels of inspection. First, the welder lays the main seam. Then they check it with ultrasound to make sure there are no voids or cracks inside. If something's off, they cut it out and do it over. I watched them redo one seam 3 times, and nobody even got stressed. That's standard practice here, because the price of a mistake in the Arctic isn't just a breakdown, it's a potential catastrophe. And that's how it goes. Every seam, every joint, along the entire length of the hull. We should talk about the hull shape. An icebreaker doesn't just have a strong bow, it's specifically designed to climb up onto the ice and break it with its own weight. That's why the bow section has that distinctive slope, and they reinforce it with extra layers of steel. In some spots, the thickness multiplies several times over, and inside they add ribs that distribute the load along the entire length of the ship. While I'm walking around here, there's constant movement everywhere. Cranes, platforms, people in hard hats, for whom all this is just another workday. Though honestly, when they're moving a whole section weighing dozens of tons right over your head, you kind of rethink the word ordinary. One of the engineers jokes that the scariest thing here isn't the cold or the metal, it's when someone forgets their lunch in the shop, because finding it among all this scale is practically impossible. When all the sections are connected, the whole starts taking its final shape. Its length becomes physically tangible. You walk alongside and catch yourself thinking it's like strolling past an apartment building, only horizontal. The height of the hull is impressive too. Several levels that will eventually become decks, engine rooms, and crew quarters. After that comes surface treatment. The metal gets cleaned, anti-corrosion coatings applied, painted with special compounds that reduce water friction and protect the hull from salt and ice. It looks like cosmetics for a giant, but in reality, this coating determines how many years the ship can operate without major repairs. And that's not an exaggeration. Arctic saltwater and constant ice friction can destroy unprotected metal in just a few seasons. Modern nuclear icebreakers can ram through ice up to 9 feet thick while underway, and the newest designs are rated for ice up to nearly 15 feet thick. Power, that's a whole other story. Heavy icebreakers can pump out over 75,000 horsepower, and without that, they simply wouldn't budge the ice. I'm standing here staring at this hull, and it hits me. This isn't a finished vessel yet. There's no reactor in here, no propellers, no control systems. But even now, the main thing is crystal clear. This is a structure built to battle the elements, where every millimeter of steel serves a purpose. And when she heads out to sea, she won't just sail. She'll carve a path where other ships wouldn't even dare to go. I'm gonna stick around here a bit longer. Listen to that metal grinding. Watch these machines come to life. Then head out to prep your next adventure. Because after something like this, you want to find something just as massive, just as complex, just as beautifully insane. When you stand next to a structure like this, you start seeing what humans can actually build differently. Not on a computer, not in theory, but right here, with hands, steel, and fire. And I think I've already got a couple ideas where to head next. So stick around, it's gonna be good. There's a metal so rare that humanity mines less of it in an entire year than it does gold in a single day. A metal that costs anywhere from $4,000 to $9,000 per kilogram. A metal you've probably never heard of, yet right now it's keeping the plane you flew on for vacation from falling out of the sky. This is rhenium, the rarest stable element in Earth's crust, a silvery white metal that doesn't exist as a standalone ore and is only extracted as a byproduct. Without it, there would be no modern jet engines, and aviation would be stuck at mid-20th century levels. Let's start with the scale of rarity. Rhenium makes up about 7/1000ths of a part per million in the Earth's crust. For comparison, gold is 4/1000ths, platinum is 5/1000ths. The numbers seem comparable, but there's a fundamental difference. Gold and platinum can be found as nuggets or concentrated ores. Nature sometimes gathers them in one place. Rhenium is never found that way. It's scattered as microscopic impurities in other ores, mainly molybdenum and copper. The concentration is so low that even calling it rhenium ore is incorrect. It's always ore of something else that happens to contain rhenium. Rhenium itself looks like a silvery white metal with a slight grayish tint. But most people have never seen pure rhenium. Even in industry, it's more often used as alloys or powder. In nature, rhenium occurs in just one mineral, jacasganite, which is so rare it literally exists in only a few places on the planet and has no industrial significance. All industrial rhenium comes as a byproduct of processing molybdenum concentrates, which themselves are a byproduct of copper mining. A byproduct of a byproduct. That's what rhenium is. Think about the scale here. To get just 1 kilogram of rhenium, you need to process roughly 200,000 tons of copper ore. 200,000 tons of rock for a single kilogram of metal. It's like searching for a needle, not in a haystack, but in an entire field planted with hay. The main sources of rhenium are molybdenum mines in Chile, the US, Kazakhstan, and Armenia. Chile dominates, about 50% of global production. The Chuquicamata mine in the Atacama Desert is one of the largest open-pit mines on the planet, where they extract copper and molybdenum, pulling out rhenium along the way. The pit is so massive you can see it from space, roughly 2 3/4 miles long, nearly 2 miles wide, and over 3,000 feet deep. Extracting rhenium is complex and multi-staged. First, copper ore gets mined and enriched through flotation to produce copper concentrate. That concentrate contains molybdenum, which also gets enriched and separated out. Molybdenum concentrate is molybdenum sulfide with microscopic traces of rhenium, typically 0.05 to 0.2%. Sounds convoluted, but it's essentially a chain: copper ore to molybdenum concentrate to rhenium solution. At each stage, volume drops by factors of thousands, while value skyrockets. The molybdenum concentrate gets roasted in special furnaces at around 1,100 degrees Fahrenheit and higher in open air. Molybdenum oxidizes to trioxide, which can then be reduced back to metal. But rhenium behaves differently. It oxidizes to rhenium heptoxide, which vaporizes at this temperature and escapes with the gases. Those gases pass through a complex system of scrubbers, towers where they're washed with water or alkaline solutions. Rhenium heptoxide dissolves, forming rhenic acid or perinates. Rhenium concentration in these solutions is tiny, grams per liter, but that's something you can work with. The solution is purified of molybdenum, copper, lead, and other metal impurities through multi-stage chemical treatment: extraction, ion exchange, precipitation. Then rhenium is precipitated as a white crystalline powder, ammonium perrhenate. This is the most common form of rhenium feedstock for further processing. To obtain metallic rhenium, the powder is heated in a stream of hydrogen at temperatures exceeding 1,800 degrees Fahrenheit. Hydrogen reduces the rhenium oxide to pure metal. The result is rhenium powder, which can then be sintered, melted, or used directly in alloy production. Each year, humanity produces about 50 tons of rhenium. 50 tons! That's the entire global output. For comparison, about 3,000 tons of gold are mined annually. Copper, 20 million tons. Rhenium is so rare that global reserves at any given moment are measured in hundreds of tons, not thousands or millions. Here's the question: why mine something this rare in the first place? The answer? Jet engines. About 80% of all rhenium goes to the aviation industry for making superalloys that form turbine blades. A jet engine turbine blade operates in absolute hell. Gas temperatures hit 2,700 degrees Fahrenheit. That's above the melting point of the alloy the blade is made from. So it's cooled from the inside by airflow through microchannels. The pressure is colossal. The blade spins at tens of thousands of revolutions per minute, experiencing monstrous centrifugal loads. A corrosive environment with sulfur impurities from jet fuel. And all of this for years of continuous operation with zero margin for error. Because if a blade cracks mid-flight, the engine destroys itself. Nickel-based superalloys, the primary material for blades, contain nickel, chromium, cobalt, tungsten, molybdenum, aluminum, titanium. But even these incredibly complex alloys couldn't withstand high temperatures for extended periods, until they added rhenium. Rhenium does something remarkable. It dissolves into the nickel matrix of a superalloy and blocks defect movement in the crystal structure at high temperatures. This is called creep, the gradual deformation of metal under load when heated. All metals creep, but rhenium slows this process down dramatically. Adding just 3% rhenium to a nickel superalloy raises the operating temperature by about 54 degrees Fahrenheit. Doesn't sound like much, but in jet engines, every 18 degrees of additional temperature yields roughly 1% more efficiency. And efficiency means fuel consumption, flight range, airline economics. Modern superalloys contain up to 6% rhenium. A single turbine blade can hold anywhere from 5 to 20 grams of rhenium. One engine on a large passenger jet, about 13 pounds of rhenium in the blades alone. 13 pounds of metal worth up to $50,000 in a single engine. And a plane has 2 engines. Every year, thousands of jet engines are manufactured. Passenger, cargo, military, and virtually all the rhenium mined goes straight into them. Because of its rarity and high cost, the industry is desperately trying to reduce rhenium consumption. New generations of superalloys with lower content are being developed, along with the use of ruthenium, an element from the same group that could theoretically replace rhenium. But ruthenium is even rarer and more expensive, so for now, it's just research. Single crystal blade technology makes rhenium work smarter. Instead of a regular polycrystalline structure, each blade is grown as one massive crystal with no grain boundaries, which are weak spots at high temperatures. This lets you cut down on rhenium content while keeping performance. But the process is complex and expensive. Each blade is grown individually in specialized vacuum furnaces with extremely slow, controlled cooling that takes hours. Recycling rhenium from spent blades is mission critical. After thousands of hours in hellish conditions, blades wear out and get replaced. The old ones don't get tossed, they're melted down, rhenium and other precious metals extracted and used again. Around 30% of rhenium comes from recycling, more than most other metals. And the reason's simple. At these prices, nobody can afford to throw rhenium away. The remaining 20% of rhenium is used in other areas. Platinum rhenium catalysts in oil refining to boost gasoline octane ratings, filaments for mass spectrometers and electron microscopes, anode materials for X-ray tubes. The strategic importance of rhenium is enormous. Countries without access to rhenium cannot produce modern jet engines. And this isn't just a matter of civil aviation, but military, fighters, bombers, cruise missiles. Interestingly, rhenium was one of the last stable elements to be discovered. German chemists found it in 1925 while examining platinum ore through spectral analysis. They named it after the Rhine. Before that, Mendeleev had predicted the existence of element number 75, but no one could find it because of its extreme rarity. Basically, the entire world supply of this metal would fit in a few trucks, and the whole world's aviation depends on those few trucks.
Every second, the world produces 28 million tons of stainless steel. And behind the shine of every spoon, every faucet, every surgical instrument stands one metal: chromium. But here's what's mind-blowing. Chromium melts at 3,375 degrees Fahrenheit, and in the electric arc furnaces that produce it, temperatures hit 5,000 degrees, hotter than the surface of the sun. A single furnace consumes 4,000 kilowatt hours of electricity per ton of alloy. That's as much as the average apartment uses in 4 months. 80% of all chromium in the world goes into making stainless steel. But where does this metal come from? Why are 99% of the world's chromite reserves concentrated in just a handful of countries? And what happens in that hellish zone beneath the electrodes where ore transforms into molten ferrochrome? Stick around. You'll discover how black rock gives birth to the metal that makes steel immortal. Picture a massive electric arc furnace as tall as a 3-story building. 3 carbon electrodes up to 6 feet across plunge into a churning mass of glowing ore, coke, and fluxes. Between the electrode tips and the furnace floor, electric arcs crack and snap. Temperatures in this zone hit 5,000 degrees Fahrenheit. That's hotter than the surface of the sun. The air above the furnace shimmers with heat. Clouds of smoke and gas blast out from beneath the half-closed roof. Inside, real alchemy unfolds. Chromium ore mixed with coke melts down, oxygen escapes as carbon monoxide, and molten ferrochrome, an alloy of chromium and iron, flows to the bottom. This is a submerged arc furnace, and this is where most of the world's ferrochrome is born. The process runs non-stop. Fresh batches of ore and coke pour in from the top, molten metal and slag tap out from the bottom. A single furnace like this can pack 25 to 45 megavolt amperes of power. This is a monstrous amount of energy. An entire power plant runs just to melt the ore. When enough molten ferrochrome accumulates in the furnace, workers punch open the tap hole, a special opening in the furnace's side. And then the mesmerizing spectacle begins. A stream of white-hot metal and slag bursts out, flowing down a channel into an enormous ladle. The stream's temperature around 3,000 degrees Fahrenheit. The metal glows bright orange, almost white. The heat radiating from it is so intense that workers stand dozens of yards away, protected by special screens and fireproof clothing. Slag floats to the top and is drained off separately. The ferrochrome cools in massive molds, transforming into solid ingots weighing hundreds of pounds. These ingots are later crushed into pieces of the right size for sale to steel mills. But the process of obtaining ferrochrome, that's only the middle of the journey. It all begins with ore, mined deep in the earth. Chromite, the only industrial ore of chromium. It's a dark brown, almost black mineral with a metallic luster. The chemical formula? Iron and chromium oxide. Pure chromite contains 68% chromium oxide and 32% iron oxide. But in nature, perfect ores like that barely exist. Real deposits contain anywhere from 40 to 50% chromium oxide. Chromite forms in igneous rocks, in massive molten masses rising up from the Earth's mantle. The largest deposits are found in South Africa, Kazakhstan, India, and Turkey. These 4 countries account for roughly 80% of global production. South Africa is the absolute leader. Its deposits in the Bushveld complex contain 200 million tons of chromite. We're talking ore seams stretching for hundreds of miles and plunging thousands of feet deep. Kazakhstan holds reserves of 230 million tons. India? 54 million tons. Now, the story. French chemist Louis-Nicolas Vauquelin discovered chromium in 1797. He isolated it from croquat, a bright red lead chromate mineral. The mineral's vivid color inspired Vauquelin to name the metal after the Greek word chromos, color. Because chromium compounds produce stunning colors, greens, yellows, oranges, reds. A year later, in 1798, Vauquelin isolated pure chromium by reducing the oxide with carbon. Iron with added chromium was first produced in the mid-1800s, and the first use of chromium as an alloying element in steel production happened in France in the 1860s. The revolution came in 1893 when Henri Moissan smelted chromium ore with carbon in an electric furnace and produced ferrochrome. This became the foundation of the modern industrial method, which has evolved but at its core remained the same. Chromite gets mined both through open-pit operations and underground mines. Open-pit mining gets used when the ore sits close to the surface. Giant excavators strip away the soil and overburden, exposing the chromite layers. Then they blast the ore, load it into haul trucks with capacities up to 300 tons, and transport it to the processing plant. Underground mining gets deployed for deep deposits. Tunnels get driven hundreds of feet down, sometimes miles. They blast the ore, load it into mine cars, and haul it to the surface. The extracted ore? It's not pure chromite yet. It comes mixed with waste rock and other minerals. That's why the ore needs processing. First, they crush it in massive jaw crushers. Chunks the size of a car get reduced to fist-sized pieces. Then they grind it in ball mills down to the size of sand or even dust. After that comes separation, isolating the chromite from the waste rock. The main method for enriching chromite is gravity separation. Chromite is heavier than waste rock. Its density is 4.5 to 4.8 grams per cubic centimeter, while the rock is 2 to 3 grams. The crushed ore is mixed with water, creating a slurry. The slurry passes through jig machines, concentrating tables, spiral classifiers, centrifugal separators. Under the force of gravity, the heavier chromite grains settle faster, while the lighter waste rock is carried away by the water flow. Magnetic separation is also used. Chromite is weakly magnetic, but modern high-intensity magnetic separators can attract it and separate it from non-magnetic impurities. After enrichment, they obtain chromite concentrate containing 46% or more chromium oxide. This is ready-made raw material for metallurgy. The concentrate is dewatered, dried, and sent to ferroalloy plants. Lump ore is needed for ferrochrome production. Fine powder doesn't melt well in the furnace. So the fine particles get agglomerated, sintered into large chunks. They mix the concentrate with fluxes and coke breeze, moisten it, and form pellets. Then they heat it to about 2,200 degrees Fahrenheit. The pellets sinter into solid lumps a couple inches across. Now the ore is ready for smelting. At the ferroalloy plant, chromite concentrate gets mixed with coke and fluxes in specific proportions. Coke is the carbon source that'll reduce the oxides down to metal. Fluxes, quartzite, dolomite, limestone, are needed to form slag with the right composition and melting point. The charge, the mix of ore, coke, and fluxes, gets loaded into the electric arc furnace from the top through special hoppers. Loading happens continuously or in batches depending on the furnace type. The electrodes, massive carbon cylinders, are submerged in the charge layer. When they switch on the current, an electric arc forms between the electrodes and the material beneath them. Temperature in the arc zone? 5,000 degrees Fahrenheit and higher. That's enough to melt any ore. Inside the furnace, complex chemical reactions take place. Carbon from the coke combines with oxygen from chromium and iron oxides, forming carbon monoxide that rises upward. Chromium and iron are reduced to their metallic state and fuse together, forming ferrochrome. Some of the carbon dissolves into the metal, producing high carbon ferrochrome with a carbon content of 4 to 8%. Typical South African ferrochrome contains 52 to 54% chromium, 6 to 7% carbon, and 2 to 4% silicon. Ores from Zimbabwe with a higher chromium to iron ratio yield a product with 63 to 67% chromium. The molten ferrochrome and slag accumulate in the lower part of the furnace, the hearth. When enough metal has built up, they open the tap hole. Metal and slag flow into a ladle. The slag floats to the top and is poured off or skimmed away. The metal is poured into molds or cooled in special forms. Once solidified, the massive ingots are broken down by hydraulic presses or hammers into pieces of the required size. Ferrochrome production is incredibly energy intensive. A single ton of high-carbon ferrochrome burns through 2,000 to 4,000 kilowatt-hours of electricity. That's why ferrochrome plants get built in countries with cheap power, often right next to hydroelectric dams. Chromium recovery from ore hits about 90% under good conditions. The remaining 10%, it goes into slag. Slag isn't just waste. Metal particles get extracted from it using mineral processing methods, and what's left goes into construction. Ferrochrome isn't the end product. It gets shipped to steel mills where it's added to molten steel for alloying. Chromium gives steel corrosion resistance, hardness, heat resistance. Stainless steel contains 10 to 20% chromium. Average, 18%. It's chromium that forms a thin, invisible oxide film on the steel's surface, protecting the metal from rust. And so, having traveled from black rock in the Earth's depths, through quarry explosions, crushing and processing, through the inferno of an electric arc furnace at 5,000 degrees Fahrenheit, ferrochrome is born. An alloy that gives steel eternal life and shine, resistant to time and corrosion. In the scorched Arizona desert, among endless sands, lies the most expensive graveyard on the planet. 4,000 aircraft, worth over $35 billion. This isn't a museum and it's not a junkyard. This is where war machines that once ruled the skies come to die. Picture this, an area bigger than 2,000 football fields, and on every square foot, stories of wars, victories, and defeats. Legendary B-52s that bombed Vietnam rest here. F-14S that defended the skies over Iraq stand here. New patients arrive every single day. But what happens to these giants after they touch down for the last time? Some get stripped for parts in a matter of weeks. Others sleep here for decades, waiting for resurrection. And some just get wiped off the face of the earth. Stick around till the end. You'll find out how machines worth millions die and why this place is called America's Boneyard. (1946). World War II had just ended, and America faced a problem nobody had thought about. Tens of thousands of warplanes were suddenly obsolete. B-17Es, B-24Es, fighters, bombers, all worth billions. But the world wasn't at war anymore. Selling them was out of the question. The technology was classified. Keeping them on active bases? Too expensive. So the military found a solution. Davis-Monthan Air Force Base in Arizona, a place where it rains 4 times a year, where humidity is practically zero, and where the temperature kills any corrosion. Hard-packed alkaline soil, natural concrete, no need for hangars or runways. The desert climate turned this place into the perfect graveyard for aircraft. The first 600 planes from the war flew in. They were parked in neat rows, mothballed and forgotten. Nobody imagined that 70 years later, there'd be over 4,000 aircraft sitting here. The 60s, the Cold War is at its peak. America is building bombers capable of delivering nuclear weapons to Moscow. The B-52 Stratofortress. Weight, 83 tons. Wingspan, 184 feet. A machine built to destroy cities. By the 70s, they'd built over 700 of them. But technology changes fast. Missiles appear that fly faster and more accurately. Bombers become obsolete. Where do you put these giants? Davis-Monthan. The base is expanding. Now it's not just a storage yard, it's a whole industry. 365 personnel. Mechanics, engineers, preservation specialists. They take in aircraft, assess their condition, and decide the fate of each plane. Some get preserved for long-term storage. Others get stripped for parts within a month. Still others head to the guillotine, a giant machine that slices the fuselage into pieces. The decision comes down to one thing. Does the military need this model? The 90s. The Cold War is over, and at the airplane graveyard, the largest destruction in aviation history begins. The Strategic Arms Reduction Treaty demands proof. Bombers must be destroyed so Russian satellites can see it from orbit. They position a B-52 on the pad, and a 13-ton guillotine drops onto the fuselage. The crunch of metal echoes for half a mile. In 15 minutes, a machine that cost $100 million becomes chunks of aluminum. Cameras capture everything for the satellites, proof of destruction. Over several years, they cut up 365 B-52s this way. Each aircraft is a story. Vietnam, Operation Desert Storm, dozens of combat missions. But treaties matter more than history. The metal goes to the smelter. One bomber yields about 50 tons of aluminum, enough to make 1,200 bicycles. That's how legends of the sky die. The process begins long before the aircraft touches down in Arizona. The military makes the call. This bird is retired. Could be a lot of reasons. Outdated model, maintenance costs through the roof, political decisions, structural wear after thousands of flight hours. The plane makes its final flight. Pilots joke it's the last ride to paradise. Though for the machine, it's more like a waiting hell. Davis-Monthan Base greets it in the receiving area. First thing, complete inspection. Engineers check every system. Engines, avionics, hydraulics, electronics. A detailed report gets compiled. This will determine the aircraft's fate. Category 1. Storage with restoration potential. These birds can return to service in 5, 10, even 15 years. Category 2, an organ donor. Everything valuable gets stripped out. Category 3, my complete disposal. This plane goes under the cutting torch within weeks. Decision made. Preservation begins. If a plane ends up in storage, it's prepped for a long sleep in the desert. This isn't just park it and forget it. It's a meticulous process refined over decades. First, they drain all fluids. Fuel, hydraulics, oils, every last drop. Even the slightest residue can cause corrosion or fire. Then they preserve the engines. They're coated with a special compound that protects the metal from oxidation. The cockpit is sealed. Every opening, air intakes, nozzles, hatches, gets covered with special film. It reflects sunlight and keeps the internal temperature from reaching critical levels. Without it, the cockpit turns into an oven. Desert temperatures in summer hit 120 degrees Fahrenheit. Electronics are sealed in protective bags with silica gel, which absorbs moisture. Landing gear gets treated with anti-corrosion coating. The whole process takes about 3 weeks. After that, the plane is rolled out to its spot. Neat rows like a parade of frozen giants. Here it can sit for years. But most aircraft meet a different fate. They become donors. Picture this. Hundreds of planes flying overhead that need parts. An engine for an F-16 costs $3 million. Brand new. But what if you pull it from a mothballed airframe? $800,000. The savings are massive. That's why there's an entire disassembly industry here. Mechanics show up with orders. Need a radar? Pull it from tail number 412. Need a turbine? That F-15 over there will give up its own. The process is surgical. Aircraft aren't stripped barbarically. They're disassembled by the book. Every part gets cleaned, inspected, tested. They document serial numbers, flight hours, condition. Then they package it and ship it to warehouses. One retired aircraft can give life to dozens still flying. Every year, more than 20,000 parts ship out from here. The value of those parts? Over $500 million annually. The aircraft boneyard operates like a giant parts store for all of American aviation. But some planes aren't so lucky. Their time is truly up. The model's obsolete and nobody needs their parts. Or treaties demand complete destruction. That's when the final act begins. The aircraft gets rolled onto a special pad. This is where the monster works, the Igor guillotine. 13 tons heavy, tall as a 3-story building. It's a hydraulic cutter that can slice a B-52 fuselage clean in half in 20 seconds. Brutal process, but efficient. The blade drops and metal 3/4 of an inch thick cracks like cardboard. The fuselage splits apart. Then excavators with shears roll in. They cut the wings, rip off the tail, crush the cockpit. In one day, a single crew can turn 5 aircraft into a pile of scrap. Aluminum gets sorted by grade, titanium separate, steel separate. All of it goes to the smelter. One F-14 Tomcat yields about 12 tons of metal, enough to make 40,000 soda cans. Circle of materials. But not every plane stays here forever. Some come back to life. History's seen dozens of cases where an aircraft that slept 10 years in the desert took to the skies again. The most famous example? B-1 Lancers. In 2004, they were pulled from service and mothballed. 5 years later, the military realized they'd made a mistake. These machines were still needed. 18 airframes were brought back online. The restoration process took months. Engineers stripped protective coatings, checked every system, replaced all fluids, tested engines. Cost of restoration, $15 million per airframe. That's 10 times cheaper than building new. These B-1s flew combat missions again. Afghanistan, Syria, Iraq. Machines considered dead were dealing death once more. The Arizona desert proved to be better storage than any hangar. Dry air preserved the metal perfectly. Not a speck of rust after 10 years under open sky. $4,200 aircraft sit at the boneyard today. That's more than all the aviation museums in the world combined. This collection's worth over $35 billion. Around 300 new birds arrive every year, and roughly the same number leave. Some for parts, some for the smelter, some return to active duty. The base operates year-round, 365 days. No days off. A staff of 400 keeps this giant machinery of death and resurrection running. The economic impact is massive. Annual savings for the U.S. Air Force, over $1 billion. Money they don't have to spend on new parts. Foreign militaries come here like it's a marketplace. They buy whole aircraft for their museums or training. Australia bought 20 retired F-18 Hornets. Israel took several dozen helicopters. The boneyards become an international hub for trading aviation history. And so, beneath the scorching Arizona sun, ends the life of machines that once embodied power and technology. Each of these aircraft isn't just metal and electronics. These are the stories of pilots who trusted them with their lives. These are missions flown over Vietnam, Iraq, Afghanistan. These are technologies humanity spent decades developing and billions of dollars perfecting. There's no museum romance here. Here's the harsh truth. Every machine is mortal, even those that ruled the sky. But there's a certain justice in this. Aircraft don't rot in junkyards. They donate their organs to brothers still flying. They transform into materials for new technologies. Some resurrect for final combat missions. The aircraft boneyard isn't the end, it's transformation. From the ashes of old machines, new ones are born. And every time a fighter climbs into the sky with an engine stripped from a mothballed bird, somewhere in the desert a metal giant smirks. I'm still flying, just differently.
Every year, the world produces over 4 million tons of hollow structural sections, and that's just in the US. Picture this, that's enough to build 400 Eiffel Towers annually. But behind these massive numbers lies the silence of steel giants we never see, because they're hidden inside buildings, bridges, and machines. How does rusty scrap metal transform into tubes capable of supporting the weight of entire bridges and weathering the storms of time? And what secret makes them both lightweight and incredibly strong? Stick around till the end, and you'll discover a secret you never knew existed. The market for hollow structural sections, where our heavy wall tubing reigns supreme, is a massive chunk of America's steel industry. Every year, the country cranks out over 4 million tons of these tubes. That number is mind-blowing. To put it in perspective, the entire Eiffel Tower weighs about 10,000 tons of steel. That means in a single year, American mills produce enough square and rectangular tubing to build 400 Eiffel Towers. It's an entire forest of steel giants sprouting up annually. We just don't see it because it's hidden inside structures. Mountains of scrap metal, remnants of cars, construction frames, old machinery, sit waiting for their fiery rebirth. A giant crane with an electromagnet scoops up this metallic chunk and feeds it into an electric arc furnace.
Down there, in that roaring inferno where temperatures hit nearly 3,000 degrees Fahrenheit, this scrap metal transforms into a boiling, blinding lake of molten steel. Into this melt, like a chef adding spices, they introduce alloying elements, so the future pipe isn't just strong, it can withstand extreme loads and won't crack in freezing cold. Then this river of fire flows into a continuous casting machine, where it cools and solidifies, becoming long, massive steel billets. For our future pipe, these are typically thick, round slugs called blooms. Automatic cutters slice off pieces to the required length, and these hot but now solid cylinders are ready for the really interesting part. This is our blank, our solid chunk of metallic dough. But how do you make a hole in it when it's hard as rock?
To do this, it's sent to a heating furnace, where its temperature is brought back up to that perfect plastic state, 2,300 degrees Fahrenheit. And from there, glowing white hot with a blinding yellow radiance, it moves to the piercing mill. This is the heart of the entire process, and it's real industrial magic. Picture two massive barrel-like rolls spinning in the same direction. They're set at an angle to each other. The hot steel cylinder enters between them, and here's where something incredible happens. As they spin, the rolls don't just forcefully push the cylinder forward, they also make it rotate at a crazy speed. Because of this rotation and compression, enormous stresses build up right at the center of the metal cylinder, and the metal there literally loosens up, preparing to split. And at that exact moment, from the other side, a special piercing rod, or mandrel, is fed in to meet it. It plunges into that loosened center like a knife through butter, literally punching straight through the solid billet, transforming it into a thick walled tube. It's an incredible sight. A solid chunk of metal becomes hollow in mere seconds, all happening with a roar and grinding that shakes the ground. The piercing process was invented in the late 19th century by the Mannesmann brothers in Germany and remains the primary method for producing seamless tubes to this day. But now we've got a round tube, and we need a square one. Our hot, freshly pierced tube immediately moves to the next stage, the forming mill. This is a series of roller pairs, but these ones aren't round.
They have special grooves whose shape gradually transitions from round to square. The tube flies into the first pair of rollers, which squeeze it slightly from the sides.
Then it rotates 90 degrees and enters the next pair, which squeezes it from different sides. And so, step by step, passing through several of these gates, our round tube transforms right before your eyes into a perfectly square one. It's like a skilled sculptor, gradually, blow by blow, giving stone its desired shape. The final finishing rolls calibrate the tube with incredible precision, guaranteeing that all its walls have uniform thickness and all corners are perfectly square. The standard sizes are impressive. There are tubes with cross-sections of 500 by 500 millimeters. That's about 20 inches wide, and the wall thickness on these monsters can easily exceed 25 millimeters. Picture a steel wall as thick as a big encyclopedia. The weight of such a tube is simply colossal.
A single yard of this pipe can weigh over 800 pounds. That's like having 4 grown men standing on every yard of its length. And a standard 40-foot section? That'll clock in at over 10,000 pounds, the weight of 2 full-size SUVs, like a Range Rover. And that's just one piece. But here's the thing. Their real genius isn't the weight itself, but how intelligently it's distributed. That's their superpower. Picture a solid steel bar and a hollow pipe of the same weight. The pipe will be way more resistant to bending and twisting. Why? Because all the material sits on the outside, as far from the center as possible, and that's exactly where the greatest stress is hit under load. The hollow core? It just saves weight. Same principle as bird bones, hollow but incredibly strong.
That's why hollow profiles have the highest strength-to-weight ratio of any structural steel shape. This makes them the perfect choice when you need maximum rigidity without extra tons, in crane booms, heavy equipment frames, bridge trusses, and even roller coaster structures. It's because of these tubes that modern skyscrapers can withstand hurricane-force winds, and bridge structures last for decades, carrying millions of tons of cargo. From the final roller, a long, red-hot, now square tube emerges. It travels along a roller conveyor to a cooling table, where it slowly cools down, gaining its final, rock-solid strength. During cooling, the metal can warp slightly, so each tube is run through a straightening machine, a system of rollers that straightens it to perfectly linear precision.
Now we've got a perfect, strong, but really long pipe. Time for the final operations. A massive saw roars to life and cuts it into standard lengths, say 20 or 40 feet. Each section goes through strict quality control. Specialists check its geometry, wall thickness, angle precision. Then they X-ray it with ultrasound to make sure there aren't any hidden internal defects. Modern flaw detectors can spot micro cracks smaller than a millimeter, invisible to the naked eye. Only then does the pipe get marked with all its info: steel grade, dimensions, batch number, production date. The finished, inspected pipes get bundled by robotic cranes, strapped down with heavy steel bands, and shipped off to the warehouse.
And just like that, traveling from rusty scrap metal through the fiery heart of the furnace, surviving brutal piercing and precise forming, this humble yet incredibly strong steel rectangle emerges, ready to become the silent but reliable backbone for humanity's most ambitious creations. From the skyscrapers of Dubai to the bridges of San Francisco, from oil rigs in the North Sea to the frameworks of space launch pads, everywhere these unsung heroes of modern civilization are hard at work. They don't demand applause, they don't seek recognition, but it's on their steel shoulders that our world stands. And now you know their story, from fire to structure, from the chaos of scrap metal to the mathematical precision of engineering calculations. This is the real magic of industry. Right now, 430 nuclear reactors are running on this planet. They light up cities, power factories, move aircraft carriers. But at the heart of every single one, a metal that can ignite a city or wipe it off the map: uranium. Just 1 kilogram of enriched uranium holds the energy of 2 million kilograms of coal. But how does this deadly element transform from gray ore into a gleaming fuel rod? You'll find out why miners wear dosimeters even in the shower, how centrifuges spin faster than a bullet, and what happens when a single uranium atom splits in two. Stick around to the end, because the finale shows how humanity tamed the power of the stars.
The story of uranium began long before the atomic age. In 1789, German chemist Martin Klaproth isolated a strange heavy metal from a mineral and named it after the planet Uranus, discovered just a few years earlier. Back then, nobody knew that this silvery gray element would become the most dangerous and most valuable material of the 20th century. In the 19th century, uranium was used to dye glass bright yellow and green colors. Uranium glass glowed under ultraviolet light and was considered a fashionable decoration. People didn't even suspect they were holding a potential bomb in their hands. Everything changed in 1938 when Otto Hahn and Fritz Strassmann discovered uranium nuclear fission. It turned out that a single uranium-235 atom, after absorbing a neutron, splits into two parts, releasing enormous energy and new neutrons. These neutrons can split the next atoms. That's how a chain reaction begins.
The world realized uranium isn't just a metal, it's the key to unprecedented power. The uranium race was on. The Manhattan Project in the US, Soviet programs, British developments, everyone was hunting for uranium deposits. And they found them. The largest uranium mines are located in Kazakhstan, Canada, Australia, and Namibia. Kazakhstan is the absolute leader, producing about 40% of the world's uranium. Canadian mines in the Athabasca Basin contain some of the richest uranium ores on the planet, up to 20% uranium versus the typical 0.2%. Australia's Olympic Dam deposit is so massive that its reserves are estimated in the millions of tons. And in Namibia, the Rossing uranium mine is one of the world's largest open-pit operations, where giant excavators work around the clock. Every year, the world mines about 53,000 tons of uranium. Sounds like a lot, but uranium is actually a rare element.
In Earth's crust, there's just 2.8 parts per million, 1,000 times less than zinc and 40 times less than lead. Uranium mining starts deep underground, or on the surface of massive open pits. Underground mines plunge down to nearly a mile deep. Eternal darkness reigns here, sliced by beams from headlamps on miners' helmets. The air is heavy, humid, saturated with the smell of explosives and dust. Temperatures hit 104 degrees. At this depth, the rock heats up from Earth's core. Miners drill holes into the uranium vein, pack in explosives, and retreat to a safe distance. The blast roars like underground thunder, and tons of rock come crashing down. Massive loaders with wheels as tall as a person scoop up the debris and haul it to the mine shafts. Uranium ore isn't pure uranium. It's rock containing just 0.1 to 20.
The rest is waste rock. But even that tiny fraction makes every stone radioactive. The dosimeters on miners' belts click constantly, measuring radiation levels. Each worker gets a strictly limited radiation dose per year. Go over the limit, you're headed home until next season. At the surface, they load the ore into dump trucks and haul it to the processing plant. That's where the first stage of turning rock into fuel begins. They crush the ore in giant mills, where steel balls the size of watermelons grind the rocks into fine dust. This dust gets mixed with sulfuric acid. Chemical leaching starts. The acid dissolves the uranium oxide, leaving the waste rock untouched. What you get is a yellow-green liquid that looks like poisonous soup. They filter it, purify it, evaporate it, and what comes out is a bright yellow powder they call yellow cake. It's uranium concentrate, containing up to 80% uranium oxide.
Yellow cake gets packed into steel drums, 440 pounds each, and shipped to a conversion facility. But this uranium isn't reactor-ready yet. The problem? Natural uranium is made of two isotopes, uranium-238, 99.3%, and uranium-235, just 0.7%. Only uranium-235 can sustain a chain reaction. So the uranium needs to be enriched, boosting the uranium-235 share to 3 to 5% for reactors, or up to 90% for weapons. At the conversion facility, yellow cake gets turned into a gas, uranium hexafluoride. This gas is poisonous, corrosive, and radioactive all at once. At room temperature, it's solid, like ice, but heat it to 133 degrees Fahrenheit and it turns straight into gas, skipping the liquid phase entirely. Uranium hexafluoride gets pumped into steel cylinders and trucked to an enrichment plant.
Here's where the most technologically complex stage begins: isotope separation. Uranium-235 and uranium-238 are chemically identical, but differ in mass by just 3 neutrons. How do you separate things that are almost the same? Gas centrifuge method. Picture a massive hall the size of a football field, packed with thousands of vertical metal tubes about 6 feet tall. These are centrifuges. Each one spins at speeds up to 100,000 revolutions per minute, faster than a speeding bullet. Uranium hexafluoride gets fed into the centrifuge, and under monstrous centrifugal force, the heavier uranium-238 gets thrown toward the walls, while the lighter uranium-235 concentrates in the center. The difference is microscopic, just 1% per pass. That's why the gas runs through thousands of centrifuges, connected in cascades. Each successive centrifuge receives slightly more enriched uranium than the one before.
The process takes months. Eventually, you get enriched uranium hexafluoride with uranium-235 content ranging from 3 to 5%. That's enough for a nuclear power plant. If you keep enriching it up to 90%, you get weapons-grade uranium. That's exactly why enrichment facilities are guarded better than fortresses. The enriched uranium hexafluoride is transported back to a facility where it's converted from gas into solid uranium oxide, a dark gray ceramic powder. This powder is pressed into small cylindrical pellets, about the size of a fingertip. Each pellet weighs around 7 grams, but contains energy equivalent to 400 kilograms of coal or 3 barrels of oil. The pellets are sintered in furnaces at temperatures of 1700 degrees Celsius. They become hard as diamond and develop a distinctive metallic luster.
Now these pellets need to be turned into fuel rods. They're loaded into long, thin tubes made from a zirconium alloy, a material that doesn't absorb neutrons and can withstand the extreme temperatures and pressures inside a reactor. Each tube is about 13 feet long and holds several hundred pellets. The tubes are hermetically sealed and assembled into bundles, fuel assemblies. A single assembly contains anywhere from 100 to 300 rods, held together in a unified structure with gaps for water circulation. One fuel assembly weighs up to 1,500 pounds. The finished fuel assemblies are shipped to nuclear power plants. Here, they're loaded into the reactor core, a massive pressurized steel vessel surrounded by walls of concrete and steel over 3 feet thick. When the rods are lowered into the reactor and the chain reaction begins, temperatures inside reach about 570 degrees Fahrenheit.
Neutrons tear through the reactor core, slam into uranium-235 atoms, split them apart, and each split unleashes massive energy. That energy heats water into steam. Steam spins turbines, turbines drive generators, and generators produce electricity that lights up millions of homes. A single fuel rod runs in the reactor for 3 to 6 years. During that time, it cranks out as much energy as an entire freight train loaded with coal or a tanker full of oil. But gradually, the uranium-235 burns out, and fission products pile up, radioactive isotopes that poison the reaction. The rod gets pulled from the reactor and dropped into a spent fuel pool, a massive tank of water 40 feet deep. Water cools the rods and absorbs the radiation. They'll sit here for years, cooling down and losing activity before they're shipped off for reprocessing or burial.
The entire journey of uranium, from a dark mine deep in the earth to a glowing reactor, is a story about how humanity learned to extract energy from the very heart of matter. From explosions in mine shafts to spinning centrifuges, from ceramic pellets to fuel assemblies, every stage demands precision, technology, and control. Uranium isn't just a metal. It's a bridge between the past, when we burned wood, and the future, when we might master nuclear fusion. Today, nuclear power provides about 10% of the world's electricity. That means every 10th light bulb on the planet shines because of uranium. But it's also a metal capable of destroying civilization in minutes. And as long as humanity holds this balance between creation and destruction, between light and darkness, we continue to exist. Uranium gave us incredible power, and now our job is not to abuse it.
Ever wonder how you make a material just 6 microns thick? That's 15 times thinner than a human hair. So thin that if you hold it up to the light, you can read a newspaper through it. So fragile that one wrong move and it tears. Yet so strong it can withstand temperatures of 570 degrees Fahrenheit and protect your food from light, oxygen, and bacteria better than any plastic. I'm standing at the gates of the Eurofoil plant in Dudelange, Luxembourg, one of the largest aluminum foil manufacturers in Europe. Here, across 50 acres, 100 tons of foil are born every single day. That's over 600 million feet, a ribbon you could wrap around the Earth 5 times at the equator. The air is thick with the smell of hot metal and machine oil. The roar of the rolling mills is so powerful the ground vibrates beneath your feet. Welcome to the place where aluminum makes the journey from crude ingot to an almost invisible film. This isn't just a factory, this is a laboratory of precision at the edge of what's physically possible. The process begins in the foundry where real metallic hell reigns. 4 continuous casting machines run non-stop 24 hours a day, 365 days a year. I put on protective goggles with dark filters. Without them, looking at molten aluminum is just dangerous. The temperature here stays at 1330 degrees Fahrenheit. This is the melting furnace where they load aluminum ingots, massive bars weighing 55 pounds each. But Eurofoil prides itself on being eco-friendly. 70% of the raw material here is recycled aluminum. Foil scraps, production waste, even old soda cans, everything gets used. Aluminum can be melted down infinitely and it doesn't lose its properties. Jean-Pierre, the plant's head metallurgist, shouts in my ear. We're standing on a platform above the furnace, and the heat is so intense that the skin on my face starts tingling. In the enormous crucible, a silvery liquid churns, molten aluminum. But this isn't just pure metal, it's an alloy. Depending on the intended purpose of the future foil, they add magnesium, manganese, silicon. For food-grade foil, alloy 8011. For technical foil, alloy 8079. Each percentage of additive changes the properties: strength, plasticity, corrosion resistance. From the furnace, molten metal flows into the casting machine, a 100-foot-long monster. Here's where the magic happens. Liquid metal at 1300 degrees turns solid in seconds. This is continuous casting. Molten aluminum pours between 2 rotating water-cooled rolls, 6 feet across. Inside those rolls, water circulates at 150 pounds per square inch. When scorching aluminum hits cold steel, instant crystallization. The sound? Like dumping a bucket of water on a blazing stovetop. Hissing, crackling, clouds of steam. Out from under the rolls comes an aluminum ribbon, 1/3 of an inch thick, 5 feet wide. It's still glowing dull red, around 750 degrees. The ribbon crawls forward at 10 feet per minute, slowly cooling in the open air. I step closer and watch as a distinctive pattern emerges across the metal surface. That's the crystalline structure of aluminum. Metallurgists call this grain. Everything depends on the size and shape of those grains, how well the foil will stretch, whether it'll tear during winding, how it'll behave under heat. The perfect grain is a labyrinth, Jean-Pierre explains. The crystals need to interlock with each other, creating a strong network. If the grain's too coarse, the metal becomes brittle. Too fine, it loses flexibility. The cooled strip winds into giant coils weighing 12 tons each. These are blanks for the next stage, hot rolling. We move to the adjacent shop, where rolling mills stand as tall as a 2-story building. Here they start rolling the aluminum strip like dough, except instead of a rolling pin, 50-ton steel rollers, and instead of a table, an alloyed steel frame 3 feet thick. They feed the coil into the mill. The rollers spin, grip the strip, and pull it through with monstrous force. Pressure hits 1,200 tons per square meter. The metal resists, springs back, but gradually gives in. After the first pass, thickness drops from 8 millimeters to 4. After the second, down to 2. Speed builds. If at first the strip crawled at 5 meters per minute, after the third pass it's flying at 300 meters per minute. Air whistles. The strip hums like a taut string. Each pass generates massive heat. Metal grinding against steel heats the strip to 250 degrees, so the rollers get continuous cooling emulsion, a water oil mix. It sprays at 30 atmospheres of pressure, forming a white cloud of mist through which the strip shoots like silver lightning. After hot rolling, the strip, now 0.12 inches thick, heads to annealing. This step is critical. Here's why. During rolling, aluminum work hardens. It gets tough and brittle. The metal's crystal lattice deforms. Internal stresses build up. Keep rolling without annealing? The strip just tears. The annealing furnace is a tunnel 260 feet long. The strip travels through at 33 feet per minute. Inside, the temperature hits 930 degrees Fahrenheit in a nitrogen atmosphere. Oxygen is completely excluded. Otherwise, the aluminum oxidizes and gets covered in loose black scale. At that temperature, recrystallization happens. The metal's deformed grains heal. Internal stresses release. The aluminum goes soft and ductile again. This process takes 2 hours. Coming out of the furnace, the strip cools in a water bath, then gets dried with hot air. Now it's ready for the most demanding stage, cold rolling to final thickness. The cold rolling mill, that's the heart of the factory. 3 state-of-the-art rolling stands here, capable of rolling aluminum down to 6 microns thick. That's the limit. Any thinner? Physically impossible without tearing. The process takes 20 passes. Each pass reduces thickness by roughly 30%. 0.12 inches becomes 0.08, then 0.06, then 0.04, and so on, until you hit 0.0024 inches, 6 microns. Rolling speed on the final passes? 67 miles per hour. The foil ribbon flies faster than a car on the highway. The slightest vibration, the tiniest roller deviation, and it tears. A tear at that speed means shutting down the entire line, losing several tons of material and hours of rethreading. That's why laser thickness gauges are installed here, measuring the strip 200 times per second, accurate to 0.4 microns. The computer instantly corrects roller pressure, rolling speed, coolant flow. A human? couldn't react fast enough. I'm watching the monitor in the control room. The thickness graph runs flat, 6.0 microns, 6.1, 6.0. Deviation within plus or minus 0.8 microns. That's perfection. But there's a problem. You can't roll foil 6 microns thick in a single pass. It sticks to itself, tears, crumples. So they use a clever trick, doubling. 2 layers of foil, each 12 microns thick, are stacked together and rolled as one. The rollers press down, and both layers simultaneously thin to 6 microns. But between them remains the thinnest air gap. After rolling, the layers are separated. And here's where an interesting effect shows up. One side of the foil, the one that contacted the roller, comes out shiny, mirror-like. The other side, which contacted the neighboring foil layer, stays matte. You've probably noticed this on kitchen foil. Well, it's not a defect and not a special coating. It's the trace of the doubling process. The matte side is the imprint of the microtexture from the adjacent sheet. At the molecular level, it's covered with microscopic irregularities that scatter light. The finished foil gets wound onto huge jumbo rolls, 6.5 feet across and weighing 3 tons. These are the mother rolls. From them, they'll later cut foil to the needed width. For chocolate wrapping, 12 inches; for yogurt lids, 2 inches; for industrial uses, 4 feet. Quality control at Eurofoil borders on paranoia. And that's a good thing. Every jumbo roll goes through a dozen tests. First up, backlighting. The foil passes in front of a powerful lamp. Any microcrack, any pore, and light will shine through. A computer flags the defect, and that section gets marked as scrap. Second, leak testing. A foil sample gets clamped between 2 chambers. Helium under pressure is fed into one. A highly sensitive detector sits in the other. If even a single helium molecule seeps through the foil, test failed. Third, mechanical testing. The foil is stretched on a specialized machine, measuring tensile strength. Quality foil must withstand a load of at least 15 megapascals. That's roughly 330 pounds per square inch. For a material 6 microns thick, that's a phenomenal number. Fourth, chemical analysis. Every 2 hours, they take a sample and run it through a spectrometer. It shows the exact alloy composition down to hundredths of a percent. Any deviation, and the batch goes back to the smelter. Fifth, corrosion testing. A sample is held in salt fog at 95 degrees Fahrenheit for 72 hours, simulating 3 years of use. If corrosion shows up, it's scrap. The final stage, slitting and packaging. Jumbo rolls feed into slitter rewinders. Disc blades made from hardened steel, sharpened to razor-edge sharpness, cut the 10-foot wide web into narrow strips of the required width. Slitting speed, 1,600 feet per minute. Blades spin at 3,000 revolutions per minute. The slightest wobble, and the foil edge comes out ragged, jagged. That's why blades get swapped every 8 hours. Slit rolls move to winding. Here the foil winds onto cardboard cores 3 inches in diameter. For household foil, the standard, 33 feet per roll. For the food industry, rolls of 1,000 feet, 1,600 feet, 3,000 feet. An automatic system measures the required length, cuts, seals the edge, marks the roll with a barcode. Output, 200 rolls per minute. Finished rolls get packed into cardboard boxes, boxes loaded onto pallets, pallets hauled to the warehouse. From here, Eurofoil foil ships to 70 countries worldwide. To Germany for chocolate wrapping, to France for cheese factories, to Italy for coffee capsules, to Switzerland for pharmaceutical blister packs, to Japan for electrolytic capacitors. I'm standing in a finished goods warehouse. Around me, stacks of pallets tower 13 feet high. Each pallet holds 2,000 rolls of household foil or 50 jumbo rolls of industrial grade. The product stored here is worth around 5 million euros. The plant runs at full capacity, 100 tons of foil per day, 3,000 tons per month, 36,000 tons per year. That's enough material to wrap the entire United Kingdom in a continuous sheet, or package 15 billion chocolate bars, or make 300 billion yogurt lids. This entire foil empire was born from a simple piece of aluminum that passed through the inferno of casting furnaces, the monstrous pressure of rolling mills, the precision of laser measurements, and rigorous quality control. From 8 millimeters down to 6 microns, a journey 1,300 times over. If you found it interesting to learn how a material thinner than a human hair but stronger than many plastics is created, hit the like button on this video. Write in the comments whether you knew that aluminum foil can be recycled infinitely. And subscribe to the channel to keep discovering the technologies that surround us every day but remain invisible. What if I told you there's a metal that flows like water at room temperature, killed thousands of workers during the colonial era, and without which gold mining would be impossible? A metal that vaporizes at 1100 degrees Fahrenheit and condenses back into liquid silver? Every year, the world produces around 1,300 tons of mercury, but that's nothing compared to historical scales. Over the last 500 years, humanity has extracted about 1 million tons of mercury from the Earth's depths. Half of that million was used before 1925. Mercury is obtained from red ore, cinnabar, by heating it to 900 to 1100 degrees Fahrenheit. During this process, mercury sulfide breaks down, releasing mercury vapors and sulfur dioxide gas. China dominates production, 95% of the world's mercury. In 2022, China produced 2,000 tons of mercury. A standard flask holds 76 pounds of mercury. These were the exact flasks used to ship it to gold mines during the gold rush. Stick around till the end. You'll discover a secret that even those who work with this metal won't talk about. Picture an underground mine somewhere in China, Kyrgyzstan, or Mexico, the world's biggest mercury producers. Deep beneath the surface, in the dim glow of miners' lamps, red streaks appear in the rock. This is cinnabar, mercury sulfide, a bright red mineral that humanity has known for thousands of years. The ancient Romans mined it both as a pigment and for mercury. The ancient Egyptians were using mercury as far back as 1500 BC. Greek philosopher Aristotle in 350 BC described how cinnabar was heated to extract mercury for religious ceremonies. Cinnabar forms in veins associated with volcanic activity and hot springs. About 90% of deposits require underground mining with tunnels. The remaining 10% can be extracted through open-pit methods. Cinnabar is separated from the surrounding rock through drilling and blasting or using powerful machinery. The ore is hauled out of the mine on conveyor belts or in trucks. Because cinnabar is a relatively concentrated ore, it can be processed directly without intermediate steps to remove waste rock. The ore is first crushed in one or more cone crushers. A cone crusher consists of an inner cone rotating on an eccentric vertical axis inside a stationary outer cone. When ore is fed into the top of the crusher, it gets squeezed between the two cones and breaks into smaller pieces. For concentrating low-grade cinnabar with a specific gravity of 8 to 8.2, gravity and flotation methods are used. Grinding to -48 mesh is the economically viable liberation point for the mineral. Some operations use mineral jigs to recover coarse heavy mineral and any metallic mercury that might be present in the ore. Flotation with one or more cleaning stages is used to produce a high-grade concentrate. It's not uncommon to obtain concentrates containing 40 to 50% mercury from ores containing 5 to 15 pounds of metal per ton. The concentration ratio is therefore high. The dewatered concentrate from flotation is combined and stored for roasting and recovery of metallic mercury. Now comes the most critical and dangerous stage, roasting. Cinnabar concentrate gets loaded into specialized furnaces. These can be multi-hearth furnaces, where ore mechanically moves down through a vertical shaft from one level to another via slowly rotating rakes. Or rotary kilns, where ore tumbles along the length of a long rotating cylinder, tilted a few degrees from horizontal. Either way, heat comes from burning natural gas or other fuel at the bottom of the furnace. Heated cinnabar reacts with oxygen in the air at temperatures ranging from 930 to 1,110 degrees Fahrenheit. A chemical reaction occurs. Mercury sulfide breaks down into sulfur dioxide gas and mercury vapor. Mercury rises as vapor. This is called roasting. Mercury vapors rise upward and exit the furnace along with sulfur dioxide, water vapor, and other combustion products. Significant amounts of fine dust from the crushed ore also get carried away and must be separated and captured. Next comes condensation. Hot gases containing mercury vapor pass through a cooling system. A condensation column is used, a special device where the vapors cool down and mercury condenses back into liquid metal. Pure mercury separates from sulfur in this process and evaporates easily. The condensation column collects the liquid metal. Thanks to mercury's high specific gravity, impurities gather on the surface and can be easily removed. The liquid mercury gets poured into standard iron flasks. Each flask holds 76 pounds of mercury. That's the standard unit of sale. These exact flasks shipped mercury to gold mines during the gold rush in California and Nevada in the 18th and 19th centuries. The process is simple in essence, with one drawback: toxic fumes. If roasting is done incorrectly, mercury vapors, which are highly toxic, can get released into the atmosphere. This was catastrophic for workers in the colonial era. The history of mercury production is full of tragedies. In 1564, cinnabar mining began in Huancavelica, Peru. With a local source of mercury, the amalgamation process was adopted for refining silver in Potosi, Bolivia, in the early 1570s. As a result, massive quantities of mercury were released into the environment. Between 1564 and 1810, approximately 17,000 tons of mercury vapor were released into the atmosphere in Huancavelica and 39,000 tons in Potosi. In 1604, an advocate for indigenous people described how fumes, dust, and candle smoke in the mine caused coughing and Huancavelica disease, and argued that forcing people to work in mercury mines meant sending them to a slaughterhouse. In 1630, a contemporary described the mines as a living image of death and a dark shadow of hell. The Jesuit José de Acosta, around 1590, wrote about the roasting process. If the smoke or fumes reach the people opening the pots, they get mercury poisoning and die, or are left in very poor condition or lose their teeth. The largest mercury deposit in history? Almaden in Spain. It was worked from Roman times until 1989, the world's biggest producer. In 2000, Almaden yielded 236 tons of mercury. Other major deposits: Khyder Khan in Kyrgyzstan, 550 tons, Algeria, 240 tons. During World War II, mercury production was critical. Mercury fulminate was essential for bullet primers, and the biggest producing region in Spain was under dictator Franco's control. The US ramped up domestic production from 1941 to 1944. The price per flask during the war years averaged around $380 in 1960 prices. Today, global mercury production has plummeted. In 2016, they produced 4,500 tons, but in 2023, just 1,200 tons. China dominates with 95% of world production, 1,000 tons in 2023. Mercury has diverse applications, but its use is declining due to toxicity. Mercury easily forms amalgams with other metals, making it useful for extracting gold and silver. Much of the incentive to develop mercury deposits in the United States arose after the discovery of gold and silver in California and other western states in 1800. When mercury mixes with gold slurry, it triggers a reaction that separates gold from ore. This amalgam is then heated to vaporize the mercury and leave behind gold nuggets. Artisanal and small-scale gold mining is the largest source of anthropogenic mercury emissions, accounting for 38% of global releases. Other applications include chlorine and caustic soda production in mercury cell electrolysis plants. Until recently, this was a major consumer. In 2023, only one such facility was operating in the U.S. electrical devices, fluorescent and mercury vapor lamps, mercury batteries, switches, and relays. Measuring instruments, thermometers, barometers, pressure gauges. Dental amalgam, a mixture of mercury with silver and other metals for fillings. But because of its high toxicity, mercury use has dropped sharply over the last 20 years. Inhaling mercury vapor is especially dangerous for the kidneys, central nervous system, respiratory and cardiovascular systems. Inhaling mercury vapor also causes neurobehavioral disorders like hand tremors and mental impairment. Exposure to other forms of mercury, particularly methylmercury, which accumulates in fish, can also lead to kidney problems, lung issues, and central nervous system damage, as well as arthritis, reproductive problems, memory loss, psychosis, and in some cases, death. The United States banned the export of elemental mercury on January 1, 2013, under the Mercury Export Ban Act of 2008. Global mercury resources are estimated at around 600,000 tons, mostly in China, Kyrgyzstan, Mexico, Peru, Russia, Slovenia, Spain, and Ukraine. And so, having traveled from red cinnabar ore through roasting at 1100 degrees Fahrenheit, through evaporation and condensation, through the tragedies of thousands of workers in the colonial era, through the gold rush and world wars, emerges a liquid metal that flows at room temperature, without which gold mining would be impossible, but which has killed more people than any other metal in human history.
Every hour across the globe, dozens of nuclear reactions, but only a handful know that at the heart of every atomic bomb lies a material capable of destroying a city in seconds. This isn't just a weapon, it's a miniature star, crafted by human hands. You'll discover how ordinary uranium births an explosion with the force of 1,000 suns, why sand in New Mexico turned to glass, and what happened to an island that no longer exists. And most importantly, what secret hides inside a nuclear warhead? Watch until the end, because the finale will change how you see the modern world. Back in the day, when the world was just learning to hear the voice of the atom, a few curious minds peered inside the invisible, into the heart of matter. Those were the years when science was feeling its way forward, but with great determination. German chemist Otto Hahn, along with Fritz Strassmann, like alchemists of a new world, discovered that uranium could split. It was as if ice cracked on a river, behind which a giant lay sleeping.
While Europe prepared for war, a group of people secretly gathered across the ocean, later to be called the Masters of Atomic Fire. In the New Mexico desert, the Manhattan Project began. Ordinary physicists, Oppenheimer, Fermi, Teller, became the creators of the greatest force humanity had ever seen. In the summer of 1945, beneath the clouds of dawn, the first nuclear bomb exploded. Sand turned to glass, sky to fire. And in the absolute silence, one scientist whispered, "Now I am become death, the destroyer of worlds."
But the story didn't end there. Days later, Hiroshima and Nagasaki became pages of grief. And just when the world thought it had seen everything, the USSR answered. Under Igor Kurchatov's leadership in 1949, the first Soviet atomic bomb detonated. A decade later, the Tsar Bomba. Its power could level a city the size of Paris. History's irony. Nuclear weapons became not a sword, but a shield. Their existence forced enemies to talk. Ideas of security, control, diplomacy became more important than warfare. For the first time, humanity faced massive questions. Can we negotiate so everyone survives? That's how deterrence doctrine was born. Don't attack, because you know attacking means catastrophe. And while this balance is far from perfect, it's delivered decades without global war between superpowers. An entire era. Cold, anxious, but without mass battlefronts.
Nuclear research sparked whole new industries: nuclear power, reactors on submarines, medical diagnostics. Even space projects got a boost from understanding the atom. To create the most terrifying thing, we learned to grasp the most complex. Yes, nuclear weapons are dangerous, but they're also a mirror of human wisdom. We built something incredibly powerful and chose not to use it on a massive scale. This is a story about power we decided to restrain, about science that taught us not to dominate, but to coexist. Deep in laboratories, where lamplight dimly illuminates blueprints, the path to building a nuclear bomb begins. This isn't just assembling metal, it's modern-day alchemy, where every gram of material holds the power of 1,000 suns. It all starts with uranium or plutonium, isotopes capable of sustaining a chain reaction.
But natural uranium is mostly uranium-238, which won't work, so they enrich it, separating out the 235 isotope using centrifuges, where gaseous uranium spins at insane speeds. Plutonium is artificial. It's produced in nuclear reactors, where uranium absorbs neutrons and transforms into plutonium, the stuff you need for a nuclear bomb. The appearance of a nuclear bomb often resembles a classic aircraft bomb, a streamlined metal casing engineered for stable descent from high altitude. In a massive hangar where the walls ring with the echo of metal, the air smells of hot steel and oil. Here begins the birth of the shell that must contain the heart of an atomic explosion. From the glowing throat of an industrial furnace flows a stream of metal, special steel, reinforced with nickel, chromium, and manganese. Its temperature exceeds 1,000 degrees. Summer sunlight looks pale compared to this fire.
Masters in protective suits with transparent face shields watch the forming process. Steel sheets bend into streamlined shapes under presses exerting hundreds of tons of force. Before their eyes, an elongated body takes shape, resembling a water droplet frozen under the pressure of the heavens. Next, mechanical arms mill the internal partitions, cut openings for tail stabilizers and locking mechanisms. Every fraction of an inch, the result of meticulous calculation, because balance during descent depends on it. After this, the casing undergoes a strengthening ritual, immersion in an anti-corrosion bath, treatment with polymer coating, application of matte paint. The color? Dark green, like a military shadow in the twilight of pine trees. And finally, testing. They drop it from height, strike it with hammers, spin it in a wind tunnel. Only after passing all trials is the casing ready to receive its lethal payload.
A quiet lab, half light, a faint smell of ozone, something heavy hangs in the air. In front of you lies an open nuclear bomb, its metal casing removed, its insides, like an organism, laid bare. There's nothing extra here, no shine, no decoration, just function, just explosion. At the center, a smooth, perfect sphere. It looks like a dull meteorite. This is the nuclear core. Plutonium-239, cold and deadly, or uranium-235, heavy as a planet in your palm. Its shape, mathematical perfection, polished down to microns. Around the sphere, an entire symphony of pressure. Composite explosives, layer upon layer, like a flower turned inside out. Their job isn't simply to detonate, but to force the explosion inward. Like hands clenching to the limit, these explosive lenses must create implosion, uniform, merciless compression that drives the material supercritical.
If even 1 second lags, the whole contraption becomes a heap of meaningless metal. And at the very heart of this implosion orchestra, the initiator, a tiny device waiting for its moment to release the first neutrons. Polonium and beryllium interact, creating a minuscule storm capable of triggering the irreversible. That's where the chain reaction begins, a match to an atomic forest. Then, the tamper layer. Heavy as a shadow, it wraps the bomb's core not for protection, but for containment. Uranium-238 or tungsten, not active, but absolutely critical. Their job? Delay the neutrons, force them back like an echo in a cave. Everything depends on this. The duration of the blast, its power, its climax. In the tail section, the brain. Automation, electronics, wires and sensors. Barometers waiting for altitude, radars tracking the ground, batteries sleeping, ready to wake. This is where it's all decided, when everything happens, above the city, in the air, after the drop. Without this nervous system, the blast would be an accident. But here, it's a calculation. If you look at the entire structure in cross-section, it resembles the layers of a planet, like chapters in an encyclopedia of force. The outer shell, smooth and cold. The explosive layer, mathematically arranged. The tamper, an invisible guardian. The core, like a seed of what's to come. And at the very center, a spark, sleeping until awakened. Over 62 years, the world witnessed 2,065 nuclear explosions. 5,224, that's not the number of nuclear explosions, but an approximate estimate of the entire U.S. arsenal, including active, reserve, and decommissioned warheads. Now, the number of nuclear tests that the United States conducted from 1945 to 1992 totals 1,154 detonations.
Each one is a separate page in the history of power, fear, and science. The first blast, Trinity, July 16, 1945, in the New Mexico desert. It was the beginning of an era when atomic energy became a weapon. Then came Hiroshima and Nagasaki, the only instances of nuclear weapons used in combat. In the decades that followed, the U.S. tested bombs at Enuatak and Bikini atolls, in Nevada, underground, in the atmosphere, over water. The blasts had different purposes, testing new designs, demonstrating power, studying effects on equipment and living organisms. Yield varied, from a few kilotons to 15 megatons, like in the Castle Bravo test of 1954. In 1952, the U.S. conducted its first thermonuclear test, Ivy Mike. This wasn't just a bomb anymore,
but a miniature star created by humans. The explosion wiped out an entire island. In the 1960s, testing became routine. The US tested warheads for missiles, aerial bombs, even neutron charges that had minimal blast waves but maximum radiation. The last official detonation happened on September 23, 1992, after which the US declared a moratorium, but the arsenal remained. It gets modernized, adapted, stored. Some warheads are on submarines, some on strategic bombers, some in NATO storage facilities. These explosions aren't just technical events. This is a story about how humanity learned to control the energy of stars and put it in the service of fear. But it's also a reminder that the power capable of destroying civilization sits under the control of those who understand the price of using it. And as long as this balance holds, the world continues to exist on the edge of the abyss, but doesn't fall in.
Today we're going on an incredible journey. From massive crankshafts that power ocean vessels to precision railroad components that keep millions of passengers safe. Settle in and let's dive into the mesmerizing world of industrial manufacturing. Here we're witnessing something truly impressive, the machining of a massive marine crankshaft weighing over 15 tons. This isn't your typical workshop project. These crankshafts are the beating heart of container ships and cruise liners, converting the explosive power of diesel engines into rotational motion that propels these ocean giants across our seas. The star of the show, a revolutionary vertical boring mill. Rising nearly 3 stories tall, this engineering marvel features a 20-foot diameter faceplate capable of machining parts up to 65 feet long. The machine's spindle delivers an impressive 1,600 horsepower while maintaining accuracy tolerances of just 4/10,000ths of an inch. That's thinner than a human hair. An advanced computer numerical control system coordinates up to 12 simultaneous axes, ensuring every cut is executed with mathematical precision. Watch as the massive crankshaft rotates at a carefully controlled speed of 15 revolutions per minute. Carbide cutting tools, each costing more than a luxury car, slice through hardened steel like butter. The cooling system pumps 500 gallons per minute of specialized cutting fluid, preventing thermal distortion while washing away chips that look more like metal ribbons. Notice how the operator monitors vibration sensors and thermal cameras. At this scale, even tiny deviations can spell disaster. The real magic happens during the finishing passes. Using diamond-tipped tools, surface finish reaches an incredible 0.4 microns, smoother than a mirror. Laser measurement systems continuously verify dimensions, while ultrasonic testing ensures the internal structure remains intact. This single crankshaft will operate for decades, generating millions of horsepower cycles. It's a testament to German engineering precision that transforms raw steel into a mechanical masterpiece worth over $500,000. Welcome to where they've redefined what heavy-duty really means. This isn't just another CNC lathe. This is a mechanical monster engineered to tackle the roughest, toughest machining jobs in heavy industry. When aerospace manufacturers need to machine titanium landing gear components, or when power plants require custom turbine shafts, this is where they turn. This beast can handle parts up to 5 feet in diameter and 40 feet long, weighing up to 25 tons. The main spindle generates 400 horsepower through a precision planetary gearbox, delivering massive torque at low speeds. Watch the machine attack this massive steel workpiece with aggressive roughing cuts. The cutting parameters are mind-blowing. Depth of cut just over ½ an inch, feed rate around a 32nd of an inch per revolution, removing over 200 cubic inches of material per minute. High-pressure coolant jets at 1,000 pounds per square inch blast away continuous ribbons of steel chips that could fill a pickup bed in just minutes. Advanced vibration damping and thermal compensation systems maintain dimensional accuracy within 0.02 of an inch across the entire part length. The CNC system with adaptive control technology automatically adjusts cutting parameters based on real-time force and temperature feedback. It's like having a master machinist intuition built right into the machine's brain. Step into the world of railroad wheel manufacturing, where safety and precision aren't just priorities, they're matters of life and death. Every single day, millions of passengers trust their lives to these wheels, which must withstand enormous forces, extreme temperatures, and millions of rotation cycles. From high-speed trains racing across the European countryside to heavy freight locomotives hauling cargo across the American plains, the wheels we're about to see represent the culmination of over 150 years of railroad engineering evolution. Our journey begins with carefully selected steel billets, heated to a blazing 2,190 degrees Fahrenheit in massive induction furnaces. Watch as the glowing steel is shaped by 8,000-ton forging presses that deliver forces equivalent to the weight of 800 elephants. This forging process aligns the steel's grain structure, creating the incredible strength needed to support railcars weighing 25 tons. The wheels are then normalized in computer-controlled furnaces, cooling slowly over 48 hours to achieve the perfect balance of hardness and toughness. Quality control begins immediately. Ultrasonic testing reveals any internal defects that could prove catastrophic in service. Now the precision work begins. Each wheel blank is mounted on state-of-the-art CNC wheel lathes, masterpieces of German engineering capable of maintaining tolerances tighter than the thickness of paper. These machines feature massive chucks 10 feet in diameter that grip the wheel with hydraulic pressure equivalent to 50 car jacks. The cutting tools are specially designed carbide inserts, each costing $200 and engineered to maintain sharp edges through thousands of cuts. Computer vision systems scan each wheel, creating a three-dimensional map that guides the machining process. This is where artistry meets engineering. The wheel profile isn't just a simple curve, it's a complex mathematical shape that determines how the train will ride, steer, and brake. Watch as the lathe creates the tread surface with its precise 1-in-20 taper, the flange that keeps the train on the rails, and the intricate root radius that prevents stress concentrations. Each cut is monitored by laser sensors measuring to within 0.01 millimeters. Surface finish must be perfect. Any imperfections will create wear that could lead to derailment at 200 miles per hour. Here we're looking at one of the most demanding machining operations out there, boring and facing an 8-inch diameter hole through massive steel components. This isn't your typical drilling operation. We're talking about creating precision holes through materials that could stop a tank round. These operations are common in heavy industrial applications like hydraulic cylinders for mining equipment, deep hole drilling for oil drilling, and cylinder blocks for massive diesel engines. The horizontal boring mill dominates this operation with its massive spindle assembly, capable of reaching several feet into the workpiece. The boring bar itself, a precision tool weighing hundreds of pounds, must remain absolutely rigid while cutting forces try to deflect it. Advanced vibration damping systems and precision spindle bearings ensure cutting tool stability. The cutting insert, $300 of carbide engineering, must maintain a sharp edge while removing cubic inches of steel per minute. Watch as a massive cutting tool begins its journey through steel, creating this perfect 8-inch hole. The cutting parameters are carefully calculated. Too aggressive, and the boring bar will deflect. Too conservative, and productivity suffers. High-pressure coolant floods the cutting zone, not just for cooling, but to flush away the continuous stream of steel chips that could jam the operation. The machine's computer numerical control system automatically compensates for boring bar deflection, ensuring the final hole diameter stays within a tolerance of 0.01 inches across its entire length. Now comes facing, creating a perfectly flat surface perpendicular to the hole. The facing head, equipped with multiple cutting inserts, machines the surface at feed rates measured in thousandths of an inch. Once complete, this component could become part of a mining excavator's hydraulic cylinder, where it'll control movements of machinery weighing hundreds of tons. The precision we just witnessed ensures these systems run reliably for decades, moving mountains one bucket at a time. Our final segment showcases the artistry of complex turning operations, creating intricate threaded components that combine multiple diameters, sophisticated geometries, and precision threads in a single setup. These parts might look simple, but they represent the pinnacle of machining mastery, demanding perfect coordination of cutting tools, spindle speeds, and feed rates to achieve dimensional perfection across every feature. This component features multiple turned diameters, each with different tolerances and surface finish requirements. Notice the stepped geometry requiring different cutting tools for each operation, the internal threading that must align perfectly with external features, and the complex radii that seamlessly blend surfaces. The threading operation demands specialized thread cutting tools and precise spindle synchronization. The computer numerical control system coordinates spindle speed with carriage speed to create perfect thread pitch. Tool changes happen automatically, each cutting insert optimized for its specific operation. Single-point threading tools carve helical grooves with mathematical precision, creating threads that will mate perfectly with corresponding components. Thread pitch accuracy within 0.0001 inches, correct thread form angles, and perfect surface finish all combine to create threads exceeding commercial standards. The completed part undergoes comprehensive quality inspection using specialized thread gauges, optical comparators, and coordinate measuring machines. Every dimension, thread specification, and surface finish gets verified against engineering drawings. These complex turned parts often become critical components in aerospace applications, medical devices, or precision instruments, where failure isn't an option.
Pick up a stone. Bright red, heavy, looking like dried blood. It doesn't smell, doesn't burn, doesn't radiate. Just a beautiful mineral. Now throw it into a furnace at 1300 degrees Fahrenheit, and liquid metal flows out. Silvery, heavy, cold to the touch. The only metal on Earth that stays liquid at room temperature. Mercury. A substance that has mesmerized alchemists for millennia, poisoned kings, and powered industry. And it's extracted from a stone that looks like a gemstone, but is actually just ordinary sulfide. Today, we're at a mine and processing plant where red rock turns into liquid silver. If you're into deep dives like this, subscribe and hit the bell so you don't miss new episodes. This red rock is called cinnabar, mercury sulfide, one of the few natural compounds where mercury shows up in Earth's crust. The chemical formula is simple: one mercury atom, one sulfur atom. Basically, nature locked liquid metal inside a sulfur cage, and to get it out, you've got to break that cage with heat. If you crack a chunk of cinnabar, the fracture surface reveals crystals with a diamond-like shine. The beauty's deceptive because the powder from this mineral is poisonous. Cinnabar was known even in ancient times. Egyptians used it as pigment, Romans painted palace walls with it, and Chinese alchemists believed the red ore was the key to immortality. Deposits are scattered across the planet, but the main ones are in Spain, Slovenia, China, and Kyrgyzstan. The Spanish mine at Almaden operated for nearly 2,000 years and gave the world more than a third of all mercury ever extracted. The ore sits in volcanic activity zones because mercury rises with hot solutions from deep within Earth's crust and settles in rock fractures as bright red veins. Sometimes cinnabar is so rich that the rock looks like someone painted it with scarlet dye. Mining starts underground. Miners drill into the rock with pneumatic jackhammers, place charges, and blast, bringing the whole face down. They load the ore into mine cars and haul it to the surface. It's hard, dangerous work. Even down in the mine, mercury vapor seeps from the rock, so ventilation runs at full blast. Mercury content in the ore is usually low, 1 to 12%. The rest is waste rock, sandstone, clay, quartz. But even 1% is worth going after because mercury fetches a high price. At the surface, the ore gets crushed in jaw crushers. 2 steel jaws squeeze the rock, breaking it down to gravel size. Then, vibrating screens sort the pieces by size. The fines go straight to the furnace. Oversized chunks loop back for another round of crushing. Dust is a whole other problem. It carries mercury, and breathing it is dangerous. So the crushing plant runs heavy exhaust and wet dust suppression. Workers wear respirators, and at the entrance, there's a mercury vapor monitor. If the needle swings into the red, they shut down the plant and air it out. Now comes the most critical step, roasting. The principle is simple yet brilliant. Heat cinnabar to 1100 to 1300 degrees Fahrenheit in air, and the sulfur bonds with oxygen and escapes as sulfur dioxide gas, while the mercury vaporizes. 2 substances locked in stone for millions of years part ways forever, one into the air, the other into a pipe. Roasting furnaces come in different designs, but the classic is a rotary kiln. Picture a massive steel drum, 60 to 100 feet long, set at a slight angle. Ore gets fed in from the upper end, burners fire from the lower. The heat inside is so intense, the furnace walls glow a dull cherry red. The kiln rotates slowly, tumbling the ore, gradually pushing it downward as it heats up more and more. When the temperature hits the sweet spot, the cinnabar breaks down. Sulfur burns with a bluish flame, and mercury vapor, invisible and deadly, rises and travels with the flue gases into the condensation system. The spent rock, now stripped of mercury, spills out the lower end of the furnace into a waste pile, gray, lifeless, having surrendered everything valuable to the fire. Condensation is the moment when invisible vapor transforms into that actual liquid metal. Gases from the furnace pass through a long system of pipes and chambers that gradually cool down, usually with water fed through jackets on the outside. Mercury condenses first. Its boiling point is only 675 degrees Fahrenheit, so when the gases cool below that mark, silvery droplets start settling on the condenser walls. They trickle downward and collect in receivers, steel or ceramic containers. The sight is mesmerizing. From the pipe, as if from nowhere, heavy silvery liquid drips down, falling into the collector with a distinctive, soft sound. Not a clang, not a thud, but something in between. Because mercury is viscous and heavy, 13.5 times heavier than water. A quart of mercury weighs more than 28 pounds. Try picturing a quart of milk that weighs as much as a bucket of cement. The raw mercury from the condenser isn't ready for sale yet. It's swimming with impurities. Soot particles, water droplets, traces of other metals. It's cleaned in several stages. First, they filter it through chamois leather or special fabric. Mercury passes through the pores while the dirt stays behind. Then, they wash it with diluted nitric acid, which dissolves impurities like zinc, lead, and tin, leaving the mercury itself untouched. The final purification is vacuum distillation. Mercury gets heated in a vacuum, where it evaporates at a lower temperature, while impurities with higher boiling points remain at the bottom. They collect the condensate, and now you've got mercury at 99.9% purity. It's poured into standard steel flasks holding 76 pounds. That's the international standard called a flask. The container's small, about the size of a thermos, but lifting it one-handed? Not easy. All because of that incredible density. Safety at a mercury plant is a world unto itself. Mercury vapor has no color and no smell, but it's extremely toxic. Just a few hours of breathing it can give you serious poisoning. Chronic exposure destroys the nervous system. That's why hatters in the 19th century went mad. They used mercury to treat felt and inhaled the fumes for years. Hence the phrase, mad as a hatter. In a modern plant, the entire facility operates under negative pressure. Air is constantly pulled inward, not pushed outward, so vapors don't escape into the atmosphere. Floors are coated with a special non-porous covering. If mercury spills, the droplets won't roll into cracks, but stay on the surface where they can be collected with a specialized vacuum or a sulfur trap. Sulfur powder binds mercury into harmless sulfide. Every worker carries a personal dosimeter that measures accumulated vapor exposure per shift. Exceed the limit, and you're pulled off the floor until your levels normalize. Where does all this mercury go? Historically, the biggest consumer was gold mining. Mercury dissolves gold, forming an amalgam. You then heat it up, and the gold evaporates out. Conquistadors in South America used this method, and it's exactly why the Spanish crown exploited almaden for centuries. Today, amalgamation is officially banned in most countries because of the catastrophic environmental damage. But in artisanal mining across Africa and Southeast Asia, millions of prospectors still use it. Poisoning rivers, poisoning soil. Other applications? Chlor-alkali industry, thermometers, barometers, mercury lamps, electrical switches, catalysts. But the world is slowly moving away from mercury. In 2013, the Minamata Convention was signed, named after a Japanese city where, in the 1950s, thousands of people suffered devastating poisoning. Mercury leaked into the bay from a chemical plant. It built up in fish. And the people who ate that fish started losing their sight, their hearing, their coordination. The Minamata tragedy became a symbol of mercury pollution for decades to come. Mercury production worldwide is plummeting. Back in the mid-20th century, mines pulled out up to 10,000 tons a year. Now, less than 2,000. Most mines have shut down. The famous Almadine in Spain stopped operations and turned into a museum. These days, mercury increasingly comes from recycling, old thermometers, lamps, industrial waste. But humanity can't completely abandon it yet. Some chemical and electrochemical processes simply have no substitute. When you stand next to a flask where this heavy, silvery liquid sloshes around, it's hard to believe that an hour ago it was part of a red rock that sat underground for millions of years. Cinnabar guarded mercury like a safe guards valuables, and only fire could pick that lock. An ancient process, simple at its core, dangerous in execution, and still without an alternative.
Every year, millions of tons of wood waste are generated worldwide, and most of it could simply vanish into landfills. But this is where a remarkable story begins, transforming ordinary wood chips, shavings, and even old furniture into solid boards that become the foundation of our everyday comfort. This isn't just manufacturing, it's a second life for timber. Picture mountains of raw material as tall as a 5-story building disappearing into steel monster machines only to emerge in a completely new form. And right now, we're about to reveal all the secrets of this process, which combines scale, precision, and a touch of engineering wizardry. It all starts at a massive raw material yard, where the foundation for future boards arrives in a continuous stream. Contrary to popular belief, high-quality timber is almost never used in their production. On the contrary, the manufacturing philosophy is all about giving wood waste a second life. Mountains of raw material are brought here, reaching heights of dozens of meters. The foundation is industrial wood chips obtained from low-grade timber. A huge proportion comes from sawmill waste, slab wood, offcuts, and thin battens. Wood processing waste is also heavily used, such as shavings and sawdust generated at furniture factories. A separate and important category is reclaimed timber. Old wooden pallets, crates, and even used furniture are given a chance at a new life as part of chipboard after thorough cleaning. Every batch of raw material undergoes strict incoming quality control. The first stage of cleaning is removing metal inclusions. Powerful electromagnetic separators screen the flow of raw material, extracting nails, staples, and any other metal fragments. The material then passes through screening systems to remove sand, stones, and other debris. If whole logs are used in production, say 20-foot lengths, they must pass through a debarking machine. Inside a massive rotating drum or using special cutters, the bark is stripped away. This step is critically important because bark has a different structure, contains loads of dirt, and significantly deteriorates bonding quality. The prepared and cleaned timber begins its journey along a conveyor belt hundreds of meters long, carrying it towards the first stage of mechanical transformation. It disappears into the steel jaws of a giant chipping machine, an industrial monster the size of a small room. Spinning at thousands of revolutions per minute, its blades bite into the timber with incredible ease, transforming solid pieces into a stream of uniform chips a few centimeters in size. But this material is only semi-finished. The resulting chips are too large and coarse. So the next step is finer, more precise secondary grinding, which takes place in specialized particle mills. It's here, amid the roar of high-precision equipment, that the actual wood particles are born, the ones that give the final product its name. At this stage, the geometry of the particles becomes absolutely crucial.